including the space station that houses our astronauts. But despite the importance of this region, it is not well known. That's why NASA and the University of California, Berkeley built ICON.
The ionosphere itself, where ICON will be doing most of its work, is where the GPS signals travel through, it's where astronauts travel, and so it's very, very key for us to understand this region because it has profound effects on us here on Earth because of what space weather is doing to us, but it also gets profound effects of what our Earth weather is doing to the ionosphere.
By studying how the ionosphere reacts to Earth's atmosphere, it will help scientists and meteorologists forecast the conditions in our space environment, reducing its negative effects on our technology. From 360 miles above Earth, at a 27-degree inclination, ICON will sample ionospheric variations in the lower boundaries of space over the course of hours, days, seasons, and decades. Traveling at more than 4 miles per second, or about 30 times faster than a commercial airliner, this satellite will examine how the ionosphere reacts to our planet's weather.
The ionosphere is highly variable, more variable than we ever expected. Now we think that the answer to understanding the conditions in the ionosphere and being able to predict those conditions relies on our ability to understand how weather below is forcing space weather above. So ICON's built to capture all the information that we think we need to understand the mechanisms and the process by which our lower atmosphere affects our upper atmosphere.
ICON will be sent into orbit by a Northrop Grumman Pegasus XL air-launched rocket. The rocket has 3 solid propellant stages and can deploy satellites weighing up to 1,000 pounds into low Earth orbit.
We selected the Pegasus XL launch vehicle. It provided an excellent combination of mission performance and flexibility for the mission design for a spacecraft of the mass of ICON.
The launch of ICON will be anything but ordinary. It will be carried on the underbelly of Northrop Grumman's L-1011 Stargazer aircraft, a launch pad far above the clouds in the sky.
The one unique thing about Pegasus is that it's air-launched. So the L-1011, which is the last flying plane of its kind, it is essentially our launch pad in the air. It's a mobile launch pad that flies up to about 40,000 feet, and that's where we launch the Pegasus from.
With the tireless effort by the team to reach mission success, it is time for ICON to prepare for another launch attempt.
There are no constraints on the
For all involved, this is familiar territory. Yet something feels different this time.
It's taking a little extra time and extra care with the launch vehicle, but we're about there.
Why I'm excited right now is that we're getting so close to launch, and it has taken a huge effort to get there.
Vandenberg Air Force Base in California is bustling with activity. The excitement is palpable as ICON literally comes together. Pegasus stages 1, 2, and 3 are assembled. The aft, skirt, and fin installation are now complete. ICON's solar array illumination is tested. And finally, the spacecraft is mated to Pegasus.
Once it's mated to the rocket, there'll be a compatibility test between the rocket and the observatory. So the rocket will be the interface to communicate to ICON so we can command it. Once we certify that, we will encapsulate it. We'll put it on a transport platform, roll it out to the hot pad, and then integrate it to the L-1011.
Now that processing and mating are complete, the ICON mission takes off from Vandenberg. Hours later, it arrives at Cape Canaveral Air Force Station skid strip in Florida. Important logistics must be coordinated with the 45th Space Wing prior to launch. Once in Florida, there is a week of processing and testing prior to launch day. Lieutenant Samantha Parr is in charge of making sure ICON launches into a safe environment.
So I keep track of the weather, I keep track of our instrumentation, and I keep track of our surveillance. and I provide a recommendation to our Launch Decision Authority, and he or she can make a determination on whether or not we're clear to launch.
We are now at launch day. The team has been here before, and optimism is guarded.
It's been a lot of work to get here. At this point, we kind of see the end, and we're looking forward to a mission and putting the satellite into orbit and seeing what that science does in the future.
Anticipation builds to a fever pitch. All systems are now go for launch.
The actual time parameters for a launch of a Pegasus mission is much different than your standard ground-based missile launch. That's tied to the fact that the Pegasus literally has a first stage by being on an airplane. The airplane's at 40,000 feet, it's moving close to 500 miles an hour. It's moving, you can't stop it, you can't slow it down, it is going and it's dynamic.
The Stargazer jet takes off from the skid strip at the Cape Canaveral Air Force Station.
L-1011 is airborne at this time.
The L-1011 has now reached a cruising altitude of 40,000 feet and has begun flying in a racetrack pattern.
We fly a pattern called the racetrack. It's an oval in the sky, and so the airplane takes off, flies through the launch point at a lower altitude as it's climbing to the point we're going to launch at, which is roughly 40,000 feet.
We verify that all of our GPS are synchronized and ensure that we are going to put the launch vehicle in the correct heading so that we get the spacecraft into the correct orbit.
LC Peg, go for fin pin retract. LPO, go for fin pin retract and fin sweep.
LC, Senior MEVCO, countdown L-1011 is in the box.
About 50 miles offshore of Daytona Beach, the Pegasus XL is released from the L-1011.
With the countdown, we hear drop on my mark, 3, 2, 1, drop. And we push a button in the cockpit. The hydraulic releases actually release the rocket.
Pegasus away.
The rocket drops for 5 seconds, the airplane climbs for 5 seconds, and at the end we have a fairly good safety margin.
5 seconds later, the Pegasus rocket ignites.
Stage 1 ignition has been confirmed.
That's the minute that I consider T0 for me.
Soon after Pegasus ignites, first stage booster burnout and separation occurs.
Stage 1 separation confirmed. Stage 2 ignition has been confirmed and attitude is nominal.
Followed by fairing separation and second stage separation.
Fairing deployment has been confirmed.
After third stage separation, the ICON satellite is deployed into its lower Earth orbit.
Spacecraft separation from the Pegasus launch vehicle. So thank you, old friend, for doing that, and good luck, ICON.
It is a monumental moment for the entire ICON team, who banded together to overcome hurdle after hurdle. Powered by teamwork and unwavering dedication to its mission, ICON has overcome all obstacles in its path on the way to a successful T0.
Well, it's been quite a ride. It's been an incredible journey to get to this point and required the sacrifice of a very large team. We couldn't be more excited and honored to have launched the ICON spacecraft in orbit.
Great job for the team. Congratulations, ICON. Status check to proceed with terminal count.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Rocket report range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Delta.
In that moment, a controlled explosion is released with such intense power, it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story.
To shed light on the mysteries of our closest star, the Sun.
The Sun, the heart of our solar system. It's as familiar as anything we know. Although the Sun has been studied for millennia, it still holds unsolved mysteries about its effects on our daily lives. To better understand the Sun, NASA is preparing to launch a spacecraft called the Parker Solar Probe. It will lift off from Cape Canaveral Air Force Station near the agency's Kennedy Space Center, located in Florida. It's a mission of unprecedented opportunities that could revolutionize our understanding of our star and the Sun's atmosphere, the corona, a long-time destination goal for scientists such as Dr. Nikki Fox.
Going into the Sun's corona for the first time, going up close and personal with our star, to be able to answer some of the mysteries that live in this coronal region. Why is the Sun's corona hotter than the surface of the Sun? Why is there a solar wind? Why does this atmosphere, this corona, become so energized that it can move away from the Sun at supersonic speeds and bathe all of the planets?
And now that Parker has finally arrived on the Space Coast, we're one step closer to solving those mysteries. Delivered on an Air Force C-17, it's not every day this crew hauls a payload destined for the history books.
Overall, the mission itself is relatively simple. I'd say the biggest challenge is probably the load portion.
A little extra to it too, because normally we're just hauling generic things, but not a $1.5 billion solar probe.
And there's only one world-class program that specializes in missions of this caliber, NASA's Launch Services Program, a team that matches the industry's top-performing rockets with the cutting-edge spacecraft NASA is committed to launching.
LSP is NASA's bridge to space. Basically what we do is we link a spacecraft customer such as the Parker Solar Probe up with a launch vehicle provider such as United Launch Alliance. And we provide them with a custom-built ride to space on a carefully selected launch vehicle.
Engineers and scientists with Astrotech and the Applied Physics Lab teams will spend its last few months checking and testing every element and completing final assembly to be sure it is ready to leave Earth for its epic trip to the Sun. Parker must be perfect before T0 arrives.
Before we start integration with the launch vehicle, we have to do final integration of the spacecraft. That includes attaching the magnetometer boom and magnetometers. We'll then also integrate the solar arrays. And then finally, right before integration with the launch vehicle, we'll add the thermal protection system or thermal shield.
The Parker Solar Probe will be the first mission to kiss the Sun, flying through the searing heat of the Sun's corona, traveling closer to the surface than any other spacecraft before. And to do that, it will need to go faster than any other spacecraft in history. That's why, for the first time ever, NASA's Launch Services Program selected the United Launch Alliance Delta IV Heavy rocket.
Parker Solar Probe will be the fastest human-made object ever. We are traveling at an unbelievable 430,000 miles per hour.
NASA selected Delta IV Heavy for the Parker Solar Probe mission because of the combined energy of the booster, Delta cryogenic second stage, and the third stage, which means that we have enough energy to go to the Sun.
I mean, if you look at the vehicle, it's huge. It's approximately 50 feet wide, 170 feet long, and about 190,000 pounds.
Going out and seeing the Delta IV Heavy on the pad is a truly awe-inspiring experience. Just seeing that amount of raw power right in front of you is just incredible. 3 boosters, our second stage, and then we have a third stage. We're a tiny little spacecraft. We look like a little hood ornament on the top of the Delta IV.
Throughout its 7-year mission, NASA's Parker Solar Probe will swoop through the Sun's atmosphere, carrying more than scientific instruments on this historic journey to the center of our solar system. It will also hold a piece of humanity itself. Back in March 2018, the public was invited to submit their names. Over 1 million were loaded into a memory card and mounted on a plaque bearing a dedication to the mission's namesake. Dr. Eugene Parker was a heliophysicist ahead of his time. He proposed this mission back in 1958 after discovering the existence of the dangerous and unpredictable solar wind.
The reason it has taken us 60 years to be able to fly this mission is not because we weren't interested. It really is because it has taken that long for technology to be developed to allow us to do this incredible mission.
During the Parker Solar Probe's perilous dive into the sun's corona, the atmosphere, it will navigate dangers never before experienced by a NASA deep space mission, 3 million degree plasma, sporadic solar flares, and delayed communication with Earth. Traveling this close is only possible because of the spacecraft's protective heat shield, the single largest piece of hardware and the most critical to mission success. One slight error in its performance could cause the probe to melt and the mission would be lost.
Parker Solar Probe is actually going and touching the sun. When we actually get to our closest approach, the heat shield on Parker Solar Probe will be at about 2,500 degrees Fahrenheit on the front surface. The back surface is going to be at about 600 degrees Fahrenheit, but then the spacecraft bus will just be operating at a normal room temperature almost. It's a little bit higher, about 85 degrees. The previous missions have been really important for solar science as we study from afar, and we can learn a lot from studying from afar. But the Parker Solar Probe is actually going and touching, almost kissing the sun, so we can learn so much more.
The spacecraft is now ready for flight, but it can't get millions of miles to the sun unless it gets a boost from a specially made third stage by Northrop Grumman.
The Northrop Grumman third stage team specifically designed and built this third stage for the Parker Solar Probe mission. The Parker Solar Probe needs a third stage because even though the Delta IV Heavy is an incredibly powerful rocket, the third stage is what gets it the extra boost to get into its final orbit around Venus and to the Sun.
Parker Solar Probe is the hardest trajectory that I've ever worked on for a couple of different reasons. One, we're flying on the Delta IV Heavy, which is the largest and most complex rocket that Launch Services Program has ever been involved with. And in addition to that, we're flying a third stage that has its own guidance, navigation, and control system on board. So from a trajectory, GNC standpoint, it's like flying two missions at once. Parker Solar Probe it's called a heliocentric orbit, which means it's orbiting around the sun. And using a gravity assist, usually we use that to add energy to the spacecraft's orbit when we go out to places like Jupiter or Saturn or Pluto. In this case, we're going in the opposite direction. We're heading inside the orbit of Mercury. The folks at Applied Physics Lab have come up with a very unique trajectory where the spacecraft is going to use the mass of Venus to slow themselves down. And not only are they doing that one time, they're actually going to do that 7 times in a row over a space of 6 years in order to get the spacecraft perihelion, because we're orbiting the sun, down below 10 solar radii. So when we're in orbit around an object, whether it's the Earth or the sun, we go fastest when we're closest to that object and slowest when we get to the top of this orbit. And therefore, when we pass very close to the sun, which is the most massive object in our solar system, we're going approximately 430,000 miles per hour relative to the sun. This really is rocket science.
During the early stages of launch, the Parker Solar Probe will be encapsulated in a large payload fairing. The Delta IV Heavy is a massive rocket designed to launch a school bus-sized spacecraft. The last step at Astrotech is safely securing the 1,510-pound spacecraft in a fairing that, by comparison, makes the probe look small.
To get to the sun, we actually need a lot of energy. Because of that, we need a very large launch vehicle. And in fact, we have the biggest launch vehicle we can get. And because of that, this fairing that is associated with this launch vehicle is very large. But because we're a small spacecraft, we take up a very small amount of space in that fairing. And that's the reason why it looks like we're a very small spacecraft on a very large vehicle. But once the spacecraft is encapsulated, that's it. We no longer get to touch it.
The encapsulated probe is now ready for a slow, steady ride to the launch pad at Cape Canaveral. It will be transported atop a K-Mag made for transporting special payloads. It can hold thousands of pounds, spin 360 degrees, and keep its payload level when traveling up inclines.
One of the nice parts about the K-Mag that we have is it has very precise steering capabilities, and it also has a lot of different steering capabilities. So it gives us a lot of capability to get into a precise location, both for hoisting operations down in the hoistway, as well as different mating operations in our horizontal integration facility.
Now, the ULA team will carefully lift the Parker Solar Probe safely nestled inside its payload fairing to mate it atop the massive Delta IV rocket. To keep the payload safe during the entire lifting operation, there's a special channel constructed in the tower itself known as the hoistway that allows the payload to be lifted without any influence from adverse weather or environmental conditions.
The exciting part about today is it's when we finally get the customer out here, we get the spacecraft hoisted, and that's what it's all been about. A heavy mission by itself is always exciting, but then you add in the factor of having a NASA exploration mission, the mission to touch the sun. That accompanied with the heavy, it's just an exciting launch for the public, a great exciting launch for ULA. It'll be a lot of fun to see and it'll be a lot of fun to track over the next several years as it gets into its final orbit around the sun.
NASA's Launch Services Program has now brought together the payload and its ride to space. After taking different roads to the launch pad, finally the spacecraft and the vehicle are together.
Goddard runs all of the Living with a Star missions, and this is what's called a flagship mission. It's one of the most important things that our science does. So the anticipation of launch is just tremendous. I've been working on this project for 10 years, and now to see it actually ready to go is just a tremendous feeling. It's really hard to describe.
Now, as T0 is just days away, it's up to ULA and LSP to make sure they're operating as one. In the hours before liftoff, the mobile service tower gantry rolls back, leaving the mighty Delta IV standing on its own, ready for launch. The final countdown to T0 is underway.
As the NASA launch director, ultimately what I do is give the go or the no-go. That's a very simple statement, but there's a lot that goes behind that. It's a culmination of a bunch of professionals that know their jobs, they know it well, and all I have to do is make sure all those pieces are in place. Then it's easy for me to make the decision to launch.
Thousands of rockets have launched from Florida's Space Coast, but this is the first designed to fly to the sun. Big Delta IV Heavy rocket is ready to roar to life with more than 2 million pounds of thrust to power the Parker Solar Probe on a trajectory of millions of miles to its destination.
Proceed with terminal count. First stage systems. Propulsion. Go. Hydraulics. Go. Locks. Go. Launch director. You have permission to launch. Status check. Go Delta. Go PSP.
3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
All 3 RS-68s look good in the full thrust mode. Response looks good. Vehicle trajectory looking good, right down the middle of the range track.
And liftoff.
10 seconds.
I think what you get a sense of is just how awesome the universe is and how tiny each of us are in the grand scheme of the wonder that exists out there. Realizing that and realizing just how overwhelmingly huge the Earth is, how overwhelmingly the physics dominates what we're doing, and that we're living in this solar system, galaxy, universe, lets you know that this is someplace kind of special. To be a part of the mission that serves on station, to be part of the mission that goes exploring space into this vastness is simply, one, an honor, but two, almost mind-changing. Mind-changing because we have businesses, we have missions here, we're focused on accomplishing the near-term goal. You get up there and you see the overwhelming portion of the Earth, the vastness that you're exploring into, and you go, wow, there is just so many questions, so much for us to do, so much for us to be able to help our brothers and sisters with. we had a special opportunity on space station because of the window arrangements to be able to seriously get immersed in the imagery. Going to the windows to watch areas that were of great interest. Patagonia, for instance, is just a beautiful, rich environment of earth tones as well as the glaciers, the water. It is just picturesque to the point where you go, I need to go visit that place. You want to find things on the earth because it is memorable but also insightful. For instance, you're going over a tan and you go, oh, you know what, I bet you I'm close to the pyramids. And so you go to the window to take a look at if you are close to the pyramids, and then take some shots that you can take home. There are areas of the world that have volcanoes and you just happen to catch in one photograph 2 or 3 active volcanoes. It's a nice experience to be able to look out the window and go, wow, we really are seeing the living earth living, and being able to be a part of it from such a vantage point. We saw Hades troubles while we were up there. The Gulf oil spill from the horizon occurred while we were up there. A number of hurricanes or tropical cyclones occurred while we were up there. You know there's a ton of energy in there. You know it's heading towards populated areas. It's not beautiful at that point. It's utter respect is what I would categorize it. I got visited by 3 space shuttles. Several of the crew members never looked outside the cupola before. I would bring them one at a time to the cupola. Tell them to close their eyes, open up all the windows, the shutters on the windows, and then tell them to open up their eyes. In that instant, when you're overwhelmed with that vista, when your eyes see nothing but the beauty of the earth, every single one of them, every single crew member that I brought in there for that exposure cried. It is heart-stopping. It is soul-pounding. It is breathtaking.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
You're looking at live footage of an Ariane 5 rocket in Kourou, French Guiana. At the very top of that extraordinary machine, one of the largest rockets in the world, we find the most ambitious space observatory ever built, the James Webb Space Telescope. And today is launch day. From all of the people all around the world working on today's launch, good morning, bonjour, buenos dias. This is live coverage of the historic launch of the James Webb Space Telescope. I'm Michelle Thaler, speaking to you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And I am very excited to be with you today. Today, the James Webb Space Telescope begins its journey to explore the edge of our observable universe, and its journey into history as well. This launch has been years in the making, and the world has turned out to watch. We'll have a lot to discuss both before and after launch, but let me set the scene for what's going on around us. While I'll be anchoring coverage from here at NASA Goddard, the big stuff happens today here at the Centre Spatial Guyanais, the Guyana Space Center in French Guiana. This is the main launch site for the European Space Agency, a close partner in this once-in-a-generation mission, and the home of all Ariane launches.
The weather's been a little bit inclement,
Katie
so we're
Haswell is
keeping an
there
eye
at the
on
launch
that, but
facility and
otherwise
joins me now
everything's
live
looking
via satellite.
absolutely great. And
Okay,
I have
how
to
are
tell
things
you,
in Peru,
there's
Katie?
just such a buzz of excitement here in the Mission Control Center. It's a remarkable feeling. Michelle, right now we're topping up the tanks really good. The boards are upper stage of the vehicle. The mission controllers are focusing hygienic arms and they clamp onto the upper stage. We are go for launch. We've had our eye on the cryogenic fuel, which has to be kept very, very cold. So inclement, so we're keeping an eye on that. But otherwise, everything's looking absolutely great. And I have to tell you, there's just such falling a buzz of excitement here in the Mission Control Center. It's a remarkable feeling. The sky booth in the Mission Control Center, we have the upper stage of the vehicle. So we've got two great big arms, the European Space Agency clamp onto the upper stage. They're standing by, hi guys, standing by to very, very cold. So commentary when we get to about right until the last minute to launch. But right now, Michelle, you'll see those arms kind of green. We're falling away just before launch in the last couple of seconds.
We'll be coming back to Katie for the final phases of the countdown in just a little bit.
Sky booth in the Mission Control Center,
So,
we have
I'm an astronomer,
NASA's
and this
Rob
launch is a huge
Navius
deal for me.
and the
I am
European
personally
Space
really
Agency's
excited.
Luce
But
Fabricate.
why is this such a
They're
big event
standing
for
by. Hi
everyone?
guys, standing by
The
to
Webb
take
telescope
on
is nothing
the
less than
commentary
humanity's
when we
next
get
effort
to
to move
about
closer
15
to
minutes to
understanding
launch. But right now,
some
Michelle,
of the biggest
all the boards
questions
are
about
green.
the origin
We're
of our
going for
universe.
launch. Back
And
to
it's
you,
not
Michelle.
just the origins of distant stars
We'll be
and
coming back to
galaxies,
Katie for the
but
final
it's the
phases of the
story
countdown
of
in just a
us,
little bit.
you and me, how we got here.
I'm an astronomer,
And
this
speaking of
launch
questions,
is a huge
we'd like
deal
to
for
include
me.
yours
I am
in this
personally
historic event.
really excited.
On whatever platform
But
you're watching
why
our
is this such a
coverage,
big
drop
event
your
for
questions
everyone?
with the hashtag AskNASA.
The Webb telescope is
Later in the
nothing less
broadcast,
than
we'll answer
humanity's
some of them
next
live on
effort
air.
to move closer to understanding
It
some
can't be
of the
said enough
biggest
that this is a
questions
mission
about
for
the origin of our
anyone who's
universe.
ever looked up at the night
And it's
sky
not
and
just the
wondered.
origins of distant
People
stars
all
and
over the world
galaxies,
are sending
but
in
it's
their
the
best
story
wishes
of
for the
us,
success of
you
Webb.
and me,
And let's look
how
at some
we
of them
got
now.
here.
And speaking of questions, we'd like to include yours in this historic event. On whatever platform you're watching our coverage, drop your questions with the hashtag AskNASA. Later in the broadcast, we'll answer some of them live on air.
Veel succes, Webb.
It can't be said enough that this is a mission for anyone who's ever looked up at the night sky and wonder. People all over the world are sending in their best wishes for the success of Webb. And let's look at some of them now. We're still on track for a launch at 7:20 a.m. Eastern U.S. time. 2 days ago, the rocket rolled out to its launch pad in Peru. Of course, there's already been a lot of activity on the launch site. Primary fueling procedures were completed early this morning, preparing the giant Ariane 5 rocket for flight. Let's watch the scene for a moment.
हार्दिक शुभकामनाएं।
We're still on track for a launch at 7:20 a.m. Eastern U.S. time. 2 days ago, the rocket rolled out to its launch pad in Peru. Of course, there's already been a lot of activity at the launch site. Primary fueling procedures were completed early this morning, preparing the giant Ariane 5 rocket for flight. Let's watch the scene for a moment. We know the world is watching. Today, humanity begins its next bold adventure to extend ourselves out into the cosmos. This is something we do as a whole planet, all of us together. Befitting the global importance of this initiative, let's review some of the basic facts about the observatory shared by people all over the world who are looking forward to the Webb mission.
The entire world is looking forward to the launch of the James Webb Space Telescope.
Today, humanity
Let's hear
begins
more
its
from
next
people
bold
around the
adventure to
globe
extend ourselves
about what
out
makes
into the
Webb a
cosmos.
scientific and
This is something we do
technological
as a whole
marvel.
planet, all of us together. Befitting the global importance of this initiative, let's review some of the basic facts about the observatory shared by people all over the world who are looking forward to the Webb mission.
The entire world is looking forward to the launch of the James Webb Space Telescope. Let's hear more from people around the globe about what makes Webb a scientific and technological marvel.
Webb is zo groot dat deze in origami-stijl moet worden opgevouwen om in de raket te passen, om vervolgens in de ruimte als een transformer te worden uitgevoerd.
Les 5 couches de son écran solaire le protégeant du rayonnement infrarouge émis par le Soleil, la Terre et la Lune. C'est un peu comme avoir une crème solaire avec un FPS de 1 million.
Webb is zo groot dat deze in origami-stijl moet worden opgevouwen om in de raket te passen, om vervolgens in de ruimte als een transformer te worden uitgeklapt.
Les 5 couches de son écran solaire le protégeant du rayonnement infrarouge émis par le Soleil, la Terre et la Lune. C'est un peu comme avoir une crème solaire avec un FPS de 1 million.
Thousands of people all over the world have worked for years to get us to today's launch. The core partners, NASA, the European Space Agency, and the Canadian Space Agency are the principal players. But a vast core of engineers, scientists, private companies, and more have had a hand in building this one-of-a-kind scientific platform. Without a doubt, this is the most complex spacecraft ever built, with revolutionary technologies, daring mission goals, and a whole lot of people all over the world have worked for years to get us to today's launch. We'll hear from our partners later in the broadcast. The core partners, first, NASA, let's hear from someone representing the science community, and the Canadian Space Agency are the principal players. Space exploration. But a vast core of engineers, scientists, private companies, and more have had a hand in building this one-of-a-kind scientific platform. Without a doubt, this is the most complex spacecraft ever built, with revolutionary technologies, daring mission goals, and a whole lot of personal passion and commitment. We'll hear from our partners later in the broadcast, but first, let's hear from someone representing the science community with a rare perspective about space exploration.
Most powerful telescope in space yet. Hello, I'm ESA astronaut Study the big questions, living and questions like the International Space Station ISS. How did galaxies I'm very excited to follow the James Space Telescope launch and planets you all from space. The sun. Even with the naked eye, we might there even be life on other planets? Sharp and brilliant. James Webb Space Telescope is a joint project with NASA, James Webb Space Telescope, and the Canadian Space will be the largest and by most powerful telescope people with origins in many countries. It was built and studied the big questions like science, questions like everywhere, where do we come from? How did galaxies form, like our Milky Way? How are stars and planets born? Like the sun.
NASA Goddard is the home of the Webb telescope, with big sections designed and built here. But actual mission operations take place
is a joint project between NASA,
this is the Mission Operations Center,
and the Canadian Space
at the Space Telescope Science Institute in Baltimore.
Of
After launch, this facility will command and control Webb for the duration of the mission. We'll be looking at the mock at key moments throughout the broadcast, and this will become a familiar location for viewers in the weeks ahead as the Webb team begins to set up the telescope. NASA Goddard is the home of the Webb telescope, with big sections designed and built here. So as we move closer to launch, actual mission operations take place. We'll keep a picture of the launch facility right here on the screen. This is the Mission Operations Center, or MOC, we're going to talk about some of Webb's Science Institute in Baltimore. After launch, this facility will command and control Webb for the duration of the mission. We'll be looking at the look of this particular machine is a direct result of familiar location for viewers in the weeks ahead as the Webb team begins to set up the telescope. We've got an expert pair of guests with me this morning to help explain those science goals and much more. So as we move closer to launch, I'm joined now on the set. We'll actually keep a picture of the launch facility right here on the screen. But for the next 10 minutes or so, we're going to talk about some of Webb's principal science goals. If you've ever seen a telescope for Webb's mirroring instrument from the European Space Agency. So of course, the look of this particular machine is a direct result of a step back and talk about the science goals of Webb. This is the part that really excites astronomers like all of us. To help explain those science goals and much more. There's unusual things about it being an infrared telescope. There are specific science deputy project scientist for exoplanet science. So maybe you could start us out, Nicole, with you're an expert on exoplanets. How is the infrared really important for your study for Webb's mirroring instrument from the European Space Agency? So
want to study their atmospheres. And
so as a reminder, exoplanets are planets talk about the science goals of Webb.
We're looking
this is
for
the part that
very
really
small
excites astronomers like all of us.
We study their atmospheres.
And I know that
and
there's
Webb
unusual
is
things about
giant
being an infrared
that we're able to
there are
use
specific
to
science goals,
collect
infrared
these small
answers.
signals and look
so maybe you
for
could start us out, Nicole,
infrared
with
signatures,
you're an expert
chemical
on
signatures
exoplanets.
of
How is the infrared really
water
important for your
methane
study?
and carbon dioxide, those types of molecules in their atmospheres.
We
Want to study their atmospheres. And as a reminder, exoplanets are planets that orbit distant stars. So We're looking for very small signals when we study their atmospheres. And WEBB is this giant telescope that we're able to use to collect these small signals and look for infrared signatures, chemical signatures of water and methane and carbon dioxide, those types of molecules in their atmospheres. And why the infrared? You know, that's really because those signatures are the strongest in the infrared. We know that they exist there, and so that's why we want to use WEBB to look there.
It seems an amazing idea. So exoplanets, planets around other stars, are light years away from us, tremendously distant. So how do we know if it's water, methane? I mean, how can we probe an atmosphere so far away?
Well, with WEBB, there's a couple different ways, but one of the main ways is actually using the transit technique. And this is an indirect method where we actually detect the decrease in starlight that happens as a planet goes in front of its star. But then imagine the planet has an atmosphere. Well, there's an additional decrease in the starlight because the atmosphere blocks some light from our point of view. And why it blocks the light is because there's usually a molecule or something in there, like water and methane, like I mentioned, that is acting as an absorber and blocking the light from our telescope, in this case, WEBB.
So going from, you know, the relatively nearby stars and planets, Macarena, you're an expert on very distant things, distant galaxies. So how does infrared contribute to your field of study?
So with WEBB, we're going to be able to observe the very first galaxies and stars. We're talking about 3.5 billion years ago, so it's really mind-blowing if you think about it. And why infrared? Well, those galaxies emitted their visible light many, many millions of years ago, and that light travels towards us in time, and at the same time, the universe expands. So in that process of travel and expansion, the light shifted from the visible to the infrared, and so WEBB will be able to actually observe those very original primeval galaxies. And not only those, but it will also allow us to observe everything in between so we can understand the evolution of our galaxies from the first ones to the ones we see today.
This is something kind of amazing. So our eyes interpret different energies of light as different colors. Exactly. And infrared light is a color that our eyes are not sensitive to. But like you said, it's actually just the space of the universe stretching out the light and changing it from visible light into infrared.
Into infrared, exactly.
So how are these first galaxies different from galaxies today?
Well, when you look at the images we have of the oldest galaxies we've seen, they look like fluffier and clumpier. We know they have a lot of star formation, so they are actually, that's a really good signature to measure them. And they are like little seeds that afterwards they merged and got together and evolved until the ones we see today, which are like spirals and elliptical galaxies.
So from, you know, the near universe to the far, one of the things that infrared is very good is seeing through dust. That's another huge advantage. Maybe Nicole, could you sort of take us through that story?
Sure. You know, with dust, there's a lot of dust in the universe, but how stars and planets form in the first place, they are forming in these very dense clouds of gas and dust that come together, and it's very difficult to see through them with normal visible light. And so the infrared is actually able to see through that, almost like an X-ray, you know, sees your bones, sees through our skin. You can use the telescope like WEBB to see through the dust and see the inner stars forming, or see some newly formed planets that are also very warm from having just formed.
And there's even a possibility of seeing some of the very first stars, or at least some evidence of the first stars that might have existed. But could you tell us a little bit about that, Macarena?
Yeah, so the very first stars, they form right around the time of the very first galaxies, even before that. And so we'll be able to measure them, maybe not the very first one, but the first population of stars, which is really interesting because they were formed out of a very pristine material. And then from there, they evolved into more evolved stars that created all the elements we know today, things like gold, platinum, carbon, everything. Us were formed out of those original stars. So it's a really amazing adventure to observe all these objects and understand them better.
You know, there's so many wonders in the universe, and one of the things that I would never have believed was real unless I'd seen it, the data with my own eyes, is the TRAPPIST-1 system. And that this is actually going to be one of the targets for WEBB, is that right? Tell us a little bit about TRAPPIST.
Sure. TRAPPIST-1 is, like you said, it's going to be a target. There's 7 planets in the system, and they're all small, around the size of Earth, actually. So it's also a very compact system. So it's not just that there's a lot of planets and that WEBB is going to observe every single one of them, but it's the compact nature that's just really fascinating, because the entire orbit of the planetary systems, like all 7 planets, they fit inside our orbit of Mercury around the sun, and Mercury is our closest planet to the sun. So imagine 7 planets in there, and you know, there's a lot going on, but it's very exciting because we'll get to learn and do comparative science and see, are all these planets, do they have the same chemical signatures in their atmosphere? You know, do they all have same amount of water, carbon dioxide, things like that?
Well, thank you so much. We're going to be back to talk to you more, but thank you for joining me.
Thank you.
Thank you. Okay. So we'll be back in some more minutes to talk with them. And remember that we're taking your questions, so use the hashtag AskNASA. WEBB looks like nothing that's come before because it's pursuing scientific goals like none that have come before. It's taken years to prepare it for flight, and as you might imagine, plans of this scope and scale inevitably run into unexpected challenges. Along the way, just like any of us, it encountered things like snowstorms in the east, wildfires in California, hurricanes that deluged Houston, Texas, and of course, the global COVID-19 pandemic, which added its own profound challenges to the whole team. This story really warrants a recap, so check this out.
The Webb Space Telescope presented many engineering challenges, but engineering hasn't been the only obstacle the team had to overcome. In 2011, an outbreak of tornadoes cut electricity to the Marshall Space Flight Center in Alabama for nearly a week, while the team rushed to finish cryogenic testing on the primary mirror segments using power from diesel generators. Engineers had to endure a large snowstorm, known locally as Snowmageddon, while testing the Integrated Science Instrument Module at the Goddard Space Flight Center. And of course, everyone has had to contend with the global pandemic. One particularly memorable challenge was working through Hurricane Harvey in 2017. This massive cyclone dumped 40 to 60 inches of rain across the Houston area over a 4-day period, causing catastrophic flooding and $125 billion of damage, all while the telescope was undergoing cryogenic testing at NASA's Johnson Space Center. Though the telescope remained safe inside the test chamber, water leaked through the ceilings, people had to cover workstations in plastic tarps, food was in short supply, and a few team members trapped by floodwaters had to be rescued by boat. It was rough, to say the least, but the team and the telescope survived the storm. Despite winds and snow and endless rain, the team got it done, and Webb is now ready for its final journey atop a rocket into space.
While the Webb telescope is a technological marvel, everything here began with questions. Questions about how the first stars and galaxies came to be. Questions about whether planets around other stars might have environments that can sustain life. And of course, the promise of discoveries we can't even predict yet. A few days ago, I had a chance to speak with someone who's probably the best person on Earth to help us understand what we know, what we don't know, and how Webb will help fill in those gaps. Dr. John Mather is a Nobel Prize winner who measured the Big Bang with an observatory built here at NASA Goddard. John is Webb's senior project scientist, and we're so pleased to have you here today, John.
Good to be here with you, Michelle.
So to start this incredible story of Webb, let's start with something that's deceptively simple, gravity. There's something special about gravity.
Gravity is special. Gravity always pulls. It's the only force of nature that always pulls. So that's special. And what makes that special is that gravity, although it's very weak, is very long range. It can reach across the universe and slow down the expansion of the material that came from the Big Bang, turn it around, pull it back together, turn it into galaxies and stars, and eventually planets and a place we could live. So that's what makes gravity special among all the forces of nature.
And something so simple, like just the idea that it's always pulling together, that simplicity leads to wonderful complexity, doesn't it?
Yes, because it's always pulling, it's possible for gravitational energy to be converted into kinetic energy, that's just heat, and the universe becomes self-heating, which is not something the other forces could do all by themselves. Clouds of gas can be compressed by the gravity until they get big enough and hot enough to light up and have the nuclear reactions inside that turn hydrogen and helium into the chemical elements you see around you, here in the house, here on the set. So carbon, oxygen, nitrogen, everything we have that we think of as ordinary came from inside stars. So we are stardust, as Carl Sagan told us, but there wasn't any stardust in the Big Bang. So we need this part of the story to be figured out. How did we come to be able to live here on our little planet when the universe started out without all of these goody things?
So you mentioned these planets around other stars. So we're almost sort of going through all these amazing science goals of the Webb. What can Webb tell us about planets around other stars?
Well, once in a while, a planet goes in front of the star, and some of the starlight goes through the atmosphere of the planet, if it has an atmosphere, on its way to the telescope. We will spread out that light into a spectrum, or what you would call a rainbow, and we will analyze it to see what are the chemicals that are in that atmosphere. So we will be able to tell you, maybe, that's the plan, whether those little planets that might be like Earth actually could have, for instance, water in their atmosphere, and maybe enough water so there could be a liquid ocean under that atmosphere. One of the great questions. So we know they're planets. We know when we should look. We just don't know what we're going to see.
So after the Webb launches, one of my dreams is I'm going to be standing outside in my backyard and point to a star and say there's a planet around that star that we know has water vapor, oxygen, perhaps methane, carbon dioxide. So what is Webb going to also do in the search for life closer to home, our own backyard?
Well, here in our own solar system, we will be looking at everything from Mars on outwards to the farthest we can see. Satellites, comets, asteroids, and the planets themselves. And some of them are really interesting and special because we know they're possible homes of life. What would make a thing a home of life? Well, if it's wet. That's the good clue. So the satellite Europa, which orbits around Jupiter, was discovered by Galileo himself. And we know now that it has an ocean that's covered with ice. There are cracks in the ice where water comes spitting out. NASA are going to send a probe over there to fly through those plumes. We're also going to point over there with the Webb telescope to see what can see about that atmosphere and those plumes of water. We'll be looking at Titan, which is a satellite of Saturn, which is so big that it has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface, is solid ice, and over that are liquid hydrocarbons, which you would use for fuel here in our home. But over there, it's liquid rain, lakes and rivers, and we will be looking at the geology of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system, but this has also been a personal journey for you. You've been working on Webb since the very beginning of the mission, is that correct?
I have. Since '95, we had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities, and we learned that we would need an infrared telescope that could do things that the Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
And thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies form. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. You know, what about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light in the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at. And that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself. Because there's several instruments on board. There's 4 different instruments, and there's some moving parts, and so you need things to be cool because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
Now, Macarena, you are the instrument calibration scientist for the coolest instrument.
It is the coolest
on
instrument,
WEBB,
yes.
MIRI. So tell us a bit about MIRI and why it needs to be so cold.
So MIRI, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. And so MIRI is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit redder, a bit cooler than the near-infrared light, and so because of that, MIRI needs to be colder in order to detect that very faint signal from high-resolution galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling, and it brings it down to about minus 450 Fahrenheit. So it's really extremely cold, a few degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's a lot of other molecules, but basically in the infrared, at the wavelengths that we want to observe some of these stars and planets and galaxies, those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even at higher mountains where they try to get above the clouds or atmosphere sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space.
Absolutely. So we talked a bit about some of the power of techniques like spectroscopy. We've heard Dr. John Mather talk about it. So let's go a little bit more into the details of how spectroscopy works and why it's so powerful. Continue.
Oh, sure. Yeah, I can keep going. Well, with spectroscopy, we heard so visible light again is kind of it's a rainbow of colors that we don't see naturally. But if you use something like a prism, you can separate out that light and see all the colors from blue to red. But then the infrared is redder than the human eyes can see. But you can still do the same technique where you have spectroscopy tools or instruments like WEBB has, all these spectroscopic tools, so that we can break up the infrared light and look at certain colors, if you will, so that we can see certain features that we are looking for, whether it's the right wavelength where a galaxy might be bright or where water is absorbing in an atmosphere.
So Macarena, MIRI has many different capabilities.
It does.
And in fact, it has one that I believe is something different called coronography as well.
Yes.
Tell us a bit about all these ways that we're going to detect different signatures from planets. Tell us about MIRI.
Coronography, it's an amazing technique, but essentially it simulates an eclipse. So when we have a very bright star with planets around, for instance, usually when you take an image, the stars outshines the light of the planet, so you don't see them. But with MIRI and with other instruments, NIRCam as well, you can actually block the light of the star and dim it, and then you see the planets around. And it's really a technique that's going to be very much used and to do, like in this image, direct imaging of planets.
Well, thank you so much. We'll be back to talk to you more with some social media questions. Thank you very much.
Thank you.
NASA and its partners began developing the Webb telescope years ago, growing from an initial inspiration to a design, then schematics, and finally reality. What started as a big dream for studying the origins of the universe required best-in-class engineering expertise to transform into something real. Let's take a short look at the very long story about the earliest days of the James Webb Space Telescope.
Before the Hubble Space Telescope even launched, scientists were already discussing what should come next. Ideas for what was then called the Next Generation Space Telescope evolved throughout the 1990s, and by the end of the decade, NASA had a preliminary plan. Construction of the James Webb Space Telescope began in 2004. Beryllium was mined to create the mirror segments, which technicians polished and coated in a thin layer of gold. Meanwhile, engineers designed and built new science instruments in the US, Europe, and Canada. Every step of the way, there were reviews and tests to make sure each part could withstand the rigors of spaceflight. By the early 2010s, the team began bringing individual components together at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It was there that the mirrors and instruments began to coalesce into the grand machine we see today.
We've said before that the James Webb Space Telescope is an incredibly ambitious mission. Big ambitions come with big challenges, and that's certainly been the story of Webb. From the beginning, the design of this observatory has been a balance between the boldest questions scientists have dared to ask and the cutting-edge technology that our best engineers could offer. The design for Webb evolved from earlier ideas of what a telescope could be, another example of the delicate balance between desire versus capability. To get a better understanding not only of the mission's goals, but also the mechanical guts of the observatory itself, I recently got a chance to speak with a pair of engineers who know the anatomy of the Webb telescope better than just about anyone. I'm here with Keith Parrish, a senior engineer on the Webb mission. And Keith, you brought something to show us today.
Yeah, yes I did. So conceptually, Webb Sunshield is actually quite simple. All we need is 5 tennis court size pieces of this material outstretched to protect the telescope from the sun. So what I have here is an actual sample of that material. This is just Kapton.
It's so light, yeah.
Yeah, it's an industrial, you can buy this and it's commonly used. And what we do is we buy it for Webb, we seam it all together in small pieces, and then we actually coat it with special coatings to give it the what we call the thermal properties we need in orbit. So this one has a nice pink or purplish kind of hue to it, and the reason it's purplish in hue, we use this on the sun side, and we actually put a silicon material on this Kapton, and then we actually put a little bit of a metal in it, and what that metal does is it gives us a nice electrical conductivity. We don't want any surface charging building up, and the other thing is this silicon coating actually drops the temperature of this layer. So, and also it's very durable and can survive, for many, many years in space.
And then this whole thing has to unfold somehow, where we can actually see that behind us.
Exactly right. So if you look at that animation there, unfolding there, so it's actually S-folded up, almost like a fan. We call it S-folding. And once we get it all folded up, we secure it to a structure by actually pinning it for launch. So, a huge shout out to our mechanical engineer and our entire Sunshield team, because they've come up with some really clever ways to secure this for launch, unfold it, fold it, and then, ultimately get it safely deployed in orbit.
That's wonderful. So speaking of unfolding and all these pins that need to release, let's go over here and talk to James Cooper. You're going to show us what's going on there.
Yeah, hi. So I have here an example of a non-explosive actuator. We have 178 of these.
These are all these little pins we're talking about, right?
James Webb, right? Yeah. 107 of the 178 are the membrane release devices. And we use this type of actuator because it produces a very low shock when it's released. And the animation shows conceptually how it works. We send an electrical signal through either one of our connectors. We use both, but either one of them can cause the release to happen. It melts a small wire inside, and then we have a spring that unwinds and allows 2 halves of a split nut to separate, and then our pin can get extracted. And so in the case of the MRDs, it's a spring-loaded pin that pulls to release the folded membranes. In other places, we would be bolting 2 pieces of structure together and then releasing them so we can deploy them.
And the Sunshield itself has 107 of these?
107 MRDs that all have to work.
Every single one has to work.
Every single one has to work. And 178 of this type of device in various configurations around the entire observatory.
Right. Well, if we go over here, we've got something sort of lovely waiting for us, a big gold hexagon. So to tell us what we're looking at, a sort of a model here of a mirror segment, right?
Right, a full-scale single segment, one of the 18 mirror segments on James Webb. The real ones would be machined out of a single piece of beryllium to the exact curvature we need. And then once we're deployed on orbit, each segment can be individually focused to make it act as a single perfect mirror.
Now that coating, tell us about this gold coating here.
Yeah, so this is coated with a very thin layer of gold. It's only a few hundred atoms thick of gold, and that gold is really good because it gives us a reflective property in the infrared, and that's really what Webb is an infrared telescope, and we need that Sunshield exists to cool this entire telescope. So this mirror actually runs about minus 400 degrees Fahrenheit on orbit. If it were warmer than that, the infrared energy coming off of this, that heat energy would swamp our detector system and our instruments. So that entire Sunshield exists to cool all 18 of these down. And again, this gold coating is what helps with all that reflectivity to make it perform even better.
Well, that's wonderful. So now you put it all together, and we have a smaller mock-up here, the sun shield, the mirror. Tell us what we're looking at here.
Much smaller. So yeah, this is our entire observatory fully deployed on orbit. And you can see the sun shield here is a large feature. You can see all 5 layers that I talked about earlier. And it's the separation of those 5 layers which lets heat energy escape out to space before it eventually gets to this cold layer. Again, that entire telescope is running minus 400 degrees Fahrenheit, and the way we get it that cold is this side is shaded. The telescope is looking to the deep universe, which is near absolute zero. And then again, this layer here, we've got about a 500 degree temperature drop, so this telescope is also looking at this layer here, which is nice and cold. So that's what lets us, harness thermal physics to cool this down to those really, really cold temperatures. Again, you can see our booms, which are fully deployed and stretching this out, and then ultimately all folds up and gets stowed into this structure for launch.
Right, so the membrane release devices would be along the back side of these structures on the forward and the aft side. And we release them in rows so that we can sequentially start to unfold the membrane once those pins are pulled out of the way.
Well, that's wonderful. Thank you so much for joining us, and best of luck on the launch. I'm very excited.
Yeah, thank you.
Okay, let's get a live launch status update from NASA commentator Rob Navius at the launch site. Rob, how are things in Kourou?
Well, thank you, Michelle, and Merry Christmas from the Jupiter Control Center here in Kourou, French Guiana. You are looking live at an Ariane 5 rocket on its launch pad, ready to send the James Webb Space Telescope on the initial phase of its journey. The fueling of the Ariane 5's first and upper stages began before sunrise, and in the last few minutes, mission controllers here in Kourou and at the telescope's control center at the Space Telescope Science Institute in Baltimore conducted polls, with all positions reporting they are go to proceed into the final phase of the countdown. Launch controllers have been monitoring weather conditions throughout the night, keeping tabs on clouds and wind speeds, both at ground level and in the flight path of the Ariane 5, ensuring that all of the precise commit criteria are acceptable for launch. Right now, we have a green board, no issues as the countdown proceeds, no issues again being tracked by the flight control team here in Kourou. By the way, our broadcast today is a collaborative effort between NASA and the European Space Agency. So that's it from now. From the Ariane 5 Mission Control here in Kourou, we'll be back with you soon. For now, let's go back to the Goddard Space Flight Center and Michelle Thaler.
Thank you very much, Rob. So WEBB asks big science questions. It demonstrates astounding technology. It inspires and excites people to dream and wonder. And the spark of inspiration is the ignition of creativity. Kids all over the world have a natural affinity for WEBB's big pursuits. And now we have a collection of young artists ready to showcase their work.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb telescope will find.
I believe that the Webb's telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space. Hello, my name is Gabriel. I am from Romania. This is how I imagine space. Hello everyone, good morning. This is a drawing of distant galaxy that can be seen by James Webb Space Telescope. Hi, my name is Anastasia, and this is what I think the telescope will look like. what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
So we've been fielding social media questions from viewers all over the world this morning, and let's take a couple of minutes to share some responses. There's been a couple questions about how long will it take for images to come out, and there's a lot of things that need to happen before the images are coming. So Macarena, why don't you take us through some of that?
Yes, so for the first scientific beautiful images to share with the public, that will take 6 months. And the reason is because so we launched today. It takes a month to take to the orbit place, to the Lagrange 2 point, and then we have a whole period of cooling down the instruments, aligning the mirrors, and making sure that all the instruments are ready to do science. So the whole process takes 6 months, half a year.
And also all of those 18 segments of mirrors, something needs to happen to get them all working together too, right?
Exactly, because initially you launch with 18 segments and they work separately. So you will take, if you observe one star, you will get 18 little points. So there has to be a process where you take images with NIRCam, which is one of the cameras on board, start moving the mirrors slightly to make them work as a single one, and then by the end of this iterative process, you go from 18 points to a very sharp, pristine single point source. So all mirrors act as a single one.
So let's see, we have a question from LV coming in on Twitter. Will WEBB be able to enhance detection of comets, asteroids, or meteors that enter our solar system? So that seems we've got a planetary person here.
Sure. Yeah, well, WEBB does have a special observing mode where it's able to track these rapidly moving objects, because compared to these distant stars and galaxies, asteroids and comets, they move pretty quickly. And so WEBB will be able to do this so that we can study material that's outgassing from them and learn more about what they're made of.
So let's see, there's so many good questions, so we only have time for a few more. So one is from Kristen Rodriguez on Facebook. How long will it take James Webb to reach Lagrange point 2? And you might also just explain, what is Lagrange point 2?
So it takes a month. I think it's actually 29 days to get there. And the Lagrange 2 point is this very interesting stable point. So the gravitational pull between the sun and the Earth create this point where it is stable, and you can, as we can see there, Webb can orbit around the L2 point in a very stable orbit, only needs a little bit of corrections once in a while, and it can always have the sun shield protecting the telescope from the radiation of the sun. In a full year, you can observe any object in the sky, and it's a continuous observation.
Well, thank you very much. We'll hopefully come back to a few more questions later.
Thank you.
So this is a big mission with a cast of thousands to bring it to life all over the world. As we get closer to launch, let's take a brief look at the main locations where WEBB took shape on its journey to space.
Inside the massive high bay clean room at NASA's Goddard Space Flight Center, engineers assembled the 18 gold-covered mirror segments into the backplane of the telescope and integrated the 4 science instruments contributed by international partners. To simulate the harsh environment of launch, they went through vibration tests and acoustic tests. And to simulate a space environment, the instruments endured cryogenic testing in a large thermal vacuum chamber. But it wasn't large enough to hold both the instruments and the mirrors, so the telescope boarded a plane to Houston, Texas, to visit the only thermal vacuum chamber in the world big enough to fit the entire assembly. Chamber A at the Johnson Space Center was originally built to test the Apollo spacecraft, and half a century later, it provided a grueling 100-day test for the Webb telescope. Next, the telescope traveled to Northrop Grumman's facilities in Redondo Beach, California to meet up with its other half, the Sunshield and spacecraft bus. Fully assembled at last, the entire observatory went through yet more tests, many focused on making sure the spacecraft could properly fold up for launch and unfold in space. Then in September 2021, Webb caught a ride on a specialized cargo ship and set out on a 16-day voyage to the European Space Agency's spaceport in Kourou, French Guiana. According to its travel itinerary, that's Webb's last port of call on Earth.
Once Webb gets into space, we're going to have some exciting things to tell you about what happens next, from its extraordinary engineering to the thrilling scientific adventure it's about to enable us to undertake. But launch comes first. And for that, I'm going to turn it over to Katie Haswell, our host at the launch site, and one of NASA's most recognizable voices, launch commentator Rob Navis. It's all yours, Katie.
Thanks very much indeed, Michelle. Well, it's all looking very good here at the spaceport for a Christmas Day launch. Operations running smoothly, the countdown ticking over nicely. All the systems are green and we are go for launch. You can see there we're looking at launch pad number 3, the James Webb Space Telescope, inside the very top of the rocket in first class with its seatbelt on, waiting patiently for liftoff. That's scheduled in about 32 minutes' time. I'm in the Mission Control Center here at the spaceport, the nerve center of operations. We're about 10 kilometers from that pad, and behind me you can see it's a laser focus here in the control center with the mission control centers all on console there as we get closer to launch. We call this the fishbowl behind this protected glass. And up in their skybox here in Mission Control are NASA's Rob Navius and the European Space Agency's Luce Fabregat, and they're standing by to take over the commentary about 15 minutes as we get closer to launch. First of all, though, let's check in on the countdown and let's see how things are progressing with Stefan Israel. Stefan is the CEO of Arianespace. Arianespace is the company responsible for getting our telescope into space today. Stefan, thanks for joining us. No pressure.
Good morning, Katie.
How are things looking?
So we are now 31 minutes before liftoff. So far, so good. Ariane 5 is ready. Webb is ready, the range is ready, and the weather is green.
Well, that's good to hear. So what can we expect to see? What's going to happen?
Yes, so in the 30 coming minutes, we will make the final operations. 10 minutes before liftoff, we will have the final authorization of the weather. And 7 minutes before liftoff, we will enter in the famous synchronized sequence.
And, I mean, how's everyone feeling? I'm guessing everyone's...
We launched for humanity this morning from the Guyana Space Center. You know what Webb is about. After Webb, we will never see the skies in quite the same way.
It's an important project, isn't it, for everybody?
It's a very special mission, but we have delivered already 111 times with Ariane. This is the 112th Ariane 5, so we will deliver this morning.
And everybody there in the control center, cool, calm, and collected. Stefan, thank you very much for having taken time to step out of the fishbowl for us. So you can head back now into the fishbowl and take up your position. Stefan Israel, thank you very much indeed. Stefan, of course, heads up what we call the flight desk, which is the authority that takes all the final decisions in the event of unplanned situations. Now, we are in French Guiana. We're on the northeastern coast of South America. We're in Amazonia. It's hot. It can get a little bit sweaty sometimes, and there are lots and lots of mosquitoes. But somebody who knows it very, very well is Raphael Chevrier. Raphael is a rocket scientist, or a rocket expert at least, from Arianespace. Thanks for joining us, Raphael. Tell us a little bit more about French Guiana.
Well, French Guiana is a French territory that borders Brazil. It's located in the Amazon rainforest. 97% of the land is covered in trees, so that's why it's so green and beautiful. And you can totally imagine that the wildlife there is absolutely incredible. This is actually one of the best preserved habitats in the world.
And of course, it is in the jungle, and yet it is actually the European spaceport. So what makes this location in South America so important and so relevant?
Well, there are several reasons for this. First, we are on the coast. It means that we can launch over the sea from north to east without having to fly over inhabited area. So this is very convenient to reach any kind of orbit. There is no hurricane here, big tropical storm, there is no earthquake, but more importantly, we are very close to the equator, so that we can benefit from what we call the slingshot effect given by the rotation of the Earth. So let me take this globe. Basically, here on the equator, we are all traveling at roughly 1,000 miles per hour. That's very convenient. Of course, we don't feel it. If we were on the poles, that speed would be very, very close to zero. It means that when Webb is right now on the launch pad, inside the fairing of the Ariane 5, it's already traveling in the right direction, and we can use this extra boost to get us into space. That's also very convenient for Webb, because doing so, it can save its fuel and increase its operational life in orbit at 1.5 million kilometers from here.
And that really is important, 1 million miles, isn't it? And so there's a real proper slingshot effect. Yeah. And the facilities here are ultra high-tech, and that's exactly what WEBB needs, isn't it?
Yeah, that's very convenient for WEBB. It's also located in a nature reserve. So this is the perfect meeting between nature and technology, and people come from all over the world to work here. But one thing that's been very important for WEBB is cleanliness, because you know that one speck of dust could alter the vision of the observatory in space. That's why we have been extremely careful in keeping a pristine environment in all our facilities, from WEBB's arrival in French Guiana to sealing it inside the rocket.
So let's talk a little bit now about the Webb Space Telescope. I really don't think you need me to tell you that it is the product of a feat of human ingenuity. And you don't get to make a telescope as complex as the James Webb Telescope and as remarkable without tremendous amount of collaboration. And the James Webb Space Telescope is indeed the product of a partnership between 3 space agencies who came together to create it. NASA, the European Space Agency, and also the Canadian Space Agency. So here to talk about that now is Greg Robinson from NASA. Greg, thank you very much for coming to the floor, out of the fishbowl as well for us. And we're talking serious teamwork here, aren't we?
Yes, Katie. We've benefited from an amazing partnership with the Canadian Space Agency and the European Space Agency. Over the life of the development, we've had more than 10,000 people actually touch WEBB, 29 states in the U.S. and 14 countries across the globe, and not to mention the amazing industrial base across the globe that have benefited here. In order to do bold missions like this, it takes lots of resources and lots of expertise, so we maximize everyone's expertise.
And how did this bold mission get onto an Ariane 5 European launcher?
So as part of the partnership, the Canadian Space Agency contributed science instruments, and they're incredibly important for this mission. And so did ESA, science instruments, and the amazing Ariane 5 that we will see take us on this journey and put us in the right direction to get to Lagrange Point 2, and we're looking forward to that.
It's a tremendous atmosphere here, isn't it, in the Mission Control Center? There's a real buzz here today. I wonder how you must be feeling, Greg. I mean, it's got to be a very, very emotional time knowing that your telescope is sitting there on top of the rocket, getting closer to launch.
It's certainly amazing. Often talk about the butterflies, and people keep asking me, have they started? Have they started? And yes, they're starting. And when we get to about 20 minutes out, they will start flying a lot. So the excitement is just amazing.
The excitement is building, and of course everyone very cool, calm and collected. Thank you, Greg Robinson. You can take your position back in the fishbowl now, because I know you've got a lot of work to do in there. Greg Robinson, thank you very much indeed for joining us. So the Ariane 5 launch vehicle is the heaviest lifter in the Ariane 5 family. I mean, the rocket is also, and Raphael, she has got an incredible track record, collaboration either, do you?
Yeah, this is a very reliable, successful rocket. 12 different countries have been participating in the development of Ariane 5 to be launched, with Ariane Group now being the very first Ariane, the Ariane 1
took off exactly 42 years ago. Why don't you talk us through it? The rocket is made of sections, and we often call those stages, which is what you might hear. Hopefully we're going to get a good Christmas present today as well.
So first you have the two boosters, solid boosters that are located on each side of the rocket.
Like this without collaboration either, do you?
Thrust, of course, just like literally push the rocket. In fact, 12 against the gravity of the Earth. Have been participating in these big tanks that form the with Ariane Group now being the industrial prime, with the main engine working at the bottom.
Right next to you, Raphael. Why don't you talk us through it? The rocket is made of sections, and we often call those stages, which is what you might hear during the commentary.
Exactly. So first you have the two boosters, solid boosters that are located on each side of the rocket. Is going to place will provide the main thrust in order to literally push the rocket against the gravity of the Earth. We first see then you have the main these big tanks that form the main cryogenic stage. We do this because we want the main engine working properly at the bottom. Before we switch on the solid boosters,
right at the top,
7 seconds
inside
later.
the fairing.
It is right there on the launch pad, and together they are put the rocket is going the third stage, a cryogenic stage, and it is this upper stage that is going to place Webb don't be surprised if you don't see the rocket lifting up for 7 seconds. That's the time for the rocket first see actually warm the main before soaring into the sky. Ignite
so once we light the touch paper, you can count to 7 before it actually lifts off. Now, one of the advantages of the Ariane 5 vehicle is that it can be modified, and that's exactly what we've done for today's launch. We've had to make some changes for it to be able to host the Webb satellite. And joining me to talk about that is somebody who, the right person for the job indeed, because he was in charge of those changes, Daniel Deschambre from the European Space Agency. Thanks for joining us, Daniel. So what did you like the touch paper? You can count to 7 before it actually lifts off. Now, one of the advantages of the Ariane 5 vehicle is that it can be modified, and that's exactly what we've done for today's launch. We've had to make some changes for it to be able to host the Webb satellite. And joining me to talk about that is somebody who, the right person for the job indeed, because he was in charge of those changes, Daniel Deschambre from the European Space Agency. Thanks for joining us, Daniel. What did you have to do?
Of the launcher, first we need to recall in order to balance as much as possible to be the inside and the outside pressure of the fairing. And this fully occupies the volume of the fairing due to with gaps as small as 10 centimeters for diameter 5 shock, which could damage the delicate layers to develop a specific web integration procedure to ensure that there is no contact with them. After separation, due to the fact that during separation, some equipment of Web are very sensitive to sun exposure of the launcher has been improved in order to balance control as much as possible will be the inside and the outside make sure that Web is always oriented and this is one face to the sun. Due to in addition to avoid any hotspot, depressurization shock, the launcher which could damage the delicate layers will create some oscillating movements like a barbecue separation to avoid any overheating. And due to the fact that after web separation, some equipment of Web are very sensitive to sun exposure, to be applied control on the launcher in order to put it on the liberation in order to make sure that Web is always oriented in order to avoid only one collision in the long term. And
thank you very much indeed, Daniel. So we'll hopefully see the upper stage rocking in space, not quite all the way around like the familiar barbecue, but a slightly different movement. Listen, gentlemen, thank you very much indeed for being with us today. I know that you're busy, you've got jobs to do inside the fishbowl, so I'm going to send you right back there now, and very best wishes for the launch. Thank you.
On the upper stage, in order to put it on a liberation
has
orbit
a long
around the
journey
sun,
ahead of it. It's
in order
got
to
to
avoid
travel a
collision
million
in the long
miles.
term.
Thank you very much indeed, Daniel. So we'll hopefully see the upper stage rocking telling us in space, not quite all the way around like the familiar barbecue, but a slightly different movement. Because it's travelled. Thank you very much indeed for being with us today. I know that you're busy. You've got jobs to do inside the fishbowl, so I'm going to send you right back there now. And very best wishes for the launch. Thank you. Into a special container. Our telescope has transported a long journey ahead of it. It's got to travel a million which had to be closed because it's so big. Destination in space, its working zone, where it's going to start telling us all about our universe. And it's already started. It travelled on that journey, special ship, because it's travelled to spacecraft from Los Angeles. Come to the French Guiana after final tests were concluded in Los Angeles. Webb was too big for that, so it had to travel by ship, and it went through the special container and transported along the LA 405 freeway, which had to be closed because it's so big. Up through the locks. It travelled on a special ship. 16 days. A lot to get to the port. Spacecraft will come to the French Guiana, where it was unloaded by plane. But Webb was too big and travelled so it had to travel by ship, and it went through the Panama Canal. 5, that's a model. Just outside the Jupiter Control Center, actually. It was unpacked very carefully the locks in the facilities that Raphael was talking about. And then fueling started, and of course, And it took 16 days. The teams had to wear special suits to get to the port, a dangerous job. In Kourou. And then it was placed where it was unloaded on top of the Ariane 5 rocket. That's not the real Ariane 5, that's a model. Just outside the Jupiter Control Center, actually. It was unpacked very carefully in the facilities that Raphael was talking about. And then fueling started, and of course it was encapsulated inside the teams had to wear special suits because and sealed a dangerous job. And then it was rolled out to the launch pad 2 days ago of the Ariane 5 rocket. From the vehicle assembly building to the pad along very special rails. Very, very slowly through the Amazon rainforest. It was raining at the time. And that was 2 days ago, and here we are now. It was encapsulated inside the fairing minutes and sealed. 46 seconds to launch and counting. Then it was all systems are go to the launch pad 2 days ago at the European Spaceport in French Guiana. We have from the vehicle control centers on the pad today. We have very special rails. The mission control center here. We also have the launch control center, which is about through the Amazon rainforest. And then we also have the telescope control center, mission control. And that was 2 days ago. Baltimore, here we are now. And that's where the operational teams are standing by 46 seconds to over the telescope counting. Operations. All systems are go. Once it's released from the mothership, that will be in about 27 minutes. We have three control centers on the job today. They'll be controlling the mission control center here for the rest of its life. The launch control center, which is about a mile from the pad. And then we also have the telescope control center, mission control in Baltimore in the US. The James where the operational teams are standing by to take over the telescope operations. People have been working once it's released from the mothership. That will be over 2 decades. About 27 minutes after launch. Some people have been working on it for their whole professional lives. And they'll be controlling Thomas Zabrucken telescope is the head of rest of its life at NASA. Very important job. He's joining me now just to talk about it. Thomas, or Dr. Z, as we can also call you. The James Webb Space Telescope. The day has come. A truly all these decades, remarkable, all this time, all these people working on the telescope, and here we are for 16 minutes and counting over to launch. 2 decades. Some people have been working on it for their whole professional lives. Right? We have this Thomas Zabrucken is the head of science at NASA.
10,000 plus people have worked on in many ways. Talk about it. Together with that telescope, all the hopes and dreams of those individuals, and also tens of thousands of scientists, some of them not even born, that will benefit from these data, are there with them waiting for these last minutes of countdown for its journey to space.
16 minutes and counting to launch. A combination of emotional excitement.
Oh, I'm so amazed.
What's going through people's minds, do you think?
Oh, I think there's a tremendous sense of accomplishment. Whenever you're on top of a rocket, 10,000 plus people really well. There's tremendous pride. Together with that telescope, all the hopes and dreams of those individuals, and also we have tens of thousands of scientists, some of them not even working on this right now, so that will benefit from these data. We're super excited with them waiting for these last minutes of countdown for its journey to space.
I guess people are feeling a combination of emotional
I'm a scientist,
excitement.
so for me, besides the technology that really is a marvel, I think there's a tremendous sense of accomplishment. Whenever you're on top of a rocket, many things went really well. There's tremendous pride. We have never seen the universe how Webb will show it to us. And can you just imagine going back in time, 13.5 billion years working on this right now, so I'm confident that we're super excited. Just think about all the new things we're going to learn about our most beautiful universe.
What are you most excited about, Dr. Z? Dr. Z, thank you very much for joining us. And I want to wish you and all the team, everybody, the very best for today's launch. Thank you.
The best we can do. What I'm thinking about is really looking at the universe in new light. We have never seen the universe how Webb will show it to us. And can you just imagine going back in time, 13.5 billion years, it boggles your mind even as a professional astrophysicist.
Hand you over now
just think about all the new things we're going to learn about our most beautiful universe.
Alongside Dr. Z, thank you very much for joining us. And I want to wish you and all the teams, everybody, from here on in. Over to you guys for today's launch. Thank you.
Well, thank you, Katie. Merry Christmas to our worldwide audience from our broadcast booth high atop the Jupiter Control Center here in Peru.
Really close now.
Joining me today for this historic launch, my colleague Luce Fabregat, the head of infrastructure and value chain for the European Space Agency. Luce, good morning. It's great to be with you. Great to be with you today.
The European Space Agency's Luce Fabregat, who are going to take on the commentary from here on in. Over to you guys. Rob.
Well, at this hour, countdown clocks are ticking backward. We are at T-minus 13 minutes, 32 seconds, and counting atop the Jupiter Control Center. Everything is in great shape. Don't let those clouds fool you. For this historic launch. My colleague, the latest weather briefing, head of infrastructure and value chain for the European Space Agency. Luce, good morning. We have a green board here in the control center today, and everything has gone extremely smoothly in the countdown. About 9 minutes ago, a major milestone passed. Our countdown clocks are ticking backward. We are at began the process 13 minutes, completed the 32 seconds of receiving commands to transition from external power to internal battery power. Clouds fool you. Following the latest in the series of those weather briefings. The latest weather briefing WEBB just will remain on internal battery power all weather parameters singular solar array unfurls about 30 minutes in the control center. Launch. And everything has gone extremely smoothly in the environmental readings. About 9 minutes ago, inside the major milestone encapsulating the telescope atop the upper stage began the process and completed the process of receiving commands to transition phase of the countdown power to internal battery some of the upcoming critical activities as we head into the phase called synchronized will remain on internal battery power until its singular solar array unfurls about 30 minutes after launch. Earlier, telescope controllers reported good environmental readings from sensors inside the fairing encapsulating the telescope atop the upper stage of the Ariane 5 rocket. And Luce, as we enter the most critical phase of the countdown, can you outline some of the upcoming critical activities as we head into the phase called synchronized sequence?
Yes, Rob. We are now reaching the end of this. They are on hold now, waiting for the last that we call the chronology, and that started yesterday evening. After this weather report have been prepared for final launch operations. We will have the beginning of this famous synchronized sequence. It's rather quiet now, will be made ready for the liftoff and also inside the launcher. This sequence will told a few minutes ago by the launch ground calculator here, and then the launcher fleets and computer systems are ready for the final automated sequence. The launch vehicle they are on hold now, autonomous, waiting for the last weather report at minus 10 minutes. You know that we have two tanks in each weather report stage. 3 minutes later, main stage, we will have the beginning of this famous synchronized sequence. Of course, all systems will be made ready for the environment where we have here in French Guiana. This sequence will first be read by the ground calculator, propellants are at very low temperature, and because of that, will slightly evaporate step by step. And to ensure the vehicle they will be made autonomous liftoff from the ground system, final loading and topping up. We know that we have 2 tanks in each before the launch stage, so that will be the beginning of the synchronized stage sequence run by the ground calculators. All 4 tanks are, of course, we will have thermally insulated from the hot environment where we have here in French Guiana. The final loading and the topping up liquid propellants are at very low temperature, and because of that, the electric side evaporate. We will have the onboard computer getting prepared for the launch also, loaded and liftoff, and the final loading and topping up will last up to 4 minutes before the launch. So that will be the beginning of the synchronized, which is today sequence run by the beginning of the windows, 9:20. Then we will have 7:20 Eastern time. The end of the topping up, the final loading and the topping up.
And Luce, so we're coming up on that final weather report. We expect all systems to remain green. We'll be going down to the fishbowl to confirm that just a moment or two from now. It's a 27-minute ride to orbit from liftoff until the time that the WEBB observatory is separated from the upper stage of the Ariane 5 rocket. Several minutes later, the commands will be given to to unfurl its solar array, followed by the confirmation
And Luce, we're
from
coming
the
up
telescope
on
controllers in weather report that we are power positive,
to remain
that
green,
electrical current
will
is
be
flowing
going down to the
through that
fishbowl
solar
to confirm
array.
that just a moment
With
or
us
two
today,
from now.
inside the so-called fishbowl,
It's a
27-minute
mission
ride
controllers
to
on
orbit
the floor
from
of the control room
liftoff is
until
Raphael
the time
Chevrier
that
of
the
Ariane Space
WEBB
Raphael,
observatory
how's everything
is
looking? What's
separated
being
from the upper
discussed down
stage
there?
of the Ariane 5
Hi,
rocket.
Rob. Well,
Several
so far,
minutes
so
later,
good.
the
We
commands
just
will be
received the
given
last,
to unfurl
weather
its solar
forecast.
array,
It's
followed
all
by the
green
confirmation
for the
from the
AGO
telescope
that is,
controllers
forecast
in
right now.
Baltimore
What we checked
that we are
was
power positive,
altitude
meaning
winds,
that
wind
electrical
in the
current
vicinity
is
of the
flowing
launch pad
through that
and
solar
risk of
array.
lightning. So
With us
right
today,
now,
inside the
it's
so-called
a relief
fishbowl,
because the
seated with
weather was
mission
a bit
controllers on the
tough
floor of the
in
control
last
room
couple of days,
is
but
Raphael
right now
Chevrier of
everybody
Ariane
is very
Space.
focused
Raphael,
on
how's
the
everything
next
looking?
steps.
What's being discussed
the
down
start
there?
of the synchronized
Hi,
sequence
Rob.
at
Well,
7
so
minutes
far, so
before
good. We just
received the last operations that was described earlier before the AGO that is in the Ariane forecast right now. What we checked was into the altitude winds, wind in the vicinity of the
Thanks,
launch
Raphael.
pad,
We'll be back with
risk
you
of
and Luce
lightning.
here
So
shortly.
right now,
We now have
it's a
confirmation
relief
from
because
Baltimore
the
that
weather
James
was
Webb
a
is
bit
on
tough
internal
in
power.
the last couple of
Amidst
days,
all of this
right now
activity, we
everybody is
cannot
very
forget
focused
that it is
on
Christmas
the
Day.
next steps.
53
The
years
start
ago,
of
the
the
astronauts
synchronized
of Apollo
sequence
8
at 7
completed their
minutes
10th and
before
final
liftoff.
orbit of the moon
Last operations
after reading
that
from
was
the book of
described
Genesis
earlier
on Christmas
before
Eve
Webb
to
and
billions
Ariane
of
5
people
are
watching
going
with
to
rapt
lift
attention
off
back
and
on our
soar
planet.
into the sky.
The astronauts then headed for home.
Thanks,
Following
Raphael.
their
We'll be back with you and Luce here
trans-Earth
shortly.
injection burn.
We now have
Today,
confirmation
more
from
than a half
Baltimore
century
that James
later,
Webb is on
we're just
internal
minutes away
power.
from another Genesis.
Amidst all of this activity, we cannot forget that it is Christmas Day. 53 years ago, the astronauts of Apollo 8 is at hand. Completed their 10th and final orbit of the moon
seconds away
after
from
reading
entering
the book of critical synchronized
Christmas
sequence.
Eve.
You're going to be
Billions of
hearing
people watching with rapt
all the
attention
critical
back on our
calls
planet.
from the
The
DDO, the range
astronauts then headed
operations
for
manager,
home, following their
who is
spacecraft's
Jean-Luc
trans-Earth
Voyer here in
injection
the
burn.
launch in the
Today,
mission
more than
control
a
center.
half
There
century
he
later,
is.
we're just
will
minutes
be
away
calling
from
the start
another
of synchronized
Genesis,
sequence,
the
all
Genesis
of the critical
of
countdown
new
milestones
of discovery.
and we
The
will
launch
be
of the James
listening
Webb
very
Space
intently
Telescope
for his calls.
is at hand.
Let's stand by.
We're just 38 seconds away from entering the critical synchronized sequence. You're going to be hearing all the critical calls from the DDO, the Range Operations Manager, who is Jean-Luc Voyer. And with that, Here
we've
in
entered
the
launch period in the mission control center.
sequence.
There he is.
You heard
he
Luce
will be
Fabregat
calling the
just a
start
moment
of
or two
synchronized
ago,
sequence. All of the critical countdown
some of the critical
milestones
activities,
and
the first
we will
one
be
coming up just a
listening
few
very
seconds from
intently
now,
for his
which will be
calls.
the
Let's
topping
stand
off
by.
of the main stage tanks. The first core stage was loaded earlier this morning with 175 tons of propellant, 150 tons of liquid oxygen, and 25 tons of liquid hydrogen. The synchronized stage loaded with 15 tons of propellant. That will be the workhorse for a 16-minute burn until the critical activities to its first one coming up just a few seconds from now, which will be the topping off and 7 seconds of the main stage tanks. James Webb will be at an altitude of about 864 earlier this morning with 175 tons of propellant, 150 miles higher than the Hubble Space Telescope, and more than 600 miles higher than the International Space Station. 15 tons of propellant that will be the workhorse about 21,000 miles an hour burn to lift James Webb to a highly elliptical halo-like racetrack orbit, some 1 million miles from Earth. 7 seconds to begin launch, its scientific James Webb will be at an altitude of about 864 statute miles. To put that into perspective, some 520 miles higher than the Hubble Space Telescope and more than 600 miles higher than the International Space Station. Webb at that point will be traveling about 21,000 miles an hour as it heads out to a highly elliptical halo-like racetrack orbit some 1 million miles from Earth to begin its scientific observations.
1 minute and 5 seconds before the launch. And we are going to see minus 6 seconds. 1 minute from now, we will see minus 6 seconds. The pressurized upper stage, this level, for the last technique arms you can see on this ignition of the Vulcan engine. Then, and in 3 seconds before the H0 are also set in flight configuration, the onboard computer, about the electrical power as the launcher will be released. It will switch from ground to internal power 1 minute 7 before the launch, 1 minute and 5 seconds before the launch of the main start. And we are going to see minus 6 seconds that will take. 7 seconds, less than we will see the disconnection of the engine will start up to its flight technique arms you can see on this picture. Once the computer has checked that the Vulcan engine is running normally, 3 seconds before the H0, the flame inertial platform that will give all the information about where it is to the launcher will be released. The onboard computer will ignite the 2 boosters that will enable to move the 770 engine of the main Ariane stage will start.
Coming up on the T-minus 4 minute mark right now, just a couple of milestones real quick. At the 1 minute 5 second mark into the flight, Ariane 5 will go through the period of maximum dynamic pressure. Max Q as it's known. That will be the period of maximum aerodynamic forces on the rocket itself. The solid rocket boosters, which will provide about 90% of the initial thrust off the launch pad, will shut down and separate at the 2 minute 21 second mark right now, followed a just a couple of milestones real quick. Fairing jettison, 1 minute 5 second James Webb Space Telescope. Ariane 5 will go through the period of maximum dynamic for the first time. The main stage separation or the first stage separation comes at the T-minus aerodynamic forces 8 minute 47 second mark into the flight. The solid rocket boosters, which will provide about 90% of the initial thrust off the launch pad, will shut down 24 minutes, 51 seconds into the flight, and then we'll go into a coast phase of about 2.5 minutes to allow any oscillations that will dampen out the James Webb Space Telescope environment for the James Webb Telescope for the first time. The main stage separation or the first stage separation comes at the T-minus 2 minute 50 second mark into the flight. Again, you're going to be hearing critical calls down the stretch here from the DDO stage engine. Range operations manager Jean-Luc at about 24 minutes 51 seconds into the flight, and then we'll go into a coast phase. The weather is 2.5 minutes to allow any oscillations to dampen out, provide the most pristine environment including for the James Webb Telescope, carefully watching the telemetry, looking intently. We're coming up on the couple of minutes of the countdown live mark into the flight. In the again, you're going to be hearing critical calls down the stretch here from the DDO or the Range Operations Manager, Jean-Luc Voyer.
On the left of the screen from Ariane Space.
The weather is go. We have a green board, and that is the DDO, the Range Operations Manager, NASA officials, including Greg Robinson, on the right, carefully watching the telemetry, looking intently at the final couple of minutes of the countdown. Lives have been spent in the preparation of the James Webb Space Telescope that is about to fly.
The flight will be in 2 phases. You will see the first part of the flight during the solid rocket boosters phase from Ariane Space. That will be the atmospheric part of the flight, the atmospheric flight.
And that is the DDO, the Range Operations Manager, Jean-Luc Voyer, as we have hit the 2 minute mark in the countdown.
We will have a very different exo-atmospheric flight after that.
And you were watching a number of people, VIPs and invited guests, moving out to the observation platform that is right next to the Jupiter Control Center as we stand by for the 1 minute call from Jean-Luc Voyer.
That will be the atmospheric part of the flight, the atmospheric flight, and the trajectory will be driven by a very to reduce the aerodynamic loads, and we will have a very different exo-atmospheric flight
after that. Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 50 seconds VIPs and invited guests moving out to the observation platform. The Vulcan 2 engine will ignite to the Jupiter Control Center. Come up to flight speed as we stand by for the 1 minute command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way. T-minus 30 seconds and counting. Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 50 seconds and counting. As you heard earlier, by for terminal, the Vulcan 2 engine will ignite. Turbo pumps will come up to flight speed for 7 seconds, and the command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way.
6, 5, 4, 3, 2, unité.
T-minus 30 seconds and counting. And we have engine start. And liftoff, standing by for terminal count. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
9, 8, 7,
Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Top.
And we have engine start.
Trajectoire est nominale.
Vehicle performance is nominal. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. To fly uphill in nominal fashion. Punching a hole through the clouds, 20 seconds into the flight. Of the powerful Ariane 5 now being felt here in the control center. 3D animation.
Trajectoire est nominale.
We can hear the noise and feel the vibrations.
Vehicle performance is nominal.
Yeah. Impressive.
13 kilometers in altitude, 7 kilometers downrange. Ariane 5 rocket continues to fly kilometers in nominal fashion.
Tous les paramètres à bord sont normaux.
The rumble trajectory reported to be nominal by Jean-Luc Voyer, the range operations manager. 3D animation. You can see at the bottom of your screen, the yellow line is the trajectory plot, perfectly overlaid over the green line, which was the pre-launch trajectory. 13 kilometers in altitude, 7 kilometers downrange into the flight, about 40 seconds away from shutdown of the solid rocket boosters. 0.6 kilometers per second.
Tous les paramètres à bord sont normaux.
The trajectory coming up on the 2-minute mark into the Voyer, the range operations manager. You can see at the bottom of your screen, the yellow line is the trajectory plot, perfectly overlaid over the green line, which was the pre-launch trajectory. 1 minute, 41 seconds into the flight, about 40 seconds away from 2 minutes, 15 seconds into the flight.
When the computer detects this threshold, it will separate.
Coming up on the 2-minute mark into the flight, we have confirmation of solid rocket booster separation from Jean-Luc Voyer. This coming at an altitude of 44 miles. The Ariane 5 and James Webb traveling almost 5,000 miles an hour.
Less acceleration.
Tous les paramètres à bord sont
We have
normaux.
about 1 minute 5 seconds to go before fairing jettison. That'll be the next critical milestone. 15 seconds into the flight.
When the computer detects this there to avoid the satellite being exposed to high temperatures and also high airflows.
We have confirmation of solid rocket booster separation from Jean-Luc Voyer. It's coming at an altitude of 44 miles. The Ariane 5 and James Webb traveling almost 5,000 miles an hour.
So each kilogram being very
We have about
important for
1
the
minute
performance
5
of the launch,
seconds to go
we are
before
going to
fairing
eject
jettison.
this
That'll be the
no
next
more useful
critical
fairing.
milestone. And let's
The
go down
fairing
to
is
the
there to
floor
avoid the
in the
satellite
Jupiter
being
Control
exposed
Center
to
to
high
Raphael
temperatures
Chevrier of Ariane
and also
Space.
high
Raphael, so far
airflows.
so good.
And as soon as the
Hi, Rob.
launcher
So far so good.
leaves
Everything
the
is
atmosphere,
nominal,
as is now the case,
we say when
the
attitude
satellite
and
does not need
trajectory
anymore
of the
to be
Ariane 5
protected
is
and
going perfectly
Webb
well.
does not
As you
need
can see
anymore to
also
be
on
Paramètres à bord
the
sont normaux.
yellow line.
Bagage de la
So
coiffe.
each
On the
kilogram
screen, we
being
have the
very
confirmation
important
of
for the performance of the launch,
separation of the two
we are
flight
going to
boosters
eject
and now
this
of
no more
the fairing,
useful
meaning that
fairing.
we have crossed the limits of the atmosphere. So
And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of Ariane Space. Raphael, so far so good.
So let's continue the mission. Everything is nominal.
And Raphael, this is a view from the upper stage camera called the Vicky Cam, looking back at the James Webb Space Telescope. This is on about a 20-second delay or so because of the way the imagery is processed here in the control room. There's your telescope ready to unfurl its wings, basically, and begin its journey to the Lagrange point, the L2 point, about 1 million miles away from Earth.
Continue the mission.
And Raphael, this is a view from the upper stage camera. Trajectory is nominal. The report from the James Webb Space Telescope. This is on about a 20-second delay or so because of the way the imagery is processed here in the control room. There's the liftoff time confirmed here on the Mission Control Center at 12:20 Greenwich Mean Time and begin 9:20 a.m. journey to Peru time, the Lagrange 7:20 a.m. Eastern time, about 1 million miles away from Earth. The Ariane 5 and James Webb, 181 kilometers in altitude. Trajectory is nominal. The report from Jean-Luc Voyer downrange from the launch site here in Kourou.
Flight control is very smooth.
The liftoff time confirmed here in the Mission Control Center at 12:20 Greenwich Mean Time. 9:20 a.m. 3.5 minutes to go. 7:20 a.m. Main stage or first stage performance. And again, you can see at the bottom of your screen the yellow 181 overlaid over the green altitude, meaning we are right on course, 50 kilometers downrange from the launch site so far for the Ariane 5 rocket.
Flight control is very smooth. All telemetry data
5 minutes, 12 seconds into the flight.
Galileo tracking station.
We have about 3.5 minutes to go in main stage or first stage performance. And again, you can see at the bottom of your screen the yellow plot line overlaid over the green line, meaning we are right on course, right down the pike, and a perfect trajectory so far for the Ariane 5 rocket.
In the middle of the ocean, and the two last stations in Africa, Libreville and Malindi, one on the east by the Galileo tracking station, which is close to here, where we are in Kourou. It will track the launcher up to the ignition of its upper stage. And then we'll have the Natal station in Brazil, Ascension as you can see on the map, in the middle of the ocean, and the two last stations in Africa, Libreville and Malindi, one on the east.
Will be processed through the Deep Space Network in Goldstone, California. We passed the 7-minute mark into the flight. A perfect ride so far on the Ariane 5. We have about 1.5 minutes to go in the first stage performance. Once the main stage engine is commanded to cut off, it will be jettisoned. And just a few seconds after that, the upper stage engine will ignite, and it will be the workhorse for a 16-minute burn space that will put James Webb into California. We passed the 7-minute mark into the flight. A perfect ride so far on the Ariane 5. We have about 1.5 minutes to go in the first stage performance. Once the main stage engine is commanded to cut off, the Space Telescope Science Institute, and just a few seconds after that, the upper stage engine will the initial series of commissioning activities for a 16-minute burn to the deployment of the James Webb into the initiation of generation of electrical power for the telescope. About 30 seconds away from main engine cutoff. About 11 minutes from now, telescope controllers at the Space Telescope Science Institute will be sending commands to prepare James Webb watchword for the initial series of range operations manager, Jean-Luc Voyer, to the deployment of his stand by main engine shutdown and separation of generation of electrical power for the telescope. About 30 seconds away from main engine cutoff.
Extinction de l'EPC. La trajectoire est normale. Préparation
Nominal
EPC.
trajectory continues to be the watchword shutdown and separation from the range operations manager, Jean-Luc Voyer, of that upper stage as we stand by for main engine shutdown in the fishbowl. So far, so good.
Yes, Rob, we have the confirmation of the separation of the main stage and the ignition of the upper stage. The trajectory is perfectly nominal.
Extinction de
This is
l'EPC.
a very important moment for us because it's always a challenge to switch on a cryogenic engine in space condition, and we are now
We have main stage shutdown and separation confirmed here in the Mission Control Center, and the ignition of that upper stage. And Raphael Chevrier down in the fishbowl.
The second stage of
so far, so
the second
good.
phase of the flight. We have the confirmation the upper stage is going to power main stage and the ignition for about 16 minutes to place Webb on its 20 nominal. And right now, very important moment for us because it's always a challenge to switch on a cryogenic engine.
And a short time from now, the so-called sawtooth maneuver will get underway. Again, like rocking a baby in a cradle, this will be a maneuver to keep Webb's optics protected from overheating
the second phase of the flight. The upper stage is going to power for about 16 minutes to place
with a very specific configuration. Of course, it will be different during its lifetime, but for the time being, it's sun-shielded.
And a short time from now, the so-called sawtooth maneuver will get underway. Again, like rocking a baby in a cradle, this will be a maneuver to keep Webb's optics protected from overheating loose.
Thermal conditioning inside the telescope. You can see the way the rays of the sun would propagate and interact with a very specific configuration. Of course, it will be different during its lifetime. Maintain the time being, thermal conditioning is really key for separating this and this telescope. And in particular, we know that one face of the telescope cannot face a number of testing studies have been performed by the this right thermal conditions in Europe and the US on specific thermal conditioning inside the telescope, what we call the sawtooth approach. And if you propagate carefully to this image with sensitive equipment, this animation inside the telescope, the upper stage is going this 30 degrees on one side is really key. That 30 degrees on the other side this telescope. And this way, we know that one face to maintain the telescope cannot face thermal conditioning for the telescope. And to produce this right thermal conditions inside the Webb, a specific roll law has been designed, what we call the sawtooth approach. And if you are watching carefully to these images, you can see this animation. You can see that the upper stage is going 30 degrees on one side, then 30 degrees on the other side, going back and forth this way to maintain this perfect thermal conditioning for the telescope.
It's worthwhile noting that after Webb separates from the upper stage of the Ariane 5 rocket, which continues to perform in excellent fashion at coming up on the 12-minute mark into the flight, the telescope controllers will be taking the baton, if you will, from the mission controllers here in Kourou. The first steps will be the opening of fuel valves, a pair of fuel valves, to start flowing fuel to Webb's onboard thrusters. They then will power on the valve drive electronics. Those are powered on in preparation to control and fire those thrusters when required. Webb's solar array is scheduled to be deployed at approximately the 33-minute mark into the flight. Once it is locked in place, we'll get the call that electricity is flowing through the array. That call will come from the Mission Operations Manager, Carl Starr, who is at the Space Telescope Science Institute at Johns Hopkins in Baltimore. Seated right behind him in that control room is Alicia Starr, a pair of stars helping to guide James Webb on its discovery of the stars. Alicia Starr is the lead engineer for launch and ascent events. Once the solar array is deployed and declared power positive, then 3 out of the 4 hold downs for the aft deployed radiator will be released to prevent binding due to the cool down of the telescope's composite structure. The contamination control heaters will be enabled to protect instrument optics on Webb from any water ice condensation as they cool down. The actuator drive unit will be powered on. This particular mechanism helps with heater control of the fine steering mirror, preventing water ice condensation, later to be used to position each of the mirror's segments. All 6 reaction wheels and the wheel drive electronics will be powered on for Webb, and that will be the precursor to the attitude control system using those reaction wheels to maintain the proper orientation with the sun, as opposed to using onboard thrusters. Of course, fuel in those thrusters, very valuable. It's a limited commodity for the lifetime of James Webb's observations of the universe. We're 13 minutes, 55 seconds into the flight. Jean-Luc Voyer, the Range Operations Manager, continues to report a nominal performance for James Webb. And again, Luce Fabregat from the European Space Agency, how is this trajectory being carefully and methodically adjusted to provide the correct parameters in the final stages of ascent?
Yes, Rob, as you can see on this plot, the altitude is slightly going down. It's perfectly normal. The launch vehicle is really on the line where it should be. This decrease of its altitude, slight decrease of its altitude, will allow the launcher to benefit and the upper stage to benefit of the gravity effect and to increase its velocity until it reaches a thermal threshold. It's about to reach it, or even already reached it now, and it will go up. And now it will go up and up to the separation of the Webb telescope. It will separate the Webb telescope on a highly elliptic orbit, but still around the Earth. The telescope will be released, inserted on an orbit around the Earth, with an apogee, a very high apogee above 1 million kilometers.
Trajectory nominal as reported by Jean-Luc Voyer. You see him in that view, 185 kilometers in altitude, some 4,500 kilometers downrange from the launch site here in Kourou, moving at more than 8 kilometers per second, right on the plot, right on the trajectory, everything looking great. We are about 9 minutes away from the completion of upper stage ignition. It's shut down, and then about a 2.5-minute coast phase before Webb will separate. Observatory separation will be called out. You'll be hearing those calls and the initial calls from Carl Starr, the mission operations manager at the Space Telescope Science Institute at Johns Hopkins, through solar array deploy and the declaration of a power-positive spacecraft. James Webb, of course, will be traveling well beyond the moon to a distance of about 1 million miles away from Earth, settling into a highly elliptical, halo-like orbit to begin its astronomical observations. And again, as we mentioned earlier, at the time of observatory separation, Webb will be at an altitude of approximately 864 miles, statute miles, traveling some 21,000 miles an hour. We're about 8 minutes away from upper stage shutdown. The stage has performed as planned. No issues reported. The launch occurring at 12:20 Greenwich Mean Time, 9:20 Kourou time, 7:20 a.m. Eastern Time on this Christmas Day.
Very smooth launch. The velocity you just mentioned is very important, Rob. The velocity you just mentioned at separation of the telescope is very important. It will be slightly below, okay, I give it in a kilometer per second, but it will be slightly below 10 kilometers per second, because it's important that the satellite, the telescope, is not inserted on an escape orbit. It will be placed on a terrestrial orbit so that there will be time for the layup, for the early phase operations and the commissioning of the telescope. And that will be, in fact, the upper stage that will leave this orbit and goes toward an escape liberation orbit.
And of course, even though we're still in powered flight, the trajectory, the acceleration, the speed at which James Webb is going towards its preliminary orbit, all modeled in advance and carefully choreographed to maintain as quiescent an atmosphere and environment around the telescope for its ultimate separation from the upper stage of the Ariane 5 rocket, which is about 6.5 minutes from now. .5 minutes into the flight. It's very quiet now here in the control center here in Kourou. NASA officials, European Space Agency officials, Arianespace officials, all watching telemetry very carefully. And as the upper stage continues to burn nominally and sheds fuel, the acceleration uphill for the James Webb Space Telescope continues to increase as we approach the 20-minute mark into the flight. Again, upper stage cutoff is scheduled at the 24-minute, 51-second mark into the flight, about 5.5 minutes from now.
After the cutoff of this main engine, as you said, Rob, we will have a short ballistic phase, a short coasting phase that will, when the upper stage will rely fully on its what we call the attitude and roll control system, and it will adjust its attitude so that during this small ballistic phase, all the requirements from the telescope are fully met, and that at the separation, when there will be the separation, the conditions will be very smooth and as requested for the telescope.
Le pilotage est calme, la propulsion est nominale.
Today's countdown was as flawless as you can imagine. The weather was perfect all the way through the early morning hours, through the fueling process of the vehicle. The weather's been a bit dicey here in Kourou over the past few days, but everything fell together on this Christmas day to send a new present to the world's astronomer. 20 minutes, 40 seconds into the flight.
Trajectoire est normale, tous les paramètres à bord sont normaux.
All parameters nominal as reported by Jean-Luc Voyer, the range operations manager. 4 minutes of powered flight remaining.
The telemetry of the launch vehicle is acquired for the time being by the Libreville tracking station on the western coast of Africa. Flight control is nominal. The trajectory is fully normal, fully as expected, as you can see on the plot with the yellow plot over the green one. That is the expected one.
The range operations manager has been calling out the milestones throughout the flight today. And the ESA teams responsible for so much fabulous work, great teamwork here to get the WEBB telescope into space, and WEBB is now heading out on its journey, on its own, with the mission controllers, the telescope mission controllers in Baltimore, following those incredibly important first actions and first operations. Charlotte Bezko there, who's responsible for the ESA operations here at the spaceport. We're hanging in there, waiting and hoping to hear from the NASA administrator, Bill Nelson, who I have absolutely no doubt will be as jubilant as everybody here at the Guiana Space Center. Charlotte Bezko,
at 13:04, we are expecting Wendy,
who has been working for, I think, most of her professional life in human spaceflight, and now heading up the ESA operations here at the European Spaceport. Over to you, Bill Nelson.
Okay, Katie, thank you very much. This is a great day. not only for America, for our European and Canadian partners, but it's a great day for planet Earth. Thanks to the team. You all have just been incredible. And over 3 decades, you've produced this telescope that is now going to take us back in time. It's a time machine. It's going to take us back to the very beginnings of the universe. We are going to discover incredible things that we never imagined. And isn't that typical of this team, where the impossible comes possible? I can't thank you enough on behalf of a grateful United States government. I can't thank our partners in Europe and Canada enough. The French launch team, the Arianespace, the flawless perfection of the vehicle. And now we have to realize there are still innumerable things that have to work, and they have to work perfectly, 344 of them. But we know that in great reward, there is great risk. And that's what this business is all about. And that's why we dare to explore. The James Webb Space Telescope is very much a part of that exploration. It's significant that we had the delays, and it kept us all the way to today, Christmas Day, when others long ago peered up into the sky and saw stars. But it's also another millennia before that a shepherd grazing his sheep would look up at the night sky. He became a poet, and he penned the words, "The heavens declare the glory of God, the firmament shows his handiwork." That shepherd, that poet, became king. And those immortal words in Psalm 19 encapsulate the expressions that we have today. The handiwork of God as we peer back in time over 13 billion years ago, capture the light from the very beginning of the creation. My congratulations to the team. My congratulations to NASA, to our partners. Go James Webb Space Telescope. God bless you, and God bless planet Earth. Back to you, Katie.
Bill Nelson, thank you very much for those incredibly moving words. Indeed, we're heading out to look at the first light of the universe. And Bill Nelson there, we have Stefan Israel with us from Arianespace. Bill Nelson there being so complimentary about the partnerships, the teamwork, and thanks as well to you guys for this fantastic launch. What a day, Stefan.
Indeed, what a Christmas gift today from the Guyana Space Center. We really want to thank NASA for its trust, the administrator, Bill Nelson. We have with us Thomas Zurbuchen and all his team, and our first thoughts are going to NASA. It is a journey of 20 years we have made together. We have worked as hell, I would say, to make this happen, and now it's done. I want to thank as well ESA, who is formerly our contractor for this launch. We have Joseph Aschbacher with us, we have Daniel Neuenschwender. We have worked hand by hand to make it happen. I want to thank CNES, Ariane 5 Design Authority, and our daily partner here in the Guyana Space Center. Philippe Baptiste is with us, Marianne Claire is with us. Thank you very much to CNES. For sure, I want to pay my tribute to Ariane Group, which is the prime contractor of Ariane 5, main shareholder of Ariane Space, and which has delivered the launcher up to liftoff. And doing so, I pay also my tribute to Ariane Space team. The Ariane Space team have worked all this year to make this 14th launch of the year and this very special mission. Your dedication, your professionalism has made the success of tonight. Tonight is a great step for the space journey. It is also a great step for the friendship between the United States of America, Europe and France. So thank you very much to all of us. And now I think we can take a little bit of a rest, but we are going now to leave with WEBB up to its final destination, to the Lagrangian point. Thank you very much. Thanks a lot.
Thank you very much, Stefan. And the Director General of the European Space Agency is Joseph Aschbacher. Joseph.
So Merry Christmas to everyone, and we have delivered a Christmas gift today to humanity, to people, to NASA, but also to all the people in this world, because with this James Webb Space Telescope, we are really enabling new science, new excitement, but also really rewarding all the engineering and all the effort that has gone into it, and I'm really grateful for this success. We have delivered a mission into space. It's power positive, everything is nominal, and I'm very grateful to Arianespace and all our partners for all this work. Stefan Israel has already thanked all our partners, but let me also just very briefly recall that this was really a team effort. It was a team effort of the European team. We call it Team Europe, the European Space Agency, obviously providing the launcher with Arianespace, with CNES, with Ariane Group, with all our partners which we have to make this possible. And I really would like to spend a minute to thank all the people involved in this. Today is Christmas. Some of them are here, have been spent weeks here in French Guiana or at the sites where they have been working. It's a special moment. I know I have made sacrifices, but it's a special moment, and really thank you from my heart. But also thank you, NASA. Bill Nelson was speaking before. Thomas Zurbuchen is here with his team. Fantastic cooperation, and this cooperation between NASA and European team is really exemplary. And a big, big thank you, Thomas and your people, for what you have done together with us, that you have entrusted this precious spacecraft to us, which we could deliver. And I'm so happy today, I can tell you, this is a very special moment. It's very nerve-wracking. I couldn't do launches every single day. This would not be good for my life expectancy, but I can tell you this was very exciting, very nerve-wracking, but really, really very successful. And thank you from my side. And congratulations, NASA. Congratulations, science community. Big science is to come, and really, really happy. Thank you from my side.
Thank you very much. So the president of the CNES, which is the French space agency, is Philippe Baptiste, and he joins us now. Philippe.
Thank you very much. Well, as everybody here in the room, I'm very, very happy to see that everything was fine, everything is nominal. It's great news for NASA, for ESA, for all of us. I just want to thank all the people who have been working over the last 20 years on this incredible instrument, on this telescope, but also people who have been working on the launch. I'm thinking especially on the 500 people who have been working yesterday during Christmas Eve to prepare the launch, to prepare this successful launch. And I really want to thank them very much. People from CNES, from ESA, from NASA, from Arianespace, and from all the partners who are around. I also want to give a special thank to the French Armed Force of Guyana who made this launch possible. They were monitoring everything, and without them, nothing would be possible here on this site. So thank you very much for all of them, and thanks also to all people from Guyana who are supporting this incredible European spaceport that we have here today. Thank you very much.
Thank you, Philippe. So we now have a pre-recorded message from Lisa Campbell, who is the president of the Canadian Space Agency.
I am so proud to witness the highly anticipated launch of this extraordinary mission. Je suis très heureuse et fière de m'adresser à vous aujourd'hui. It's a remarkable feat of international collaboration to think of all the scientific and engineering coordination that made today's events possible. In fact, WEBB is the result of close to 25 years of planning and development with our international partners. Notre participation au télescope WEBB est l'aboutissement de plus de 25 ans de planification et développement avec nos partenaires internationaux. We're playing a big role on the world stage. Canadian excellence has helped make this flagship telescope a reality. Our participation in WEBB is extremely significant. It's the largest space science project in the 60-year history of our space program. WEBB est effectivement le plus grand projet de sciences spatiales dans lequel nous avons été impliqués depuis le début de notre programme spatial. The successful launch of this groundbreaking telescope bolsters humanity's quest for knowledge of the cosmos and ignites interest in astronomy for a new generation. The Canadian Space Agency is proud to have contributed critical instruments to this large-scale partnership as part of a global effort to spur the next great scientific leap. We're thrilled to take part in a mission of such enormous scientific promise. Nous sommes ravis de faire partie de cette mission extraordinaire. Canadian astronomers are excited to use WEBB's data and benefit from the tremendous science opportunities offered by this one-of-a-kind observatory. We congratulate the fantastic team of over 10,000 people who put all their skills, ingenuity, and effort into developing the telescope for more than 2 decades. Bon voyage, WEBB! Canadians will follow your journey with great interest.
And now I'd like to hand you over to Thomas de Brucken, who is the head of science at NASA. Thomas.
Well, Katie, what an emotional day, what an emotional time. We're here, all of us who have been working together for so many weeks, months, and years, and more importantly, our teams who are taking team images behind us, who have put in front of their lives as a highest priority for so many of them to actually get this done and get it done here, working even during the holiday times. I just couldn't be more grateful to the many, whether it's Arianespace, CNES, the European Space Agency, all the amazing people around French Guiana, the forces that are here, all the good people that have been such great hosts to our teams. All of them I want to thank. You know, whenever we look at launches, they're both an ending and a beginning. They're an ending of an engineering project on the ground. And with many amazing hours and challenges that are there, but they're a beginning. They're a beginning of one of the most amazing missions that humanity has conceived. And I'm so excited to look forward to the next setup of this telescope and all the science to come. Thanks to everybody. This is what we can do when we come together, Katie, as one, humans. It's just absolutely incredible. Thank you.
It's wonderful. And Dr. Z, thank you very much. Massive congratulations to you all, to everybody who's involved in today. Huge congratulations from everybody here at the Guiana Space Center, and also our very best wishes to all the teams in Baltimore who are now monitoring those early operations of the telescope as it starts to unfold. I'm going to hand you back now to Goddard, but before I do, I just want to say from all of us here at the Guiana Space Center, Merry Christmas. Over to you, Michelle.
Thank you, Katie. I can tell you that here it feels like the dawn of a new age. Historians of the future will divide our understanding of the cosmos into eras before WEBB and after WEBB. WEBB is this milestone that marks a bold effort to look backwards in time to the mysterious origins of everything. Of course, we move at human time scales, so here's what's coming up. In the next few weeks, engineers will unfold WEBB's critical sun shield to begin chilling the telescope to unimaginably cold temperatures. They'll extend the DTA, the Deployable Tower Assembly, the structure that supports the Great Golden Mirror. And then finally, they'll unfold that mirror and begin the process of fine-tuning the system for work. Through it all, we intend to bring you live coverage of all of the important events that are happening, along with expert commentary and extraordinary images from the Mission Operations Center and our own broadcast headquarters here at WEBB's home, the NASA Goddard Space Flight Center. Stay with us over the next few weeks because the adventure is just getting started. Speaking for everyone on the team, it's been a great pleasure to be with you here today. I'm Michelle Thaler, and you've been watching special live coverage of the historic launch of the James Webb Space Telescope. Thank you for joining us.
Hello everybody, good morning and welcome to our NASA briefing on NASA's James Webb Space Telescope, the world's largest and most powerful space telescope ever built. Webb will explore every phase of cosmic history, from within our own solar system to the most distant observable galaxies in the early universe, and everything in between. Webb will reveal new and unexpected discoveries and help humanity understand the origins of the universe and our place in it. We're lucky to be here today with our NASA experts to hear how this mission will have the most complicated series of deployments of any NASA mission ever. Our panelists today will tell us how this telescope will unfold out in space. We'll have time for questions after their updates. This briefing is remote with participants at NASA and at our launch site in French Guiana. This will live stream on NASA TV, the NASA app, and the agency's website. With us from the team, we have Bill Oakes, Webb's project manager from NASA's Goddard Space Flight Center, Mike Menzel, Webb lead mission systems engineer from Goddard, and live from the launch site in Kourou, we have Begonia Villa, Webb instrument systems engineer, Alfonso Stewart, Webb deployment systems lead, and Crystal Puga, Webb spacecraft systems engineer from Northrop Grumman in Kourou. Let's kick it off with Bill.
Good morning. This is an exciting time for JWST. Over the past year, we have accomplished many major achievements leading up to the road to launch. During that past year, we've completed our observatory level environmental testing, the final deployment of JWST. We stowed JWST into its current launch configuration. We completed the final full-up observatory electrical test, the final test between the spacecraft and the Mission Operations Center located at the Space Telescope Science Institute in Baltimore, Maryland, shipped the observatory to the launch site, and most recently we completed our final major mission rehearsal. To accomplish all these tasks, it is taking a team of over 10,000 people, 20 plus years to achieve this, to get to this point. This has included our friends from the Canadian Space Agency, as well as those from the European Space Agency and their contributions to the program that have spanned 14 countries and 29 U.S. states. We've overcome various technical challenges and issues, as well as challenges that have been thrown at us by Mother Nature, including tornadoes, lightning strikes, a blizzard, Hurricane Harvey, and then the most recent challenge, and probably the most difficult one, and that is completing observatory INT in a COVID pandemic environment. We arrived at the launch site with the observatory by ship on October 5th. In addition to the observatory, we sent 38 trailers ranging in size from 20 feet to 40 feet, containing our ground support equipment down to French Guiana. Since arriving there, we have unpackaged JWST. We completed all of our post-ship inspections, our post-arrival electrical test, and we are currently in the process of loading or prepping the spacecraft for loading propellant. What we have left down at the launch site includes the actual fueling of JWST, integrating JWST to the rocket, completing our final closeouts in inspections and testing, integrating the fairing, and rolling out to the pad, and then launch on December 18th. Once we get past launch, we have a 180-day period of on-orbit commissioning, consisting of a spacecraft phase where we have launch and ascent. We do a mid-course correction maneuver to get us on the proper trajectory to get out to L2. And then what you're going to hear about today are deployments. Once those are completed, we will kind of move into the mirror phase of the program, where we will deploy the mirrors. We align those mirrors to create the perfect image. At the same time, we'll initiate some of our science instrument activities, as well as finish our cooling down to our operating temperature below 50 degrees Kelvin. From launch plus 118 days to launch plus 180 days, we will commission our 4 science instruments. As I mentioned today, this panel will discuss deployments as well as some aspects of the science that JBST will do. And for that, I will turn it over to Begonia down at the launch site.
Thank you, Bill. I'm here in Kourou outside the viewing window in the clean room on the Space Center, where JamesWebb has been in its deployment configuration since its arrival. And here is where all the inspections, electrical testing, and mechanical activities to confirm everything is nominal after shipment have been completed. It will be here for about another week, and then, as Bill mentioned, it will be moved for its fueling. The JamesWebb was designed with very lofty science goals in mind. To look back in time 13.5 billion years to see the first galaxies that form in the universe and see how they change and evolve to get to the type of galaxy where we live in today. Also to look at the first stars, the first light in that universe, stars that were 300 times more massive than our sun, and that when they exploded as supernova generated radiation and the heavy elements that made us. JamesWebb will continue looking for planets around those stars, exoplanets, and will be able to look in the atmosphere of the planets to see if it detects the type of elements that we identify as a sign of the life that we know: water, carbon dioxide, methane. To be able to, as well as all these faraway objects, JamesWebb is also able to look in our neighborhood to look at planets, comets, and asteroids in the solar system. The light from these faraway objects has been traveling those 13.5 billion years in a universe that is expanded. So the wavelength has expanded to, and it has moved to the infrared. So to be able to take the images and spectra of these objects, we need to do so in the infrared wavelengths, which is a little bit different from Hubble that looked mainly in the visible part of the spectrum. Planets and stars are formed in parts of the universe where there is a lot of dust and gas, and again, visible wavelength is not able to look through. So that's another reason why infrared is the optimal wavelength for JamesWebb. Now, everything emits on the infrared. We can think of it as heat. So to be able to detect the faint signals of these objects, we need to be able to cool down the mirrors and the instruments. The instruments will be very close to absolute zero, only 40 degrees Kelvin above. That's about minus 385 Fahrenheit, minus 233 centigrade. And JamesWebb achieves these cool temperatures by having a large sun shield, as large as a tennis court, made of special material, Kapton, and 5 layers that is too big to fit in deployed, so it needs to be folded to fit inside the rocket and will be open once we are on orbit. The other design driver for JamesWebb was to be able to collect more light to detect the faint signals of these objects. And we do this by having a large mirror that has 6 times the collecting power than Hubble did. Again, this mirror cannot fit in one piece, so it's made of 18 small mirrors that can be folded to fit inside the rocket. They are made of another special material, beryllium, that behaves well at cool temperatures and also can be made light. And the mirrors have a coating of gold, which is optimal to reflect infrared light. When we are at home, our mirrors are coated of silver or aluminum, which is optimized for our visible eyes. JamesWebb is going to be very far. Hubble orbits the Earth. JamesWebb is going to be 4 times the distance of the Moon, so we cannot service it. So lots of redundancy has been built into it as well. The instruments on JamesWebb are also state-of-the-art with state-of-the-art detectors. JamesWebb is an international collaboration, so one of the instruments that will be the guide and keep the observatory stable is a contribution of the Canadian Space Agency, as well as the science instrument for the near-infrared imager and slidless spectrograph. Two of the instruments, as well as the launcher, the Ariane 5, are the contribution of the European Space Agency. So those instruments is a near-infrared spectrograph and a mid-infrared imager and spectrograph. And the final instrument is a contribution from the US and the University of Arizona, a near-infrared camera. As Bill mentioned, after launch, we have 6 months of commissioning, the first month dedicated to the deployments, which you're going to hear more about today. 3 months dedicated to the alignment of those mirrors. When we look at the star, the first star with James Webb, we will see 18 stars, and we need to make it a single one. And then 2 months dedicated to the calibration of all the science instruments observing modes. To tell you a little bit more about the design of James Webb, here is Mike Mansell.
Good morning. As Begonia has already told you, the science of James Webb demands a 6-meter class telescope. And with a primary mirror diameter of 6.6 meters, the James Webb will be the largest telescope ever put into space. It'll be over 6 times bigger than its predecessor, the Hubble Space Telescope, and have light collecting power over 44 times greater than a previous infrared telescope, the Spitzer. Now, aside from just the size, science also demands that the telescope be cold, because you don't want the telescope glowing brighter than the faint stars that it's going to look at. And that telescope has to be very cold, about 55 degrees above absolute zero, or minus 360 degrees Fahrenheit, all 3.5 metric tons of it. And the science instruments have to be even colder. They have to be around 40 degrees above absolute zero. To get to those temperatures, we built a sun shield that is essentially an umbrella that'll keep the telescope and the science instruments in the shade. But this sun shield is no ordinary umbrella. It's going to be irradiated by 200,000 watts of solar radiation. And it should only allow about 0.02 watts through. So if it were suntan lotion, it would have an SPF of about 10 million. And the way we do this is the sun shield is composed of 5 individual layers, each about the size of a tennis court. The first layer facing the sun will reflect most of that 200,000 watts that hit it. But of the small amount that gets through, that wattage, that power, will reflect back and forth between the first layer and the second layer until it eventually bounces out the edges. And that small amount of power that gets through the second layer will then bounce between the second and third layer and eventually go out the sides. So here we have this, the James Webb Space Telescope. When it's integrated with the telescope and the sun shield, we'll have an observatory that stands about 3 stories tall, is 6 metric tons. It's about the size of a tennis court, and the telescope will be below 55 degrees Kelvin. This is a very challenging mission. Now, you can see the telescope and the observatory have 4 major parts to it. First, the telescope itself that we call the OTE, optical telescope element, and it has that large primary mirror consisting of 18 individually controlled segments. Behind it are the 4 science instruments that are integrated into a common assembly that we call the ISIM, the Integrated Science Instrument Module. Then we have that big umbrella, the sun shield, consisting of 5 layers. And on the hot side of the sun shield, we have the spacecraft bus. And that spacecraft bus has the traditional spacecraft subsystems, electrical power, telecommunications, guidance and navigation, that kind of thing. So with an area of about the size of a tennis court, James Webb does not fit into the launch vehicles we currently have. Ariane 5 launcher, and to fit into the 5-meter diameter Ariane 5 launcher, we have to fold which has a 5-meter diameter. Let's fold the observatory up. We have to fold the telescope up. Let's fold the observatory up. A very complex and challenging procedure. A very complex and challenging about 40 years ago. I remember one of the first lessons I got taught was avoid deployments on orbit. I remember one of the first lessons I got taught was avoid deployments on orbit. In fact, James Webb cannot perform some of the most complex sequence. In fact, James Webb has to perform some of the most complex sequence. And these come with many challenges, but I categorize the challenges into two broad categories. And these come with many challenges, but I categorize the challenges into two broad categories. Is that many of these deployments are what I'd call precision deployments. Challenge, particularly those deployments are what I'd call precision deployments. Now, think of what we're doing here. We've built on world-class infrared. Now, think of what we're doing here. We've built on world-class infrared telescope. We've tested it. We've proved it works. We've built it. We've aligned it. We're going to have to take it up. We've proved it works. Fold it up. Now and actually we're going to have to rebuild it on orbit, rebuild it, realign it, and actually rebuild it on orbit, rebuild it, realign it, retune it, and get it to work robotically on orbit. That's never been done before. And this rebuilding and this alignment are to optical tolerances. And to put that in perspective, what that means is any light ray through the telescope has to have an error no greater than 150 nanometers from its prescribed path. And if you want to know what 150 nanometers looks like, well, that's about 1/670th of the width of a piece of loose leaf paper. Now, the second set of challenges comes because a lot of these deployments involve floppy, indeterministic members like those big sunshield layers that we talked about. You know, NASA is used to deploying rigid beams on hinges because they're deterministic. You can control how they move. But these, when I say something is indeterministic, I want you to, that's illustrated by this example. Take a string and put it on a tabletop and push on it. And see if you can predict the shape of that string. Chances are you will not be able to. And so it is with the membranes of the sun shield. So we can't really predict their shape, but we can constrain it. We can try to prevent it from going in places that we don't want it to go, places where it could snag or tear or maybe impede the deployment of other members. And we do that by building in restraint mechanisms. And there's going to be a lot of these restraint mechanisms when you're talking something the size of a tennis court. We've done extensive studies, we've done extensive experiments to determine just how many of these release devices we want. You see, we want to have enough devices to control the sun shield, but not too many to add unnecessary failure modes. Now, we've done these exhaustive studies, and the answer we came up with was reviewed by various independent review groups. And in the end, we've all agreed. We found the sweet spot on this. We found the right mix of mechanisms. The final part of the mission that I want to talk about that's a little unique is our orbit. We're not going to be orbiting the Earth. James Webb will operate around the Sun-Earth second Lagrangian point. Now, that's a point 1 million miles away from the Earth, 4 times farther than the Moon, on the opposite side of the Sun. It follows the Earth around the Sun every 365 days. And it's a point where the gravity of the Earth and the gravity of the Sun combine to make a relatively stable point. Now, our Ariane 5 launcher will put us on a direct inject path out there, and it'll take about 40 or 50 days to get out at that distance. And during that time, we'll do 3 mid-course corrections. We'll do our deployments that you'll hear more about in a second. And around 40 or 50 days after our launch, we will actually fall into a little orbit around the L2 point. By that time, we will have cooled down, and we will be calibrating our instruments. And at launch plus 180 days, the observatory will be commissioned, and we'll be ready for our science mission. And during that science mission, we will execute an orbit around the L2 point that takes about 180 days. Now, because the L2 point is only close to stable, we have to do station keeping maneuvers to stay in that orbit, and we'll do station keeping about once every 21 days. And now to talk more about the deployments, our deployment systems lead, Alfonso Stewart, will come up and give a better explanation of some of these.
Thanks, Mike. Here at the launch facility in French Guiana, helping to prepare Webb for the integration to the launch vehicle. You've heard about the science goal from Begonia and the overall design of Webb from Mike, but what I'm going to talk about is the nominal deployment sequence we're going to go through in order to achieve the deployed state. So what is origami? Like an origami object, proper folding and unfolding is necessary in order to achieve a specific shape, and Webb will do origami in reverse, meaning that it will unfold in a certain sequence. Now, you may have also heard the reference 29 days on the edge, and what that means, there are 2 important times in that deployment scenario. There's the launch And also at L plus 28 days, there's the thruster burn to insert Webb into its operational orbit. The timeline we're going to talk about today is the nominal timeline. However, we do have the flexibility within that timeline to adjust if necessary. Now, at the start of deployment, the predicted temperature is approximately 20 degrees C, about room temperature. However, over the deployment timeline, the temperature will decrease down to negative 200 degrees Celsius. The first deployment is the first set of deployments are the solar array and high gain antenna. So why the solar array first? Well, electrical power is required for the observatory to function, and the battery can only last a few hours. So we need the solar array to be deployed in order to continue with the mission, and then followed by the high gain antenna for the necessary communication capabilities in order for us to continue the commissioning activities. In preparation for the sunshield deployment, the UPS, or unitized pallet structure, deployment tower assembly, and the trim flaps are deployed. Then we start the sunshield deployment sequence. That sequence starts with the membrane cover release as shown here in the graphic, followed by the mid-boom deployment that pulls out the membrane in radiator shade. Next, we have the OTE assembly that deploys the secondary and primary mirror assembly. Now, in addition, as I mentioned before, this is a nominal deployment sequence that we're planning. However, Webb uses contingency operation in the event of an anomaly deployment action. Now, these operations range anywhere from the simplest, such as checking the telemetry and resetting the command, to a more complex operations such as switching to the redundant system, or we can also use what we call excitation of the observatory, what we aptly name shimmy, twirl, and fire and ice. And now we have Crystal Puga that will describe the most complex of these deployment in further details. Over to you, Crystal.
Thanks, Alfonso. I'm here in the launch site control room in the satellite processing building in French Guiana. This is the room where Webb engineers will monitor the observatory's state of health on the day of launch using the telemetry you see on the screens behind me. So as the other speakers mentioned, the sunshield is a critical part of the observatory. It has one simple task. It needs to protect the observatory by blocking the heat from the sun, the earth, and the moon. Although it's a task, it is worth diving deeper to truly understand the truly pioneering system and how the sophisticated umbrella works. The sunshield separates the Webb into the hot and the cold side. On the hot side of Webb, it is a toasty 260 degrees Fahrenheit. Meanwhile, on the cold side, it's a freezing negative 300 degrees Fahrenheit, which is colder than any place on Earth. That's a roughly 600 degree temperature differential, which is accomplished passively using 5 tennis court-sized sunshield layers made out of a special material called Kapton. Kapton has unique thermal properties that are needed to keep Webb cold. It's highly resistant to heat and remains stable across a large temperature range without burning or melting. On Earth, Kapton is typically used as an electronic insulator and is actually a translucent amber color. So in order for us to accomplish the heat radiation bouncing technique that Mike described in an earlier section, we first need to enhance the Kapton even more. First, we coat it with an aluminum on both sides, which makes the membranes reflective, allowing for that bouncing and for the heat to be able to reflect out in between the layers. We also apply a silicone treatment, which is applied on the sun-facing side of the 2 hottest layers, which is the silicone is actually even more effective at radiating the heat back into space. This also gives the sunshield a soft purple color that you see on the bottom of several of the images. The sunshield Kapton material is super lightweight, and in fact, it's really thin. It's only about the thickness of a human hair. And I have a sample here with me. You can see the sample. It's very crinkly, and it's very, very thin. In order for us to construct the sunshield, we actually put it together like a quilt using patches of this Kapton that we thermally bond together. So you can see a bond here, thermal bonds, putting 2 of these pieces together. Those bonds create about 10,000 seams. Each layer has a unique template because each layer is actually slightly different in size and in shape. To strengthen the membranes, we actually add reinforcement strips about every 6 feet. These reinforcement strips act as ripstops to help eliminate or contain any tears or holes that are caused by micrometeoroids. The metallic ribbons also help to provide structure to the membranes. Before we get into the sunshield deployment, we first need to address the stowing process, which is just as critical. The sunshield has to be packed away to fit inside of a 5.4 diameter rocket fairing. The folding process has a very specific sequence. First, we carefully fold back and forth accordion style using engineers that are fully trained and know not to handle the material very delicately to avoid any creases or tears. They also use a specially designed folding fixture to allow them to do that. After we fold each sunshield membrane, we then fold it up in between around all of the sensitive telescope and optics. So we need to make sure that when we deploy, we don't accidentally snag on any of those sensitive components. Our sunshield is very similar. It's our lifeline, similar to like a skydiver's parachute. It needs to be folded perfectly so that it unfolds and deploys perfectly without those snags, without any tangles. Now to the sunshield deployment. I think of the sunshield deployment similar to like a Rube Goldberg machine in that it uses a series of reactions that work in successions, triggering one event after the other until the entire sunshield is fully deployed. Some of the key hardware include 140 release mechanisms, about 70 hinge assemblies, 8 deployment motors. We have several bearings, springs, gears. About 400 pulleys are needed and 90 cables totaling 1,312 feet. The sunshield deployment starts on day 3, just after we pass the moon, and it will take approximately 3 days.
Temperature-wise, to still have a successful mission. And what I mean by that is, if all the layers don't fully deploy and separate exactly as planned, can you still do science if 2 layers are touching, for example? Or if it gets hung up somehow, like can the near-infrared instrument still collect valuable science, even if you don't get a full deploy? If somebody could talk about those scenarios, I'd appreciate it. Thanks.
Sure. That's a great question for Mike.
Yeah, we do have some tolerance to that. One of the things that we've insisted on during the design of this is a cryogenic margin, heat rejection margin, and right now we're flying with about 80% of cryo margin, meaning we could anticipate, we could have unknown heat loads, for instance, about because of the layers touching. Now, we wouldn't want all the layers to touch, but if it's a localized touching in one place between 2 layers, that shouldn't be a problem for us, and that should only consume something of around 10, 15, at most 20 percentage points of our margin. So for the near-infrared instruments, I don't think that would be a problem at all. If it was more global contact, then if we started to eat significantly into that 80% margin, then we'd start to have a problem. But for our near instruments, that would the degradation would be graceful. And I don't have an exact number for you in terms of temperature on that, but I would suspect that detector temperatures probably, of around anywhere between 45 and 50 degrees Kelvin could still be tolerable to our mission in the near infrared.
Thanks.
Our next question comes from Marcia Dunn. Your line is now open.
Yes, hi. I have some questions for Mr. Metzel again.
Certainly, the sun shield deploy. Correct me if I'm wrong, but it certainly sounds like the tensest, most hairiest, the most hairy part of the whole deployments. Is that true in your mind? Is this really going to be the most dramatic part of the whole early part of the mission? And how much of a gap is there between the layers? I'm wondering, like, it's the size of a tennis court, but how thick, if I were looking from the side once deployed, how thick would this be? And lastly, if I'm looking at this tennis court size sun shield, do you have to have at least, would you guess, half of it deployed properly in terms of how the perimeter? I mean, just 3/4, or is it? Or can you not really specify? Thanks.
Okay. Well, first to your first element. Yeah, of all the things that that I guess I don't want to say worried about, but the things that we focused on for deployments, it's definitely the sun shield for reasons, at least my personal reasons that I've already elaborated on. The sun shield is one of these things that is almost inherently undeterministic, unlike the things on the OTE, where once again we have rigid booms that are on hinges and latches that we know how to control. Although we've certainly focused on that. So the sun shield is the one that has some risk to it, and we've certainly tried to concentrate on that. In terms of your other question as to the different failure scenarios, it would be, I don't think that I would say that if half of it didn't deploy, we wouldn't have a problem. We certainly would. As to, if portions of it didn't deploy exactly the way we wanted to, a lot of that would depend on where the misalignment was. But as I said, we have a cryogenic margin for some of that. And if the imperfection was localized, let's say to something around 12% of the perimeter didn't have the gap we want, we would probably be okay with that. As for the exact gap as for the exact dimensions between the gap, I think I might see if Crystal might want to answer that. I think it's of the order. The largest gap we have might be of the order of about 0.8 meters, or somewhere between 1.5 meters. If Crystal would want to correct me on that.
Yeah, so we do have a separation about 16 to 18 inches in between the layers. It actually the distance varies because if you look at the photo of the James Webb, it's actually closer in the core region. There's actually a smaller gap, and as you extend out towards the edges of the sun shield, the gap gets a little bit bigger, and this helps again with kind of that bouncing of the heat in between to radiate it out, which is why it's a little bit wider on the edges.
In the meantime, while we're waiting on the next...
Our next question comes from Chelsea Goes. Your line is now open.
Thank you. Chelsea Goes with Space.com. As you've all illustrated, Webb clearly has a very complex deployment ahead of it. Could you talk a little bit about the kind of contingency plans you have in place? As I assume any anomaly at any of these stages of deployment would require perhaps multiple contingency plans, and how much pressure is on the team to get this right?
That's another good question for Mike.
Well, we do have multiple contingency plans, and I'll turn it over to Alfonso to talk about some of them in detail. Some of these plans have been pre-formulated for the more time-critical deployments, and there's only one deployment really that's time-critical, and that's to get the solar array out. So we have some pre-formulated, pre-canned deployment plans or contingency plans for that. For the other type of deployments, I'll talk to Alfonso a little, or I'll hand it over to Alfonso to talk a little more about that.
Yeah, thanks, Mike. Yes, there are numerous deployment operation or contingency operation that we have, and as I mentioned before, the contingency range anywhere from the simplest to the more complex. And I mentioned as an example, you can simply send the command again. Also, there are quite a bit of redundancy in the system. We have multiple ways of sending the same signal. In some cases, it's just a telemetry. In order to know that you have an anomaly, it could be just you have an erroneous telemetry. So we have redundancy telemetry, or we can check and verify telemetry through other means. So there's quite a bit of redundancy. In addition to over the past years or so, the team have been practicing these contingency scenarios where an anomaly is introduced and the team will work to try to solve it in a sort of rehearsal plan. So both the design from in terms of redundancy and features in the mechanism, as well as procedures in the way we operate and the way we deal with these, we have been practicing and using and exercising those systems over the year to anticipate and to deal with these anomalies if they come up. So yes, we have been practicing quite a bit for that.
Our next question comes from Stephen Clark. Your line is now open.
Thank you for taking the question. I think my question is probably for Mike or Alfonso. Are there any areas in any of the deployments where there could be a single point failure? If there's an area where something doesn't work, it would be very difficult to recover from that, like a mechanical structure or an electrical system or anything like that. And also, the deployments of the mirrors and the sun shield, do those, I know you said you have some flexibility in the schedule, but do they have to happen before you get to L2, or could you push that weeks, beyond the scheduled intended date if necessary? Thanks.
Let's start with Alfonso.
Yes. Let me take the last one first. I believe the question was about do we have flexibility in the schedule for the mirror deployments? Yes, we do. The nominal deployment sequence is that we start the mirror deployment over approximately a 9-day period at around L plus 14 days. However, that deployment can occur much later into the program, even after the second burn at L29. So we do have quite a bit of flexibility in the mirrors. Now, I think the first question you asked about other flexibility we have or single point failures. Yes, we have identified single point failures on the system, and once we've done that, we have very detailed and extensive testing and review of the design, and just to make sure that these things are the reliability or such. But there are single point failures on the system. I don't remember the quite number. I think Mike, if you remember the numbers, but there are quite a bit of single point failures. Single point failure system on the observatory. But we have identified those, and we have developed really rigorous test plan and operation procedure to deal with those. Yes.
Well, only as Alfonso alluded to, when we identify a single point failure, we give it very special treatment. We have what we call a critical item control plan, and we always throw in extra inspection points, and we've done extra offline testing on these devices. For each item that we've identified as a single point failure item, we do detailed analysis, and that includes testing, to identify all the possible ways that it could fail, and to make sure, for instance, if we know one of the ways it can fail, we add in extra inspection steps and extra tests and extra screening to make sure that probability of its failure is extremely low. So we've given our single point failure items a lot of attention, because when it comes to deployments and mechanical things like deployments, it's very hard to not have single point failures in them. And that's one of the reasons why we take our deployments, these deployments, as a very, very serious matter.
Okay, let's go to our next question.
The next question comes from Paul Brinkman. Your line is now open.
Hi, yeah, this is Paul with UPI. I'm wondering if, I guess, kind of a follow-up to what Alfonso has been saying. You mentioned sending commands during the deployment.
I think we just lost Paul for a second. So we have a question from Rosie on Twitter. When is it going up? Bill?
So the launch date is December 18th, about 9 o'clock in the morning or so, Kourou time, which at that point will be 2 hours ahead of East Coast time.
And then the follow-up question from Alex on Twitter. Most telescopes are enclosed by a tube. Why doesn't the Webb telescope use that? Mike?
Yeah, that's an excellent question. The reason for that is due to the thermal. A tube around the telescope would actually impede its cooling. So we couldn't have a tube around it, which causes us, obviously some risks with stray light. But we've put in light shields at various places to preclude that. But the bottom line is we don't have a tube around that telescope, because if we had a tube there, it would actually impede its cool down to the 55 degrees Kelvin that we want.
Okay, next question from our operator.
Next question comes from Jeff Foss. Your line is now open.
Good morning. For the SunShield deployment, I'm curious what sort of instrumentation you have to monitor the deployment, the ability to stop or even retract the deployment if you detect any sort of snagging or tearing or other problems as you try to deploy the SunShield. Thanks.
Crystal?
Yeah, so we do have telemetry. We have read switches and telemetry switches that will allow us to determine when some of those deployments are made. In terms of being able to have the ability, some of the motors that are used, we can retract them, we can turn them back if we need to do any adjustments.
Okay, next question.
Okay, our next question comes from Lauren Grosh. Your line is now open.
Hi, thank you so much for taking my question. I was wondering if you all have an unofficial point during the deployment process that you've agreed upon you'll breathe a sigh of relief. I'm wondering if that is the essential deployment or if there's more to come after that that will be a sigh of relief for y'all. And then I'm curious, what is the protocol if you do realize that there is a showstopper failure, and what do you do if that ends up happening? Thank you.
Bill?
Let me try to take it. So I think I'll answer the first question first. Where we all breathe a sigh of relief is going to depend upon who you're talking to. As the project manager, I won't breathe a sigh of relief until we declare we're operational 180 days after launch. From a deployment standpoint, it's when all deployments are completed. We do have procedures set in place where if we start having issues that are extracted for a long period of time, we will go through a process of really narrowing down in on the problems. This team, one of the things, I've been a project manager for almost 11 years, and this team does not give up. So we don't talk about what do we do if we fail. We talk about how we correct problems that we see on orbit and how we move forward from there.
Okay, next question.
And as a reminder, if you'd like to ask a question at this time, please press star 1. Again, that is star 1. Our next question comes from Jonah Abels. Your line is now open.
Hi, thanks very much indeed. I think this might be a question for Alfonso. He mentioned excitation and shimmy. If there's a problem in the deployment of the SunShield, I wonder if he could explain to us when and how he would dance with the stars, so to speak.
Yeah, I like that analogy, dancing with the stars. So let me explain. Again, that's a contingency. It's sort of like the very end of what we would normally do. And those that excitation contingency is basically, if you can imagine, you are exciting this observatory. And when I say, for instance, shimmy, you're rocking the observatory back and forth. So, for us to do that, we would have to determine that will it really work, depending on what the failure is, and there'll be quite a bit of investigation to find out whether or not that particular system will work. Now, in terms of twirl, just like it says as twirl, we basically can spin the observatory about any given axis. And for fire and ice, what that's referring to, we can orient the observatory in such a way to put sun or heat up certain areas that we need to if we deem that that's necessary for the deployment. So that particular exercise of that contingency is probably the last ditch. Again, like I said, we have quite a bit of alternative contingencies in the system, such as redundancy and multiple ways of sending the same commands. So hopefully we don't have to use that one. Thank you.
Our next question comes from Marina Korn. Your line is now open.
Hi,
Can you give us an exact number for how many single point failures exist in the observatory overall? I've seen 307, 344. Do you have an exact number? And two quick follow-ups. Does this observatory have more single point failures than any other NASA spacecraft? And why are there so many? You said that it's hard to avoid so many for this kind of mission, but why is that? Thank you.
Mike?
Yeah, there are 344 single-point failure items on this observatory. That's the correct number. The reason for that is approximately 80% of those are associated with the deployments and are associated with the fact that we have mechanisms. It's hard to avoid, when you have a release mechanism, it's hard to put full redundancy into that. It's hard to compare it to other missions I've tried, and there are two things that make the comparison a little hard. First, we have a lot of release mechanisms, and I tried to emphasize the fact that we tried to decrease that, and we found the sweet spot between getting the control that we want for these large, flexible membranes, and still, not or not putting more single-point failures on there. So we've done extensive studies on that. And, as I said, I've tried to compare this to other missions. And the other thing that to bear in mind is very early on, our review boards wanted to make sure that we really took good attention to that. So when we counted our single-point failure items, and when I give you 344, those are individual single-point failure items. Some other missions count them slightly differently or count them a little less conservatively. We've been very conservative on this, and our review boards have actually lauded us for the fact that we've paid this much attention to it. But when you're talking about release mechanisms, mechanical release mechanisms, it's usually pretty difficult to avoid an item that we considered a single-point failure item.
Our next question comes from Paul Brinkman. Your line is now open.
Hi, can you guys hear me? Hello?
Hi, we can hear you.
Oh, okay. I guess I'm kind of following up on something Alfonso said. To what extent is the process automated or robotic? And you mentioned sending commands, so I'm wondering how many times during the deployment do you have to send those commands if everything is going perfectly well? And I'd also like to hear, to what extent the eventual operation is robotic. And compared to Hubble, is James Webb more independent in terms of its operation, or is that kind of identical to Hubble? Thanks.
Alfonso?
Yeah, thanks for the question. For James Webb, the solar array and the initial release of the deployment radiator, the aft deployment radiator shader, or ADIR, is the only sort of automatic release system that we have. The rest of the deployments are all ground command, meaning that we will take our time and we send the command from the ground and wait for confirmation via the telemetry. So that all of the deployment after the initial deployment of the solar array are ground command, which we take our time to do. Did I answer all your questions? I don't remember. Yeah.
I just asked about operations also. That might be better for Begonia to answer. Is James Webb kind of more autonomous than Hubble is, or do they operate sort of similarly in terms of finding targets for investigations, I guess?
Okay.
Yeah, James Webb is a little bit similar to Hubble. So once the once the targets are selected, right, an instrument wants to observe a particular target, those are loaded on board. A particular guide star is found that will achieve the target needed, and those are loaded on board and they run autonomously once they are launched. During the commissioning period, we do it step by step as we, again, take our time. So there is a very careful set of activities that we will be doing, and they are generated on the ground, loaded on board, and launched. We get the data, we confirm it's good, and continue. But after the 6 months of commissioning, the plans will be structured. for the different science programs, also in a way to avoid unnecessary slewing of the observatory in an optimal way, and those can be loaded continuous weekly to proceed.
Okay, thanks.
Thank you. Next question.
Next question comes from Bill Hardwood. Your line is now open.
Hey, thank you very much. Just a question for, I guess, Mike. We've all focused on the sun shield, and that's an obvious thing to focus on. But could you talk a little bit about the complexity of aligning the optics, how each of the mirror segments has, the motors that can reorient them, can change their shape slightly, and how you go through that process of moving from 18 images of a star down to one tightly focused image? Thanks.
Yeah, I think at the next briefing we'll go into more detail on that. But I will tell you that our optics team, in particular our wavefront sensing and control team, has formulated a very methodical approach to taking those initially the 18 individually blurred blurred images that will come from each segment, and coalescing them into one image and then refining that to get one diffraction limited image at 2 microns. We have a very definite way of doing that, and we've tested that way several times on various test beds. One of them, called the telescope test bed, is a small version of James Webb. It's essentially an optical telescope, but it has 18 individual segments that the team has practiced alignment on. And I think you'll hear more about that when we get our optics leads up here for the next briefing. But there is a very methodically, well thought out and well practiced wavefront sensing and control procedure that will take those 18 blurred images using the 7 degrees of freedom on each mirror. The 6 of them are the right, left, up, down, in, out, and then we have the tilting in the 3 directions, and then we actually have a 7th that can actually alter the shape of the primary mirror segments a little. So they'll utilize that along with actuation on the secondary mirror to get that final refined diffraction limited image at 2 microns. So, but the one takeaway I would say is that has been practiced on various test beds, one of which we call our telescope test bed. That is a miniature telescope with 18 individually controlled segments.
Thank you. We have a question from social media. This is for Crystal from Alan Smith on Twitter. Why is each sunshield layer such a complicated shape? Why couldn't each layer be a simple plane?
So, we were trying to, in the way that we were designing the sun shield, right, we're trying to obviously cool it to get it to very cold temperatures. So each layer, the bottom layer, we wanted to actually block more of that's coming from the various heat sources. So it actually has to be a much larger shape at the bottom. We can get away with maybe making them slightly smaller as we go in. So we didn't necessarily need to make them all the exact same size. And then I think actually I'll pass it over to Mike to elaborate a little bit more on that.
Yeah, when it comes to the question of why it couldn't be one plane, that was one of the very early trades that we all looked at. And it turns out by making it almost a biplane, as you can see, it kind of looks like this. That helps us with the way momentum is accrued, angular momentum is accrued by tilting, when we tilt the telescope to various attitudes, the solar radiation vector, the pressure vector from solar radiation, and our center of mass and our center of our inertia can become misaligned. So by putting 2 planes in there, we can actually accrue less angular momentum for various attitudes. So that was the first question. And as for the shapes, we did want to tension the membrane. So part of that shape comes as a result of the tensioning and the fact that we want a gap at the edge, and we don't want as much of a gap where we anchor it. So part of that was a natural consequence of those boundary conditions. But when it comes to why we have 2 planes, it's essentially to try to minimize angular momentum accrual over the various attitudes that we will be scanning to.
Let's go to our operator.
Our next question comes from Marcia Dunn. Your line is now open.
Yes, for Mr. Metzel or Oaks, either or. I'm curious. Once the sunshield is deployed, how vulnerable is it to bits of space junk, micrometeoroid? I mean, is this going to be something daily that you're always worrying about to ensure that it's not damaged somehow? And I know that the spacecraft will be impossible for astronauts to reach. However, if SpaceX or somebody came up with some kind of mission to try to salvage it, is this spacecraft even repairable by human hands if you were able to get someone there in an emergency situation, or would that just be impossible the way it's designed? Thanks.
Yeah, I'll answer the micrometeoroids. I don't have the exact numbers with me, but we anticipated micrometeoroid degradation on both the sun shield and the primary mirror. We've accounted for that, and I don't have the exact numbers, but we do know we did hypervelocity experiments at Auburn University in the early days of this to see what kind of damage a micrometeoroid would do. And luckily for us, given the velocities that we expect from these things, the micrometeoroids, when they hit the mirror, will put nice, well-defined little bullet holes in it that'll really just detract from the collecting area. And when it comes to the sun shield, when they hit one of the layers, the micrometeoroid will pretty much disintegrate upon its first impact, and the debris will go out and maybe strike the next layer. The good thing about it is it's very unlikely that one micrometeoroid will put a bullet hole in line through all 5 layers. That would be a bit of a pain, because then sunlight could make its way through. When it comes to your other question, as for serviceability, I will give that to Bill to answer.
So we get asked that question quite a bit. I think it was designed from the get-go to be serviceable. We have not been designed that way. There are aspects of us where you could not go in and change out an instrument. Our instruments are intertwined together. You cannot easily go in there and remove those instruments. There are other aspects that might be, if somebody was ingenious enough to service. Maybe there's some boxes that we might be able to get to, but there's no boxes on the outside of the spacecraft bus. They're all on panels that are folded on the inside, so that would make them difficult to get through. The one thing that we have done is our limiting resource is fuel. And right now we should have fuel to go 10, maybe even 10 plus years, out to even 13 years. We have put targets on the around where the fueling is, and I've made the fueling, let's say, for lack of a better term, the gas tank is available. So if somebody was ingenious enough to get up there and try to refuel it, they would be able to refuel it.
Thank you. We have one more question from the media.
That question comes from Stephen Clark. Your line is now open.
Thanks. I think my question is regarding the decision not to put cameras on the observatory to monitor any of these deployments. I know that decision dates back some time, but in hindsight or with modern technology, do you wish you had put cameras on, and would that really offer any insight into any sort of anomaly with any of these deployments? Thanks.
Mike?
Yeah, we've labored over that for many years, and frankly, I don't regret the decision, but it was a tough decision, and here's some of the factors that went into it. First, we could put some cameras on, and the first thing we asked ourselves is, well, what do we want to see? And and where do we want to look? And we found that the range of places that we wanted to look were all over the observatory. So now you could solve that by saying, well, let's put a wide camera on there. But that wouldn't really help you diagnose something that's really going wrong, like a snag. So let's put a high magnification camera on there. Well, then you got to put a lot of them. And where do you want to put them? Well, the majority of them are ended up going to be on the cold side. So now you've got cameras on the cold side, but when the sun shield deploys, it's going to be dark there. So now you're going to put lights on the cold side. And now you're going to be putting all the wires that go over to the cold side on there, and that's going to add parasitic loss. That's going to help heat leak from the hot side to the cold side. So, and then after the thing gets down to temperature, you need cameras that can passivate, or the cameras that can tolerate temperatures in the 55 degree or maybe lower region. So when we started summing all this up, summing all these cons against the cameras, against their benefits, we found that it really, we were in a land of diminishing returns where we really weren't getting all the benefit we'd want from these cameras, but we were getting a lot of extra nagging problems that we'd want to go along with this. So, it was a tough decision, and we've re-looked at it over the years, and each time we re-looked at it, the cons seem to outweigh the benefits, and that's the short story on this, but it is a good question and is one we've labored on over the years.
Thank you so much to our team here and in French Guiana, and thank you to everyone watching for the privilege of your time today. If you'd like to follow more news on the Webb telescope, go to web.nasa.gov or follow the hashtag NASAWeb. Have a nice day, everyone.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
It is pretty fitting that these are called cosmic flames. These packets are nothing but a bunch of different elements. So lithium makes red, barium makes green, and so on. And then they burn in these really pretty colors. Burning chemicals is a legitimate way to find out what something is. Chemists call it the burn test. All elements actually give off a signature when they are put into an excited state. Here, we are witnessing what happens in a fire. The James Webb Space Telescope will be able to read the same signatures from unknown stars and planets. I've been taking you through different elements that are built into the Webb telescope. Gold reflects infrared well and will not corrode. Beryllium is lightweight. Silicon is a tried and true semiconductor. Isn't it just poetic that Webb is designed to detect elements? Webb uses a device called a spectrograph. It works by splitting the light with a prism. We can tell what element we see based on the pattern from the light through the prism. Every element releases light at a different wavelength, and when that light is split by the prism, black bands appear due to the transition between the energy states. These are called absorption lines. The lines always appear in the same part of the rainbow, which is why we call them atomic fingerprints. I've made my own simple spectrograph to give you an idea about what Webb sees. And the object that makes this whole thing work is a relic of technology. It's a CD. CDs and DVDs use the same principle as another ancient device, the record. They use tiny tracks or bumps to convey the information. Records use a 3D representation of the sound, and a CD uses raised binary points. The point is that the discs have a very fine groove pattern that physically splits light. That's why they have a rainbow or iridescent color. Webb spectrograph also uses fine grooves to split light. The near-infrared spectrograph, called NIRSpec, is designed to take spectra from up to 100 objects at once. You don't need to go all the way to space to see the spectra from different objects. My little homemade spectrometer can tell me the primary element that different light sources use. Neon lights get their name because the lights use neon gases to get their color. Actually, the neon only refers to one color. These types of lights use other gases to make more colors. Let me show you the full spectrum of colors that we can see based on a combination of these different elements. Webb spectra really give more information than just the elemental makeup. They can also tell astronomers about the temperature, the mass, speed, and density of the objects as well. All elements have a cosmic start. Smaller elements are forged in the heat and pressure of a star. Anything larger than iron needs a powerful force of a supernova or colliding neutron stars. These elements may stay as dust clouds or eventually coalesce into asteroids or planets, characterized by their original elemental makeup. The spectra Webb will see not only tells us what elements we're looking at, but the warmth and the density of the bodies as well. So we might detect some distant biosignatures. Webb's build might use a scarce element like beryllium for its mirrors, but will this cosmically occasional element help us find something far rarer, like gaseous carbon, oxygen, or nitrogen? Can we determine where to find the building blocks of life in other worlds?
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb telescope will find.
I believe that the Webb's telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space. Hello, my name is Gabriel. I am from Romania. This is how I imagine space. Hello everyone, good morning. This is a drawing of distant galaxy that can be seen by James Webb Space Telescope. Hi, my name is Anastasia, and this is what I drew, what I think the telescope will look like, what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
When you look at NASA's James Webb Space Telescope, you can't help but see the huge gold mirrors. But that gold is really only on the surface. The rest of the mirrors are made out of a metal called beryllium. Let's head over to the shop that worked on these mirrors to get a better idea about why this metal is so remarkable. And it's like, follow the noises. Engineers chose beryllium for 3 major reasons. It is super lightweight. It is the second lightest of all the metals and only 2/3 the weight of aluminum. It's super strong. Beryllium is 6 times stiffer than steel. Each of these cantilevered weights are the same except for the type of metal. They are the same length, the same weight, and size. Look at what happens when they are lifted and released at the same time. That beryllium wiggles with less intensity and stops moving first. That's because it's far stiffer than the other two. So it can also hold its shape over a really broad range of temperatures, and that's especially important in the cold ones. I measured these identical aluminum and beryllium mirrors, and then left them in some dry ice for a while. Science. I do have to admit that my measuring technique could use a little work, but the aluminum shrunk more than the beryllium. Materials as a whole tend to change in shape, volume, and density in response to temperature. When something is heated up, the molecules begin to vibrate and separate a little. The amount that the material changes is predictable and is based on its coefficient of thermal expansion. So beryllium, it stops shrinking and changing its size when it cools below 100 Kelvin. So the mirrors we see are a little too large on Earth, and will be the exact size they need to be once they are out in space. Beryllium is obviously an incredible material, but everything does have its nuances. So, why isn't beryllium used more often?
Machining beryllium requires extreme care. And if you think about it, beryllium actually is a powder that is pressed together and requires very, very light cuts. Any small mistake, it would crack, and there would probably be a piece that would chip off. And you've lost a part that could be worth anywhere between $1,800 to $2,000 a pound.
Under the wrong circumstances, beryllium may be fragile, and it's fairly expensive. But it holds its shape well, is very stiff, and most importantly, it's lightweight. Rockets need a lot of fuel for each pound of payload. So any weight-saving measures are really, really worth it. In a specialized building like this, NASA built a new machine for science. The James Webb Space Telescope is a complex collection of scientific instruments designed to tackle some of the biggest questions in astrophysics. Webb has 4 instruments contained within the Integrated Science Instrument Module, or ISIM, located directly behind the primary mirror. They're all designed to observe an infrared light, which is invisible to human eyes. Infrared is a longer wavelength of light located on the electromagnetic spectrum, just beyond light human eyes can see. We feel infrared light as heat. Each of the instruments play a different scientific role. The near-infrared camera, or NIRCam, is the main imaging system. NIRCam will look back in time to study the formation of the earliest stars and galaxies. One aspect of its design includes the ability to block light from a bright object, so much that a much dimmer object nearby might be observed. This means that in addition to looking at distant objects from the earliest days of the universe, scientists hope to study aspects of planets orbiting nearby stars. The NIRCam instrument also plays a key role in the process of aligning Webb's 18 primary mirrors, its secondary mirror, and its fine steering mirror using a clever technique called wavefront sensing and control. One of the best ways to find out new information about distant objects is through analysis of the light those objects emit. The Near-Infrared Spectrograph, or NIRSpec, will collect spectral information about distant objects in order to determine their composition, temperature, velocities, and mass. To do this, MirSpec will employ a unique technology called a micro-shutter array. It's an extraordinary collection of mechanical shutters, each barely wider than the thickness of a human hair, that can simultaneously collect high-resolution data from up to 100 distant objects. Different wavelengths of light present different information, and each of Webb's scientific instruments pursues different slices within the infrared spectrum. The mid-infrared instrument, or MIRI, will look at wavelengths of light that are a little longer than the other instruments will observe. Not only will this enable extraordinary images, but it will also allow scientists to search for planets around distant stars, dust warmed by starlight in protoplanetary disks, and comets and asteroids in our own solar neighborhood. MIRI is the coldest instrument on Webb, operating at just 6 degrees Celsius or 11 degrees Fahrenheit above absolute zero. The fourth part of Webb's instrument suite is 2 instruments. The near-infrared imager and slitless spectrograph, working in concert with the fine guidance sensor, will look for ancient light in the universe and information about planets around distant stars. The fine guidance sensor helps keep Webb pointed and perfectly steady during all observations. Together, these instruments and the technologies that will enable them will make up one of the most complex and ambitious undertakings in the history of humanity. This is NASA's James Webb Space Telescope. The most prominent and beautiful part of NASA's James Webb Space Telescope is its gold primary mirror with a smaller secondary mirror suspended out in front. The Webb telescope is a reflecting telescope, technically an astigmatic telescope. This means that its concave primary mirror captures the light and reflects it to the secondary convex mirror, which reflects the light back to the concave rectangular-shaped tertiary mirror, and then, finally, to the flat fine steering mirror, which sends the light through a hole through the center of the primary mirror to focus on the science instruments behind the primary mirror. This kind of telescope enables a wider field of view and minimizes optical distortion. The primary and secondary mirror form what is called a Cassegrain telescope, similar to the Hubble Space Telescope. It's this third powered mirror that makes Webb an astigmatic telescope. Webb has the largest primary mirror ever to fly in space. At 21 feet and 3 inches across, or 6.5 meters, it's built to see the faintest light coming from the most distant luminous objects in the universe. Its size presents one of the biggest mission challenges. The primary mirror is larger than the fairing of the rocket lifting it into space. So Webb's mirrors has to be segmented and folded for launch, and that means it has to be unfolded and focused in space. Webb's mirrors are made out of a rare metal called beryllium. Because this chemical element is very strong, lightweight, and virtually ceases changing shape when it gets really cold. Starting from beryllium mines in Utah, the mirrors crisscrossed the country. The beryllium was made into a powder of microscopic spheres, then fused by intense pressure into solid discs that were machined and polished. Lastly, the mirror segments were coated with a thin layer of pure gold, less than 100 atoms thick, to best reflect infrared light. All of the mirror machining and polishing was done at room temperature. Because beryllium changes its shape with temperature and only becomes stable at very cold temperatures, the mirrors were manufactured to precisely the wrong prescription at room temperature, so that they have precisely the right shape at operating temperatures. That's negative 388 degrees Fahrenheit or negative 233 degrees Celsius. That's colder than the surface of Pluto. A robot-like system perfectly mounted each mirror onto Webb's composite backplane structure. Behind each mirror is an actuator system that can move each mirror segment precisely in every direction, as well as modify each segment's shape ever so slightly, so that all 18 segments can be aligned to form a single perfect mirror. After Webb is deployed, it takes several months for the instruments to cool to their operating temperature. During this time, engineers on the ground will use Webb's near-infrared camera and a process called wavefront sensing and control to align Webb's mirrors. The mirrors will be retuned as needed during the mission to maintain Webb's perfect vision. Once Webb launches and the science team aligns those extraordinary mirrors, a new scientific era will begin.
How did we get here? Big questions about who we are and how we got to be that way are at the core of our nature. We've developed technology to see amazingly far across space and also time. Light moves through space, just like we do, only much faster. It takes time to get somewhere. So, viewing the light of distant stars and galaxies is like looking into the past. It took time for the light to reach us. Yet, after all our years of exploring, to better understand ourselves and our origins, there is still so much to know. Our story stretches back more than 13 billion years, not long after the expansion of time and space first began. At some unknown time, the building blocks of life were forged in the heart of the first stars. But much of the early universe remains a mystery. There are theories about how gravity first brought stars, gas, and dark matter together to form galaxies. But that time period has never been observed. Detecting light from the first galaxies to form has been a challenge for even the most powerful telescopes. As the light early galaxies emitted traveled through space, that space itself was expanding, stretching the light to longer infrared wavelengths. Past telescopes have detected infrared light, but the faint light of the very first galaxies has remained out of reach. Until now. The James Webb Space Telescope is specially designed to detect the first galaxies. Webb's large mirror and sensitive instruments will enable it to collect more infrared light than we've ever seen, allowing the first galaxies to emerge into view. With Webb, we can begin filling in some of the blank pages at the beginning of the universe's story. When did the first galaxies form? How massive were they? What types of stars and elements did they contain? The universe's story is our story, and with Webb, we can finally explore these questions, as well as uncover new ones we haven't even thought to ask.
There's a lot of hustle and bustle because the integration is in full process. Just look at NASA's James Webb Space Telescope. Its gold mirrors are definitely its most stunning feature. And yeah, that's real gold. Humans have a long history of searching for gold and using it in their most prized possessions. These mirrors weren't gilded to make them pretty. There isn't even all that much gold. About 5 men's wedding rings worth over the 18 mirrors. So I wanted to see for myself, why does it make sense to use a microscopic layer of gold on these mirrors? So our everyday mirrors tend to use silver or aluminum as their reflective material. One of the major differences between our earthly mirrors and these fancy optical mirrors is the position of the reflective material. Look at the side of this small mirror. It has the glass in the front and the metal coating behind it. That glass actually traps a tiny amount of light and creates what we call a ghosting effect. So the clearest reflection that we can actually have has the metal coating on the front. Dentists and hygienists also use front surface mirrors to get an accurate look at your teeth. The position of the reflective coating might make a sharp observation, but the kind of metal also matters too. There are a couple of reflective materials that really excel at reflecting infrared light, which is how Webb will observe. Aluminum reflects 85% of that wavelength of light, silver up to 95%, and gold up to 99% of all the infrared light that it encounters. But gold is special, and I can show you using the rings that I typically wear. This one is gold, and this one is made out of silver. And in the presence of the right chemicals, these two materials react differently. I think actually it's a little easier to show kind of all of this with this spoon. My mom surprised me by pulling out this whole tub of silver. Not tub, it came out of a box. So I'm able to demonstrate sort of on a bigger surface here how silver can react differently using an egg. Smush that in. Got nothing. We've got nothing. So what we have is a really fast reaction between the sulfur in the egg and the silver, and it creates a new thin layer on the spoon of silver sulfide. Silver might be great at reflecting infrared light, but it tarnishes so easily. Not only does gold reflect more infrared light, but it is also one of the most unreactive metals. It is too durable to oxidize and decay in space, and it is certainly Webb's best chance at seeing the cosmos.
We got together and looked at the very first diffraction-limited images that came out of the Webb telescope. And what we collectively saw as a group is we have the highest resolution infrared images taken from space ever. So you think of it as a blob on a picture, but it is extremely high resolution. We have exceeded every expectation. The telescope has performed better than the models said it should. We've even achieved, we talk about resolution and wavefront quality. We've done better in those regards than we thought we would do, and we're just thrilled to death. And to get there, we went through a process. Well, we did the segment identification, and then we formed the image array. And then once they were in the image array, we used this phase retrieval technology to position each of the mirror segments and the secondary mirror itself such that all the optical aberrations were effectively eliminated. We tilt the mirror segments to bring the light from each mirror so that it falls on top of each other at a common point in the middle of the detector. And we call that image stacking. And that concentrates all the light in a single place, but the segments themselves are not cooperating. They're not working together at that point. They're all their own individual telescope. And the next phase in the process is something we call coarse phasing. And that's where we adjust, literally it's the piston. It's the up and down motion of the mirror segments relative to each other. We control the piston of the segments so that they all come together in creating a complete monolithic primary mirror. If you know exactly what the shape of that telescope is, and you know exactly how the light is falling on your detector, it turns out that you can actually prove mathematically that that is enough information to tell you exactly what you need to do to that telescope to fix the alignment errors. And why do we know this? We know this because of something called a pupil imaging lens. And this allows us to take a picture of the primary mirror of the telescope. People have referred to it as a selfie. Right? Well, that's what it is actually. But that's really important mathematically. Now, there's a catch, however. Just because you know a solution to something exists does not automatically give you that solution. And that is the difficult part. That's what we have spent 20 years working out. It's highly mathematical, uses something called Fourier analysis, but that's what we do, is we tease out those solutions and we find what we need to do to each optical element to achieve perfection. We then turn to a different way of doing phase retrieval across the entire aperture of the telescope at the same time. And for that, we're not going to take the telescope out of focus. Instead, we have some lenses that are in one of the science instruments that we use to automatically create a defocused image. And we look at these images and taken as a whole, then we can tell the last little bit of alignment errors that are in the telescope that we need to fix. And that's what we accomplished today. We analyze those images and we apply the corrections leading to the diffraction limit of the perfect performance of the telescope. So there's only one thing left to do, and that's to see how well the telescope is aligned in the other science instruments. And we'll check the alignment there, and if necessary, then we'll apply a solution that optimizes for the entire telescope. We then periodically measure the alignment of the telescope and make corrections as necessary. I cannot wait to see what it discovers.
Well, first of all, the first evaluation images came in the middle of the night, but the team all came in and we gathered and we evaluated whether the camera was working well enough for us to proceed on with the alignment. And as we analyzed those first, photons, if you will, the team was pretty positive that the camera was working properly and the instrument was working properly. So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will, and we were very excited to find them. And the 18 spots were actually fairly close to each other, so really everything was very close to what was predicted. We've identified which of the 18 spots is which mirror. At this point, we even know which ones are from the wings, and it turns out one of the wings, you can actually see those 3 spots are a little farther over, and that's sort of what we expected. So we've identified all 18 spots, and the next step is to make an array of them, and then we're ready to start what we call global alignment, which is when each of those 18 spots will start to be aligned and focused. And that's sort of the last step before we take those 18 spots and put them on top of each other to start forming a single star going through the 18 separate telescopes. That's the work that will be starting soon. We also took a selfie of the primary mirror. We took an image of the primary mirror, and that helps us understand the alignment of the telescope, especially the primary mirror, to the camera itself and the instruments. There's actually a special lens in the near-infrared camera that you can put in, and it allows you to take a picture of the primary mirror itself. And in this particular case, one of the segments is pointing at a star, so that is the segment that lights up. But you can see the outline through the shadows of all 18 segments, and you also can see the outline of what's inside of the instrument itself, and we can see how well that primary mirror in the telescope is aligned to the instrument. And that gives us some initial confidence that the alignment looks good, and that's a good starting point for doing the alignment of the telescope. We have now gotten some data looking through focus, and we've been able to see that we don't see any surprises in the shapes of the mirrors that we're looking at. So far so good, but we do have a long way to go.
I'm gonna go this way where it looks like there's probably a gold sink, which would just be in a pool like this. I am on a quest for gold. Since NASA's James Webb Space Telescope has a microscopic layer on the mirrors, I want to know, where does gold really come from? Now, California is known for gold. It flows through the rivers, is embedded in the mountains. But is this really where gold originates? I know. This is a terrible example of what gold panning looks like. But at this point, I had already driven all the way to the San Gabriel Mountains, only to find that it is illegal to pan for gold because it is now a national monument. But it would just be our luck that we ran into Bill Schuster, whose family owns property for a really long time in the mountains, and he really showed me how to properly pan for gold.
See, the first thing you gotta know, you're gonna get wet, so don't worry about getting wet. Gold is so heavy, the ripples will catch it. Most people are so scared that they're gonna lose gold, and believe me, it will not go out. I already see two pieces, two big pieces. A little more angle. There you go.
So gold is incredibly rare. We can take all of the gold that we've ever mined or panned and stick it in 3 Olympic-sized pools. And the reason that gold is so rare is because it isn't even from Earth. It is extraterrestrial. As it turns out, finding gold's cosmic origins is a topic of hot debate. So I needed an expert to help me understand. And luckily, Mansi was in the area.
Do you like to wear gold?
Yeah, in fact, I actually got this gold ring in India myself.
Gold is one of the heaviest elements in the periodic table. In fact, if you peeked into its nucleus, it would be filled with 197 neutrons and protons. And until a few years ago, we had no idea where gold is made in the universe.
Scientists debated what energetic event could make heavy elements. Is the power of a supernova enough? Or does it need more?
That turns out to be very difficult to synthesize in any ordinary cosmic explosion. You need a very special explosion that can actually synthesize heavy elements like gold by our process.
Now, the R process is one of the ways to make heavy elements like gold. It is another way to say rapid neutron capture process, and it happens in the matter of a couple of seconds.
On August 17th, 2017, when the 2 neutron stars merged, that's when we saw the hallmark infrared signature for the very first time.
Now, this neutron star merger was and is still a big deal. It's the only time scientists have witnessed and measured the R process in action. And up until then, it was all theoretical.
Let's begin with 2 neutron stars spiraling towards each other and then merging to give birth to a black hole. This is where we think we saw for the very first time the gold being synthesized. You have an abundant supply of free neutrons. So when these neutrons are flying out, they are able to bind to each other, join together, and undergo rapid capture. And this rapid capture gives you a slew of heavy elements all the way up to gold.
What I learned is that, like all heavy elements on Earth, gold has been here since Earth was formed. It was floating around in the gas and dust that formed our sun and all the planets in our solar system. But gold is heavy. Much of what we find comes up through many veins running through our crust. That's why we often find gold alongside rivers and volcanoes. But what is even more poetic, we are using an element forged in the death of stars to investigate the dawn of our universe.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1,000,000 miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built WEBB to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you. Shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our high-gain antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, or approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton.
70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy a side. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind WEBB is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, WEBB is in its final configuration, but we're not done yet.
After 47 deployments and accomplishing the hardest spacecraft unfolding NASA has ever done, WEBB still won't be ready for science.
While the instruments cool, we'll control motors behind each of WEBB's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, WEBB will be ready to explore the cosmos.
This is it. I am standing at the place where the beryllium was mined for the James Webb Space Telescope. Let's take a step back. I traveled just south of Salt Lake City to a town called Delta, Utah. Well, here we are. What is it? 5:30 in the morning. And then back on the road the next morning as the sun rose up to meet the beryllium miners, all in my quest to find out. So Utah is home to many valuable materials: copper, magnesium, uranium, gold, and silver. But most of the world's beryllium is mined here. And engineers chose beryllium for Webb's mirrors because it is lightweight, it is strong, and it is dimensionally stable. So that means that it is not going to warp when operating at really, really cold temperatures. What is even here? As we were driving down into the pit, I learned that we were in fact driving on the beryllium. This rock looks nothing like metal. Where is the beryllium? How does this turn into this? I, of course, needed to speak to an expert, and he came in the form of the VP of Operations, Greg Gregory.
So we're actually standing right on top of the beryllium ore seam. Beryllium is in a volcanic ash dust. It was hydrothermally deposited millions of years ago and then covered by volcanic rock. We have to remove the volcanic rock on top of the ore seam, and then we use a scraper and a bulldozer to extract the ore that we're standing on top of. "90% of the beryllium that was mined in the world last year came from this deposit."
Let me clue you into how rare this metal is. This area has most of the world's known beryllium, but the highest concentration is only through a 10-foot tall diagonal ribbon well below the surface of the ground.
The ore concentration is 0.25% beryllium. So that means that in a ton of ore, there's about 5 pounds of beryllium. So to get to this point, we had to remove 400 feet of rock to get to the ore seam.
Once the ore is extracted, it goes through a bunch of processing to extract the pure beryllium. Then the powder beryllium is pressed into a block, ready for machining. Webb's mirrors started out as solid 5-foot tall, 5-foot wide, and 2-inch thick blocks of beryllium. But in order to machine those blocks, millions of pounds of rock were removed. It comes to about 4 tons of rock for every pound of beryllium. That is a lot of work for one remarkable metal. So in the heat of the summer, these visors really can make a difference. And the Webb telescope uses the same principle to block the heat of the sun and even what bounces off the Earth and the moon. And just like my car's visor, the telescope's sunshield unfolds, but its 5 layers are a little bit thinner. This thin material is called kapton, and it makes the sunshield of NASA's James Webb Space Telescope. So what is this strange kapton? It's a combination of carbon, nitrogen, oxygen, and hydrogen, but its primary element is carbon. It is only 1/1000th of an inch thick. That's a quarter of the thickness of the thinnest hair you can find. The 5 layers of this reflective material will keep Webb cool. It'll block the light of the Earth and Moon and our very bright sun. Each layer is the size of a tennis court. The sunshield happens to be one of the most complicated parts of this telescope. That's because it has to be packed perfectly like a parachute to fit into the rocket, and then it has to unfold in space. Let's get a better idea of how good this kapton is at reflecting heat. I asked our resident expert in all things MIDI to make me a 3-layered model of the sunshield using the same kapton that's on Webb. And then we put this tiny light bulb to mimic the heat source that would be the sun, Earth, or moon. See? You can see the heat reflecting off the bottom layer. And then the kapton worked so well that none of the heat is detected at the top of the model. The sunshield is capable of dissipating 500 degrees Fahrenheit over the 5 layers, and that heat radiates out from each of the layers. That's why each layer gets a little smaller from the bottom to the top. NASA actually uses kapton for most of its missions. It not only shields or contains heat, it also because it is electrically conductive. All that shifting kapton of the unfolding sunshield, it could create static electricity. But that charge won't build up on the kapton and jump to the observatory's super sensitive electronics. And then kapton stability over a wide range of temperatures is why it's also a great choice. This modified version, called Mylar, might even help you if you get cold.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb telescope will find.
I believe that the Webb's telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space. Hello, my name is Gabriel. I am from Romania. This is how I imagine space.
Hello everyone, good morning. This is a drawing of distant galaxy that can be seen by James Webb Space Telescope.
Hi, my name is Anastasia, and this is what I drew, what I think the telescope will look like, what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
Beryllium is one of the many elements that people mine, and that's how we obtained it for NASA's James Webb Space Telescope. It exists in many rocks, just in tiny quantities. We collected rocks with the highest amounts of beryllium, crushed them up, put them through many chemical processes, and these rocks only have 0.25% beryllium. To explain beryllium's rare beginnings, we need to talk about the cosmic origins of most elements. When a massive star is forming, it's mostly two elements, hydrogen and some helium. Over time and pressure, temperature builds up in the core, so much that some of the hydrogen atoms fuse, creating helium and officially bringing the star to life. That fusion creates a tremendous amount of energy and is literally what fuels the star and makes the light we see. That star will eventually run out of hydrogen, and the helium atoms start to fuse, creating even larger atoms. That keeps happening, and we get larger and larger elements. These new elements are denser than the former hydrogen and helium, and they cause the star to contract and get even hotter. But that all stops with iron. There isn't enough energy to fuse something more substantial, so once there's too much iron in a star, which means that there's no fuel, it dies, but not without a dramatic exit. The core collapses under the pressure, and all of the atoms knock around into one another, which causes a sort of shockwave, and it explodes into a supernova. This is the energy needed to create heavier elements. This is when more than half of the elements in the periodic table are made. But beryllium is not in that mix. Look at where it is on the table. It has an atomic mass of 4, much smaller than the heavy new elements. So why isn't beryllium made when the other small elements were? It's just too unstable. If, during the chaos of a supernova, a cosmic ray hits one of these newly formed larger elements, a special reaction happens. This is called cosmic ray spallation. This ray hits a molecule and it bursts into smaller particles. The pieces can continue splitting into smaller parts, some of which turn into beryllium. It takes a supernova and a cosmic ray to reduce a large element into what could be a variety of combinations and sizes to create beryllium. No wonder it's so rare. What is the backbone of life? That super stable central element to all organic molecules, and happens to be the 4th most abundant element in the universe? It's carbon. Carbon has once again proven its worth in the form of the Webb telescope backplane. Now this structure holds 2.5 tons of science instruments, those beautiful gold mirrors, and it's made out of a carbon composite. You might be more familiar with graphite, a crystalline form of carbon. Graphite is really everywhere. It's in airplanes, bikes, our tripods. It's great because it's strong and super lightweight, just like Webb's backbone. Just look at the difference in weight between the aluminum and the same amount of the backplane material. The backplane isn't entirely all carbon. A durable polymer binds those carbon fibers together with a plasticky-like glue, and then they are baked in an autoclave like this. Alright, so I think we should probably go just maybe in front of the Pathfinder. Once out in the cold vacuum of space, this backplane will shift because all materials change with temperature. But this structure is aligned so that it's perfect once it does shift into space and cool down. That happens to only be 1/10,000th the diameter of a hair. So frickin' cool. It is pretty fitting that these are called cosmic flames. These packets are nothing but a bunch of different elements. So lithium makes red, barium makes green, and so on. And then they burn in these really pretty colors. Burning chemicals is a legitimate way to find out what something is. Chemists call it the burn test. All elements actually give off a signature when they are put into an excited state. Here, we are witnessing what happens in a fire. The James Webb Space Telescope will be able to read the same signatures from unknown stars and planets. I've been taking you through different elements that are built into the Webb telescope. Gold reflects infrared well and will not corrode. Beryllium is lightweight. Silicon is a tried and true semiconductor. Isn't it just poetic that Webb is designed to detect elements? Webb uses a device called a spectrograph. It works by splitting the light with a prism. We can tell what element we see based on the pattern from the light through the prism. Every element releases light at a different wavelength, and when that light is split by the prism, black bands appear due to the transition between the energy states. These are called absorption lines. The lines always appear in the same part of the rainbow, which is why we call them atomic fingerprints. I've made my own simple spectrograph to give you an idea about what Webb sees. And the object that makes this whole thing work is a relic of technology. It's a CD. CDs and DVDs use the same principle as another ancient device, the record. They use tiny tracks or bumps to convey the information. Records use a 3D representation of the sound, and a CD uses raised binary points. The point is that the discs have a very fine groove pattern that physically splits light. That's why they have a rainbow or iridescent color. Webb spectrograph also uses fine grooves to split light. The near-infrared spectrograph, called NIRSpec, is designed to take spectra from up to 100 objects at once. You don't need to go all the way to space to see the spectra from different objects. My little homemade spectrometer can tell me the primary element that different light sources use. Neon lights get their name because the lights use neon gases to get their color. Actually, the neon only refers to one color. These types of lights use other gases to make more colors. Let me show you the full spectrum of colors that we can see based on a combination of these different elements. Webb spectra really give more information than just the elemental makeup. They can also tell astronomers about the temperature, the mass, speed, and density of the objects as well. All elements have a cosmic start. Smaller elements are forged in the heat and pressure of a star. Anything larger than iron needs a powerful force of a supernova or colliding neutron stars. These elements may stay as dust clouds or eventually coalesce into asteroids or planets, characterized by their original elemental makeup. The spectra Webb will see not only tells us what elements we're looking at, but the warmth and the density of the bodies as well. So we might detect some distant biosignatures. Webb's build might use a scarce element like beryllium for its mirrors, but will this cosmically occasional element help us find something far rarer, like gaseous carbon, oxygen, or nitrogen? Can we determine where to find the building blocks of life in other worlds? In a specialized building like this, NASA built a new machine for science. The James Webb Space Telescope is a complex collection of scientific instruments designed to tackle some of the biggest questions in astrophysics. Webb has 4 instruments contained within the Integrated Science Instrument Module, or ISIM, located directly behind the primary mirror. They are all designed to observe an infrared light, which is invisible to human eyes. Infrared is a longer wavelength of light located on the electromagnetic spectrum, just beyond light human eyes can see. We feel infrared light as heat. Each of the instruments play a different scientific role. The near-infrared camera, or NIRCam, is the main imaging system. NIRCam will look back in time to study the formation of the earliest stars and galaxies. One aspect of its design includes the ability to block light from a bright object, so much that a much dimmer object nearby might be observed. This means that in addition to looking at distant objects from the earliest days of the universe, scientists hope to study aspects of planets orbiting nearby stars. The NIRCam instrument also plays a key role in the process of aligning Webb's 18 primary mirrors, its secondary mirror, and its fine steering mirror using a clever technique called wavefront sensing and control. One of the best ways to find out new information about distant objects is through analysis of the light those objects emit. The Near-Infrared Spectrograph, or NIRSpec, will collect spectral information about distant objects in order to determine their composition, temperature, velocities, and mass. To do this, NIRSpec will employ a unique technology called a micro-shutter array. It's an extraordinary collection of mechanical shutters, each barely wider than the thickness of a human hair, that can simultaneously collect high-resolution data from up to 100 distant objects. Different wavelengths of light present different information, and each of Webb's scientific instruments pursues different slices within the infrared spectrum. The mid-infrared instrument, or MIRI, will look at wavelengths of light that are a little longer than the other instruments will observe. Not only will this enable extraordinary images, but it will also allow scientists to search for planets around distant stars, dust warmed by starlight in protoplanetary disks, and comets and asteroids in our own solar neighborhood. MIRI is the coldest instrument on Webb, operating at just 6 degrees Celsius or 11 degrees Fahrenheit above absolute zero. The fourth part of Webb's instrument suite is 2 instruments. The near-infrared imager and slitless spectrograph, working in concert with the fine guidance sensor, will look for ancient light in the universe and information about planets around distant stars. The fine guidance sensor helps keep Webb pointed and perfectly steady during all observations. Together, these instruments and the technologies that will enable them will make up one of the most complex and ambitious undertakings in the history of humanity. This is NASA's James Webb Space Telescope.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal. have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
Good morning. Good morning, everyone. We are live, and this is it. Today is the day we have all been waiting for, so let's get excited. I think you all could do a little better than that. Let me hear you again. There you go. There you go. We are less than an hour away from the moment we have been working toward for 2 decades, the reveal of the first science images from the James Webb Space Telescope. Now that's worthy of another round of applause. For the past 6 months, the Webb team worked tirelessly to get the telescope ready for this very moment. In those 6 months, the team unfurled Webb's giant sun shield, deployed and perfectly aligned its gold-coated mirrors, and cooled the instruments to their near absolute zero operating temperatures. And can you believe all of that was done while navigating the telescope to its ideal position 1 million miles away from Earth? Come on, guys. To everyone in this room, staff, supporters, scientists, and engineers, and all the other professions that contributed to us being here today, welcome and thank you. It may have taken us more than 20 years to get here, but after you see these images, you'll know that all that time and hard work was well worth it. Congratulations. I'm Michelle Jones. I'm the Chief of Communications here at NASA Goddard. And to celebrate this incredible moment in history, some of the lead Webb project members, elected officials, and heads of agencies from around the world want to personally thank you, the team, the people who made the impossible possible. I see a lot of familiar faces in the room who have contributed to the success of the Webb Space Telescope. This was a partnership between NASA, international, corporate, and university partners. And many of those partners are here with us today. I understand we have representatives from the European Space Agency, the Canadian Space Agency, Ariane Space, Lockheed Martin, and the Space Telescope Science Institute. I'd also like to acknowledge the Greenbelt City Council and the Maryland General Assembly. It's a true pleasure to have all of you here for this historic moment. To start things off, we have my boss, Goddard Center Director Dennis Andrusic, who presided during the final years and all the way through launch. Dennis, come on up.
Wow. Good morning, everybody. What do you think about the cheerleaders coming into the building? Oh, my goodness. Thank you all. That was just absolutely awesome. You know, before I get into some of the prepared remarks, I just want to mention that, you know, there's an old proverb that says, may you live in interesting times. And I'll tell you what, my friends, these are interesting times. The images you're about to see today will blow you away. They are just so spectacular. Things that I had never even dreamed that we'd be able to see are here before us. And I'll tell you what, it has just been a fantastic, fantastic journey that's gotten us to where we are today. By the way, if you're seeing my name in writing, it looks so much worse than it is in reality. The last name is pronounced like the boy's name Andrew, who is sick. You run it together, you have Andrewsic. It's that simple. It looks so much worse when you see the spelling. So anyway, I want to thank everyone for joining us today, whether it's in person, on NASA TV, or in any other media outlet that you've chosen to be able to view today's events. And speaking of viewing the events of today, we had the distinct honor of Administrator Nelson, Jane Rigby, Thomas Zerbuchen, Greg Robinson, Nancy Levison. Where's Thomas? I know he's here. There he is, Thomas. To present some of the images last night. The President and the Vice President were so excited with the great news and what they were seeing that the President actually took the opportunity to thank Jane Rigby, the scientist we'll be hearing from at 10:30, by calling her mother and leaving a voicemail message about what a great deal her daughter was doing to improve our knowledge of the universe. And that was such a touching thing. It really meant a lot to me. It meant a lot to Jane. And I think that talks about what the administration feels about NASA, that he was willing to take that time. And I know I'm about out of time. So let me get back into the program. Again, pleased that we have not just some of the dignitaries that Michelle mentioned. We also have Northrop Grumman, Scott Willoughby's here. So thank you all for coming. We also have the Webb family in the audience. Jim and Barb Webb are right over here. Raise your hands. And their guest, Kaleem. I've worked with Kaleem at NASA headquarters. You'd think I would be able to get this right. Kaleem Oluche, thank you for joining us today. Well, the entire NASA, James Webb Space Telescope has been 2.5 decades in the making. And as the director of this fabulous NASA center, I'm extremely proud of all of the employees, as this entire project has been one of the largest collective efforts in our center's history. And I'd like to assure you that it has been truly a collective success. We've had many engineers and scientists supporting the James Webb Space Telescope. And it is also becoming just a scientific, it's been an engineering marvel, it's about to become a scientific marvel. But we haven't done it alone. As Michelle mentioned, we've been doing it with partners, and it's those partners that have helped make Webb successful. Across the NASA community, Johnson and JPL, Kennedy, and other centers, with industry, as was previously mentioned, and I'm over time, so I'll start to shorten on that. But I will just say, I'm up before you as a kind of a NASA bureaucrat, as the Goddard Center director, but at heart, I am still a NASA geek, still an engineer. A launch never gets old, and the science gets even better with each passing mission. Thank you all for coming, and let's get on to the next presenters.
Thank you, Dennis. A great project like Webb takes great leadership, and today we have someone who knows what it means to be a leader. Not only was he a United States Senator, he was also a payload specialist on the Space Shuttle Mission 61C in 1986. Everyone, please put your hands together for NASA Administrator Bill Nelson.
I didn't know I was coming to a pep rally today. But that's all the better. And you've got a lot to be rallying for. And you should have seen the president and the vice president last night. I mean, they were like kids. And they asked just a million questions about a lot of things. And this is all because of you. It's all because of that team that is out there, that over decades, this project has come to fruition. It tells us something about NASA's unmatched ingenuity, where we make the impossible possible. And it's not going to stop, because this telescope's going to keep, like the Energizer Bunny, because of the Ariane rocket putting it on a perfect course. And so it's got fuel for 20 years now. And if that were not enough, this fall, we're going to launch the largest rocket ever, and we're going back to the moon in preparation, and we're going to Mars. Now, this morning, folks across this planet are going to see the images captured by this telescope. And every image is a new discovery, and each will give humanity a view of the universe that we've never seen before. You're going to see the formation of stars. You're going to see devouring black holes. It's going to reveal all of this. This telescope, because of infrared, is going to be able to penetrate through the dust clouds, and it's going to see light from faraway corners of this universe. Now get this, because of a NASA scientist here at Goddard who got the Nobel Prize, Dr. Mather, he determined that the universe was 13.8 billion years. Okay, this telescope, the images you're going to see today, exceed looking back 13 billion years. And then we will look back to as far as 13.5 billion years. Think about that. The speed of light is 186,000 miles per second. And that light has been traveling for 13.5 billion years, only about a few 100 million years after the beginning. That's the threshold that we are crossing. And it's an example of what NASA can achieve. But we don't do it alone. We do it with industry. We do it internationally. In this specific case, our partners, the European Space Agency and the Canadian Space Agency. And by the way, we are now going to be determining things that we don't even know what the questions are that we ought to ask. And so it's one of these great engineering feats, not just for us, but for humanity, for planet Earth, for the citizens of planet Earth. And so there have been setbacks along the way, but because of the perseverance, here we are today. And it's these engineers and scientists and innovators that have poured their life's passion into this work, and it's now come to fruition. And it's progress like this that drives us forward, and it gives us inspiration. Our rockets run on fuel, but inspiration is the fuel that drives NASA, and indeed drives humanity. So this novel innovation that made WEBB possible is exactly why NASA and why humanity continues to push the envelope, as the test pilots say. Push the edge of the envelope. NASA's no stranger to first steps, and as we enter this new era of space flight and discovery, we need to be bold. We have to take risk, but the reward is worth the risk. And this is proof of that. It represents the largest international space science program. It collaborates internationally. Now, Michelle, I'm going to turn it back over to you to share messages from our international partners.
Thank you so much, Administrator. The mission would not be as successful as it is today without the teamwork and contributions from our mission partners, the European Space Agency and the Canadian Space Agency. We are pleased to share with you a special video message from ESA's Director General, Dr. Joseph Aschbacher, and their Director of Science, Gunther Hasinga.
The James Webb Space Telescope is such a fantastic opportunity. It's a once-in-a-lifetime opportunity which we have here, and we are so excited, both Günther and myself, on this first data release. It will really change the understanding of our universe. But before I hand over to Günther, just one word. This is also a symbol of international cooperation. The partnership we have with NASA is outstanding. It's really exciting but really fantastic, and also with CSA, the Canadian Space Agency, and this is more than science, it's also a symbol of international partnership. But Günther, a bit more about the James Webb Space Telescope, what this means.
Thank you very much, Joseph. Yeah, this is the day that we have all been waiting for so long, and now it's happening. You know, James Webb is a fantastic machine, and its infrared eyes are 3 times sharper than the Hubble Space Telescope, and they're 100 times more sensitive. So with these infrared eyes, you can peer into dark, obscured regions in our universe. You can look at the very first phases of the universe after the Big Bang. You can look at planets in our own solar system and around other stars. And it is indeed a once-in-a-lifetime chance, almost like the moon landing for astronomy. And it will actually feed many, many careers. It has already shaped a whole new generation of scientists, and this will continue. It's a masterpiece for international cooperation, as Joseph had said. We are working with NASA and the Canadian Space Agency, and this is actually in tradition to Hubble, to Cassini-Huygens, where NASA is leading and ESA is partnering. But we are also opposite, having missions where ESA is leading and NASA is partnering, like for instance, WEBB Colombo, JUICE, the Euclid spacecraft, and so on. So ESA, the science program, is actually enabling the European scientists to lead in a number of discrete fields, and one of the important fields is, for instance, astrometry with Gaia, where we are really having a leadership position. And now James Webb. James Webb will answer a lot of questions, even some questions which we do not even know about yet.
Talking of NASA and what we do here, I mean, of course, we have many contributions in the James Webb Space Telescope. We have instruments, 1.5 instruments that we are providing. We have a science team that is working with NASA and the other partners. But one event was very special, and which was the launch of the James Webb on Christmas Day from Kourou on Ariane 5, and this was really a very important event for us. Not only is NASA entrusting this James Webb Space Telescope to us, of ESA, but also the insertion of the James Webb Space Telescope into orbit was so precise that scientists have a much longer lifetime of the James Webb Space Telescope, actually doubled the lifetime. And this is really fantastic, because this really shows also that our space transportation technology, in addition to the science technology, is just outstanding, and very proud and very happy about that.
So go Webb, go.
Go Webb, go.
Our next video is from the Canadian Space Agency, and this is from the President, Lisa Campbell.
Hello, everyone. Today marks a major milestone in the Webb Space Telescope mission, as we're about to witness Webb's unprecedented view of the universe. Webb promises to be the next giant leap in space astronomy. We're confident that the observatory will exceed expectations. bold, important missions like this are only possible through strong international collaboration. This one-of-a-kind mission is a testament to what we can achieve when we work together, and WEBB is truly a global effort. Congratulations to our partners, NASA and the European Space Agency. Thousands of brilliant minds around the world are behind the design, launch, and operation of this complex space telescope. The Canadian Space Agency is honored to be part of WEBB. Canadian specialists across industry and academia united their efforts to provide our instruments. Canada's fine guidance sensor will keep WEBB perfectly aligned during all of its observations. And the nearest instrument will observe the earliest galaxies and perform in-depth analysis of the most promising exoplanets. For the science community in Canada and across the world, having access to data collected by WEBB will lead to unexpected discoveries. WEBB will not only help us work out long-awaited answers to age-old questions, it will also inspire new, cutting-edge research that leads the way to our cosmic origins. Congratulations to all who made these imminent discoveries possible.
If it wasn't for years of steadfast congressional support, this extraordinary project wouldn't have been able to get off the ground. So it's fitting that we have representatives from Team Merlin joining us. And let me clarify, these gentlemen are not just representatives. They are friends of NASA Goddard. Please join me in welcoming Maryland's 5th Congressional District Majority Leader of the United States House of Representatives, Steny Hoyer, Senator Ben Cardin, Senator Chris Van Hollen, and the Representative Trone from Maryland's, David Trone from Maryland's 6th Congressional District.
Thank you very much, Michelle. It's good to be here with astronaut Nelson. So sorry you're sick, Andrew. All of us have fought. Hubble was at risk. Goddard was at risk. Webb was at risk. This day gives a new meaning to as far as the eye can see. The vision of the world is greater today than it was yesterday. And it will redound to the benefit of all the peoples of this earth. What a wonderful day. I want all of you who have worked on this project to stand up. Stand up. All right, you're using our time. America thanks you, and the world community thanks you. Our time is short. Let me yield to the senior senator from Maryland, my dear friend Ben Cardin, who has fought so hard, along with Barbara Mikulski, to make this day happen.
Thank you, Steny. First, I'm very excited. This event is out of this world. How many times have I said that? I can really mean it this time. We are so proud of the role that Maryland has played. You heard Michelle mention all the different organizations and government agencies and institutions and private. So many of them are located in Maryland. Steny already acknowledged the incredible workforce. We know the 20th century will be known for space exploration by Neil Armstrong's steps on the moon. The 21st century will be led by the work done by the James Webb Telescope. This is an incredible moment. It's now back to the future, and we're going to be part of it.
Chris Van Hollen.
Well, it's great to be back here at Goddard, and thank all of you who have been part of this team. You know you've made it when you have your own cheerleading squad. As somebody who was briefly a physics major but bailed out after quantum mechanics, I want to thank all the scientists and the engineers and everybody who stuck with it to bring us to this brilliant day. This is a great day for humanity, peering further back into time, deeper into our universe, answering some questions that are fundamental to who we are and how we got here. Thank all of you from around the world, because this was an international endeavor. And while there were bumps along the way, once the launch happened, everything had to go perfectly. And it did because of all of you. I do want to say Maryland is proud, at least on this day, to be the center of the universe. And thank you. Thank you to Goddard. Thank you to the Space Telescope. And we're going to continue to invest in this mission and so many others, along with my friend David Trone, who's also on the Appropriations Committee in the House of Representatives.
So thank you all very much for this incredible moment in scientific history, and space exploration is what connects us all. And that's what's so fantastic about it. As the saying goes, if you want to go fast, go alone. But if you want to go far, go together. And this team has gone together, so thank you and congrats.
This telescope is by far the largest science endeavor NASA has ever undertaken, and it required a huge network of companies from around the world to build it. Northrop Grumman led that team and helped NASA and its European and Canadian partners to achieve the success we see today. To help celebrate that success, we have a special message from Northrop Grumman CEO, Kathy Warden.
On behalf of the entire Northrop Grumman team, congratulations to the space and science communities around the world on what will be the first of many exciting and truly historic Webb missions to come. These incredible images, never before seen by humankind, carry us further than we've ever gone before, and we're just getting started. The extraordinary telescope represents a new era in human discovery, and equally important, it represents the engineers, technicians, scientists, and the countless other teams that have come together to define possible. Our work, the technology we've created, and the images it captures will inspire the next generation of thinkers, innovators, and problem solvers. This is the true legacy of Webb. Thank you, and congratulations.
As I said before, it took companies from around the world to get Webb in space. Right now, we're going to hear from the CEO of Ariane Space, Stefan Israel, with a message he would like to share with you.
Webb, an incredible adventure we at Ariane Space were honored to be part of. A 20 years collective challenge that finally brought us together in Kourou with Dr. Z, Greg Robinson, Joseph Ashbacher, Daniel Nunschwander, and Philippe Baptiste on a Christmas morning we'll never forget. 27 minutes and 11 seconds, which will be among the most important of our lives. After a perfect launch with our Ariane 5, which has doubled the Webb lifespan, and such a long journey, we are now on the verge of discovering images that will revolutionize our understanding of the universe. A game changer created by the collective work of passionate and brilliant people from USA, Europe, and Canada. To these dedicated teams, I want to say thank you. Thank you for your trust in Ariane that made this incredible adventure possible. Go Webb.
All right, guys. We're only a few minutes away from seeing the first images, but before that, I would be remiss if we didn't take an opportunity to let those that led the way have an opportunity to say a few things. We have the Webb Program Director, Greg Robinson, Northrop Grumman's Webb Program Manager, Scott Willoughby, and last but certainly not least, the Webb Project Manager, Bill Oakes.
get teleprompter, so I'll just wing it. So I will say, when I came up the stairs, by the time I got to the top, I wanted to throw off the jacket and run out to the 50-yard line. So thank you for that welcome. I don't know what I would have done when I got there. So who did not see that image yesterday? Well, as the old saying goes, you ain't seen nothing yet. Just hang around a little bit longer. I just want to do a couple of quick thank yous. You've heard from most of them. Thanks to the entire team, certainly the Goddard-led project team, Northrop Space Telescope Science Institute, and our international partners. Also, I want to thank, I call it the ninth floor, the NASA administrator and his team, and the White House and Congress. All of us are part of this, and when I say team, I mean everyone from beginning to end. And we all had to be aligned to make this happen, as Thomas often reminds me. So thanks for all of that. I want to do a couple of special thanks. Special thanks to Scott Willoughby for leading the team out at Northrop, Bill Oakes for leading the overall team, and I know both of them will say more about their teams and the capability of the spacecraft. And a special thank you to Thomas. I often say twisting both of my arms to get me to take over this, to be part of this incredibly smart and resilient team. So thank you, and thanks for coming.
It's humbling to be here at Goddard. My team from Northrop Grumman spent a lot of time here and at many of the NASA centers and other places around this country. But this is where relationships were forged, and it's relationships that built the James Webb Space Telescope. And it's been a common theme here for a purpose, right? The international relationships, the government industry relationships, but the relationships that are dearest to me are the ones that took place on the floors of the high bays and in the meeting rooms and debating hard problems. And sometimes those answers weren't certain as much as engineering wants to be, and you're using judgment and people's guts and brilliance to make decisions that led to perfection. And what Bill and I did throughout all of this was really kind of singular. It was giving that team power. And I just kind of leave with a phrase that I used back when we were getting into the final build of Webb, when people were putting this together, that every human who touched this for the last time should know you get that privilege. And you get to bring your pride to the floor to do that. But you have to check your ego, because pride is powerful. But somebody's going to ask you a question, did you do it right? And somebody's going to look at a picture when you did it and see, was it right? And somebody else was going to review that and stamp that it was right. And every single person mattered in that. And in the end, it was perfect. So thank you. And working with Bill was really a relationship that's going to last a lifetime, over a decade. I think we broke the record for industry-government partnership. We're not supposed to be together for 10 years, but we were. Bill.
Thank you. Well, I guess I'm the cleanup, typical job for a project manager. First, just a little update on the observatory. Over the weekend, we finished the last commissioning activity, so we are officially done with commissioning. We have an observatory that is in excellent shape, that either meets or exceeds requirements. And as mentioned earlier, we have 20+ years of fuel on board. And finally, we have actually started our first year of normal science operations, and that is now in full swing. So, as the old saying goes, it takes a village. Well, with Webb, it actually took a town of about 20,000 people over a period of 20+ years across 29 US states and 14 countries. And even more, if you add to that number the family, the friends, the significant others, etc., who supported Webb, they are also part of that Webb team. You cannot really single out any one person for the success of Webb, but everyone here should know that as you see each image, you are a part of that image. We would not be successful without your contributions to the Webb program. When I see these images, I see four things. I see dedication. And I have never seen dedication on this project like I have seen on any other mission I have worked. I see personal sacrifice of so many individuals that my heart is just overwhelmed with pride for the folks on this program. Finally, also I see passion. I've never seen the passion for this program, and that's what helps with the first two things I mentioned. Finally, I just see the faces of all our individuals who have worked on this program, both the past and the present. And neither myself nor NASA will ever be able to thank these persons enough. And finally, on a more personal note, the WEBB team itself, we are all going to be bonded for the rest of our lives by the WEBB experience. And I have to thank you for the privilege that you have allowed me to be part of that experience. Thank you.
Thanks. All right. Thank you and congratulations, gentlemen. And congratulations to all of you once again. Today, we celebrate you and your achievements. Now listen, I'm sure you're excited to see exactly what WEBB will show us. So here's the plan. We're going to take a quick break, but as you all at home can see the countdown clock, we're literally minutes away from the reveal. Are you all still excited? It has been my absolute pleasure spending this time with you. We can't wait to share what humankind is capable of, and we are just getting started. Let's enjoy this journey. Now, on the count of 3, I want you all to scream, "Go WEBB." 1, 2, 3. Go WEBB!
Skywatchers, this is it. This is the day we get the first science images back from the James Webb Space Telescope, and you've got a front row seat to the cosmos. I'm Michelle Thaller, your host for what can only be described as a celebration for everyone on Earth. So think about this. Light from the earliest days of the universe has been traveling to us for billions of years. Just over the last few weeks, we've captured some of that light with a telescope that sees the universe in an entirely new way. And today we share the very first results. So longtime space fans are going to know who this is. This is Dr. John Mather. He's the senior project scientist for the Webb telescope and a Nobel Prize winner. And John, I couldn't be happier to be here with you today.
Thank you. It's a thrill to be here for this very special day.
How are you feeling?
I am thrilled and I'm relieved because you know when you start something this big, you know there's always a possibility it might not work. It did work. We are so proud.
And you've been on this project for a very long time, right?
Yeah, started in 1995. We had just finished measuring the Big Bang. We measured it with a Cosmic Background Explorer satellite that we built right here at Goddard. And we measured the spectrum. We measured there are hot and cold spots in the Big Bang. So we said, now we know it all, how it all got started. But then what happened after that? So then I got a call from NASA headquarters. Would I like to work on this new telescope that's going to help answer those questions? What happened after the Big Bang? How did the galaxies grow? How did the first black holes grow? What happened all the way from there to here? So this is our time machine, and I just wanted to be part of it. I am so thrilled that we got a chance to do it.
One of the things that I remember you saying, and this is kind of amazing, that after you win the Nobel Prize, you thought that this mission was the most important thing to work on.
Absolutely. It's the next question. After you know how it started, what happened then? And you know, suddenly we now have the technology to do it. We didn't have 50 years ago. We didn't have the technology 25 years ago, even when we started this. We had to invent things along the way, so we did that, and here it is.
Well, thank you. We'll be back to you in just a moment. So at the moment, we're going to talk about the way that Webb is a completely new way to explore the universe. So today, the mission releases its first science images and gives wings to the dreams of so many people who worked so hard for so long to make this possible. For everyone on Earth, this is your telescope. This is the largest, most powerful observatory ever put into space. It's the product of thousands of people working for more than 2 decades. This is a mission that's singularly focused on the biggest questions in science. So the following phrase is often used too easily, but today actually does mark the dawn of a new era. Today, the Webb mission is open for scientific business, and this is just the beginning. The best is yet to come. So, John, one of the things you told me about is that you really want to make sure there are some people that get thanked, people that put a huge amount of effort into this.
Absolutely. Our current project manager, Bill Oakes, took the project from a time of trouble when we didn't exactly know how we were going to get this to work and got it all the way to the end. Here it is working, and it's because of Bill made this worldwide team. 20,000 people around the world were involved in making this thing all work, and Bill has been there every day making sure that it would happen. So other special person is Senator Barbara Mikulski. She saved our telescope, and she saved the telescope before us. She made sure after the Hubble telescope was launched and it was not in focus that we would go up and fix it. She made sure that happened. When the Webb telescope needed more resources, she made sure we could get that. So Barbara, we thank you.
Well, it is such an honor to be with you, Jay. I mean, it's been a pleasure to be working with you through this whole thing. Thank you so much. Congratulations, and go Webb.
Thank you.
So this broadcast, much like every part of this mission, is a partnership. On our journey to explore distant places in space, we've been joined by intrepid travelers from around the globe. We have so many extraordinary collaborators. So let's check in with our partners who will be sharing the stage with us today as we reveal Webb's 5 first science images. From the European Space Agency, I'm joined by Katie Haswell in Darmstadt, Germany. Katie. I see Katie in the background there. Also joining us from the Canadian Space Agency in Montreal, we have Natalie Willette and Sarah Gallagher. Bonjour. I see Katie in the background there. See the waving too. And so naturally, we're also going to be visiting the nerve center of this mission, the Space Telescope Science Institute on the campus of Johns Hopkins University in Baltimore, Maryland. And there we have Alex Lockwood and Carl Gordon, and they're going to give us updates and more. Good morning. Great. So we'll be back with our international partners shortly, where they'll each reveal one of the new images. But today we're also going to be joined by millions of science fans from around the world. Many are gathered at watch parties just for this event. So here we are really going international. So I'm beginning with Bhopal, India. Do we have a signal from Bhopal? Yes. Excellent. Welcome to NASA. Hello, everybody there. Wonderful to be talking to you today, all the way in India. We'll be back to them later, yes? Great to wave to you. Hi, wonderful. And we also have a warm welcome now in Portland, Oregon. So we have the feed from Portland. A bit dark, but I see everybody there. Hello, Portland. They're in an auditorium, I see. Okay, next we're going to go off to Milan, Italy. So afternoon in Italy. Do we have the feed from Italy? I guess we have a screen from Italy. And next we're going to go to Rutland, Vermont. So is this Vermont? Hello, Vermont. Hi, everybody. Nice to see you. Thank you for being part of this today. Okay, going even a little bit further afield, we have Netanya, Israel. Hello. Hello, Israel. Yay. Really nice to see you guys. Okay, and just one more for now. I see people like giving me hugs. Okay, we also have Vancouver, Canada. Hey, Vancouver. Hi. All right. Wonderful. Wonderful to have all these people with you. So right across from the campus from me, there's also a huge watch party taking place with members of the WEBB team. So the wonderful thing is that they actually are people that have worked on the mission, and they are part of our NASA Funny family. So hello WEBB team. There they are. Yes. A lot of people I recognize there. So it's incredibly important to me personally, and also to all of us at NASA, that the universe belongs to everyone. And we are thrilled to share this day with fans everywhere around the world. We'll say hello to some more later in our broadcast. So now it's time to start the main event. What you'll see over the next hour will be a collection of images newly processed by the WEBB science team. Only a tiny handful of experts have seen the images so far, and I can tell you that we have been so excited to unwrap them for everyone. We will be releasing each image in turn in real time. As soon as you see it on this broadcast, it will be available for download on the internet. On the screen below, you can see a timeline showing where we are in the show and what's coming up next. And by the end of the show, all 5 images will be available to everyone. So hopefully you can tell I'm excited. Okay, so let's do this. Okay, we're going to release the first image right here at NASA Goddard Space Flight Center, Maryland, and we're just outside of Washington, D.C. NASA Goddard is home to the project office of the Webb telescope, and the observatory portion of the telescope, the mirrors and the science instruments, were integrated and tested here before launch. So for many of us, including myself, seeing Webb come together bit by bit right in front of our eyes was an emotional and very inspiring experience. So it's kind of like a part of us was out there with Webb right now. A million miles away, part of our hopes and dreams are out there. So I'm joined now by Jane Rigby, the operations project scientist for the Webb mission. And she's a familiar face for people who've been following this before, so welcome, Jane.
Hi, Michelle.
Okay, so Jane, you not only get the honor of revealing the first image, but this actually got a little bit of a sneak preview. I understand there was a very select audience who's already seen the image.
Yes, so last night, on behalf of the project, I had the privilege of traveling to the White House with the NASA Administrator Nelson and other senior staff to share our first image with President Biden and Vice President Harris. And it was really fun. Oh my gosh. They really geeked out. We had a closed-door session where we got to walk through all the images and just share the excitement, and they were so thrilled, and they got the profundity of what we're seeing. And so now let's do it.
Okay, we've got the whole world watching. Are you ready to put the first image up?
Oh, let's do it.
Absolutely. All right, here we go.
Okay, so the first image is a deep field, and it's also a deep field with a cluster. So why don't we walk through this just a little bit? So if we come up and look at this image, first of all, it's really gorgeous, and it's teeming with galaxies. And that's something that has been true for every image we've gotten with Webb. We can't take blank sky. Everywhere we look, there's galaxies everywhere. And so, this image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And so the cluster are all these white, kind of ethereal galaxies. We're seeing them as they looked back in time. right? The speed of light is only so fast. And so as we're seeing distant galaxies out in space, we're seeing them as they looked billions of years ago. So these cluster galaxies, the white ones, we're seeing as they looked about the time the sun and the earth formed. And then behind the cluster, we have the gravity of the cluster is distorting and warping our view of what's behind. And so there are these galaxies that look stretched and pulled, kind of like they've been magnified because they've been magnified by the gravity of the cluster, just like Einstein said they would. And it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before. There's just a sharpness and a clarity we've never had. And so we can look at, if we zoom in on this image, and I encourage you as you grab this image at home, like zoom in. You can really zoom in and play around. There are galaxies here in which you're seeing individual clusters of stars forming, popping up just like popcorn. And then we also see in the background of this image, kind of littered like jewels all over the back of the image are these faint red galaxies. Now, that was what we built the telescope to do. The most distant of those are billions of years. We're seeing as they looked more than 13 billion years ago. And so galaxies like that one right there, this little red guy, you're like, okay, yep, what is that? Well, Webb got spectra to figure out what those galaxies are made of, and this is that one. We're seeing as it looked 13.1 billion years in the past, less than a billion years after the Big Bang. And we're seeing the elements of oxygen and hydrogen as well as neon. This is how the oxygen in our bodies was made in stars, in galaxies, and we're seeing that process get started.
Yeah, I want to give this a little bit of context. So this is now the farthest away galaxy that we have this sort of detailed information about.
That we know what it's made of.
We know what it's made of.
Yes.
And this was not a long exposure for Webb.
No, the previous record holder, right, the Hubble Extreme Deep Field, was 2 weeks of continuous work with Hubble, and it was just imaging. With Webb, we took that image before breakfast. The amazing thing about Webb is the speed at which we can churn out discoveries. So everything that you're going to see here in this broadcast is a week, and we're going to be doing discoveries like this every week.
That is absolutely incredible, Jane. So thank you so much for joining us. It's been an honor to be working with you. Congratulations on all your hard work.
Thank you. It's so wonderful to see it pay off.
So thank you, and I'll see you later on today, I hope. So
yes.
Enjoy the day.
Thank you.
Right. So from distant galaxies, we now turn our eye to something a bit closer. It's a planet, but not one in our solar system. Remember that Earth and its sibling planets aren't the only show in the universe. When scientists and engineers started developing JWST, the search for exoplanets wasn't even part of the plan. That's changed. Exploring exoplanets is now a major component of the mission and the subject of our second big reveal of the day. I'm going to send it now to our friends Nathalie Ouellette and Sarah Gallagher at the Canadian Space Agency in Montreal. So again, bonjour. I guess we're having a little. We'll go.
Okay. I'm Nicole Cologne, and I'm here to tell you.
Sorry for the brief pause there. We're now going over to Canada. Okay. Yep, we're all ready. Yeah. Okay, I apologize. We're having some trouble with the signal from Canada, but luckily for us, we have an exoplanet expert right here, just in case that happened. So this is Nicole Cologne, and she's an exoplanet scientist at NASA, and we're going to talk about this amazing new result from a very hot planet, I understand about 1,000 light years away.
That's right. The exoplanet is named WASP 96b, and it is this hot, gaseous, giant, puffy planet that it is about 1,000 light years away. So that's why today's release is so exciting, because it teases at what Webb is able to do for such a distant.
Absolutely. So talk us through what this discovery is and why this is so significant.
Mm-hmm. Well, this reveal that you're going to see is going to show that we have not had access to
before. So we've been able to use other telescopes to explore exoplanet atmospheres in the infrared, but not to this level of detail. And this is just one sliver of data that WEBB is providing us using the nearest specifically.
And there's something about infrared that is actually particularly good for the spectrum. So in this case, what we're doing is we're actually going to take the light and break it up into a rainbow and look very, very carefully at how much color is coming in each part of the spectrum. So I believe we have that image, if we can put that up.
Okay, yes, I believe we're revealing the spectrum right here. So we now have our spectrum, and this is exactly what you're seeing. As you just described with spectroscopy, what we did was we observed a transit of an exoplanet. We observed the planet as it passed in front of the star. Now, mind you, this is not a direct image. This is an indirect image. So we've seen the effect of what happens when the planet and its atmosphere passes in front of the star. The starlight filters through the atmosphere, and then you can break that down into wavelengths of light, and you get a bunch of what looks like bumps and wiggles to some people, but it's actually full of information content. So you're actually seeing bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
So we have the spectrum up here. Is there anything you'd like to highlight particularly?
Yeah, absolutely. So we have several features marked here. So I call them features. They're these, what I just referred to as bumps and wiggles, but what you're seeing here is a telltale signature, the chemical fingerprint of water vapor in these atmospheres, in the atmosphere of this specific exoplanet. And the other thing we can tell actually is that there's evidence of clouds and hazes because the water features are not quite as large as we predicted. So we can take that and infer that there are presence of clouds and hazes.
Right. Now, one thing that we really want to make sure people understand is with this particular planet, this is a hot world. It's actually closer to its star than Mercury is to our sun. And so we're not looking at liquid water here, but we're looking instead at sort of steam, water vapor.
Yes, this is an exoplanet. It's about the size of Jupiter, about half the mass of Jupiter. It orbits around a sun-like star, but it does it every about 3.5 days. Right. So it's extremely hot, extremely close in, nothing like our solar system planets. But that's okay, because what we're seeing is, again, the first exoplanet data from WEBB, and this is just the beginning. We're going to start pushing down to further, smaller but also
planets,
there's other
and being able to
three
take
other
measurements
just like
that will
with
add
the
to our
nearest
knowledge
in the infrared, as well as direct imaging modes along with the transit method. So there's a lot more was built by the Canadian Space Agency.
Is not only are we going to be looking at planets
there's
that are more like the Earth in the future, but we'll also be looking at planets in our own solar system.
Absolutely.
Yes,
Three
we're
other
going to have
instruments that
exciting
will
data
add to our
from
planets in our solar system, from Mars,
as well as direct
outward,
imaging
as well as
modes,
asteroids and
along
comets.
with the transit method.
Stay tuned.
So there's
for
a lot more to come. Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. But we'll also be looking at planets in our own solar system.
We have three more big
We're going to have
exciting data from planets in our solar system.
But first, let's take a look back at the journey that brought us to
from
this
Mars outward, as well as asteroids and comets. So
stay tuned
for a lot more to come.
Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. See dramatic moments in its life cycle, the news and images that come out in updates and press releases. We have three more big image reveals, that doesn't really give you the sense of the huge effort that goes on behind the scenes every day. Take a look back at the journey, the plans, schedules, and organization to keep everything moving forward. Are only possible really happens with years of hard work from a cast of thousands. WEBB started as an idea that took even the most enthusiastic. It grew first into planning spans, research projects, schematics, life cycle, the news and images. Then began the long journey to become real with the development of new technologies, cutting-edge engineering, and press releases. And finally fabrication. But that doesn't really give you the sense of the huge effort that goes on the visionary journey to how we all got here today, behind the scenes every day.
So today was
the plans, schedules,
final closeout of the purge.
Okay, guys, I can hear Rupa, but organization to keep everything moving forward really happens for the most part out of people's games.
For the very last time, right? You know, you're the last one to touch this.
WEBB started as an idea.
So that was the final operation. And